Everyone. I would like to welcome you all in our second day in the second international conference on chemicals and materials of emerging technologies, sustainable development goals, where today we will be talking about goal 7, affordable and clean energy. We will consider energy storage, batteries, solar cells, and clean energy. And in the evening session, we will be talking about goal 9, which is industry, innovation, and infrastructure. Today's morning session will be moderated by Dr. Abd Shakur, and we have here Zuair Qureshi who will be helping him. Mr. Mamlouk, the floor is yours.
Hi, good morning. So welcome to day 2 of the chemicals and materials for emerging technologies. So Professor Mohammed Mamlouk is the chair of electrochemical engineering science at Newcastle University with 19 years experience in electrochemical energy storage and conversion technologies. His Mohammed Mamlouk is a member of the Electrochemical Technology Group Committee of the Society of Chemical Industry and their treasurer. He has provided consultancy work to several energy conversion and storage industries. For example, New Cell Technologies, AFC Energy, and InnoCell Limited. He's based off of Newcastle upon Tyne, Newcastle University in the UK. And over the last 5 years, Professor Mamlouk have been awarded 20 research funding through national, EU, and international projects amounting up to £6.5 million worth of funding. So he mainly provides expertise in the field of electrochemical engineering, complemented by device modeling, fabrication, and optimization on electrocatalysis and membrane science and engineering. So his talk today will focus on offshore green hydrogen production, which is his forte, the challenges associated with it, and the opportunities. So I can now invite Professor Mamlouk to speak now.
Good morning, everyone. Can you hear me?
Yes, we can hear you and we can see you.
Right. Can you see my screen?
Yes, great.
Yes. 2 seconds. We'll just put it on full mode. Right. Well, good morning, everyone. I'd like to start by thanking the local organizer, Dr. Abdul Shakur, for his kind invitation to talk to you today about offshore green hydrogen production and really the latest thinking and the latest development and somewhat I see as the challenges and the opportunities in this field. So I'll start by briefly introducing myself, and then I will introduce the electrolytic green hydrogen production. I apologize if this is quite simplistic, the introduction, but I understand the audience have a broad range of discipline and background, so I thought I'd bring everybody to kind of the vocabulary that I'm going to use through the talk. So then I'll go over some of the commercial electrolyzer technologies, the alkaline, the PEM technologies, talking about their figures of merit and where they really excel, what areas and what are their limitations. Then I'll move on to some of the emerging technologies in terms of anion exchange membrane and solid oxide fuel cells, a bit more on some of technologies that's currently under still research and development, quite early technology readiness level. And then I'm going to move to the scale up of electrolyzers and looking at, as we move to larger systems, what are the challenges? We look at the cost of hydrogen between operating costs and capital costs, effect on the cost of the hydrogen produced, and what are the opportunities to produce hydrogen in offshore location, and really the UK vision around that, and I'll summarize. So I'll start introducing myself. So I'm the chair of electrochemical engineering, and I sit at the School of Engineering in Newcastle University. And my area really spans energy conversion and storage. So that's electrolyzers, hydrogen productions, fuel cells, as well as batteries, metal ion and metal air batteries. Myself, I have a broad background across disciplines. I have a BSc in applied chemistry and then I moved to chemical engineering and process control, and then I've done a PhD in electrochemical engineering. So I've got around about 20 years experience in specifically electrochemical engineering field, and I work on the interface between science and engineering. So work in terms of materials, so electrocatalysis, mostly focusing on earth abundant catalysis, membrane materials as well for some devices, where that is a restriction, for example, anion exchange membranes and polymers and separations. Batteries, I'll not go into details, I'll keep the focus of this talk about hydrogen, but also a lot of mathematical modeling and engineering and design of the system and fabrication. So to give you a bit of flavors, what I'm working on at the moment, so the current projects, I have one European project working on development of anion exchange membranes. We'll go in a bit in details what that is. So these are targeted for electrolysis of seawater. So if we have low-grade water or seawater, high salinity, can we electrolyze it directly with minimum pretreatment? So looking to address the challenges around the catalysis, the materials, the membranes, and the systems. I have a very large UK funding, 5 years funding called Ocean Refuel. We are leading the energy to carbon-free fuels. So what we're looking in this project is we're looking at to exploit the offshore resource, particularly the wind, for example, in the UK. And then we're looking at how can we go deep offshore, convert in the offshore location the energy directly into hydrogen. So produce it offshore, and then potentially transport that energy in the form of hydrogen or ammonia or other form, as a chemical form, from those offshore locations, either to the UK or export it abroad. The next project we're looking at is improving the polymer of anion exchange in terms of its stability towards particularly oxidation and radical attacks. The following next project we're looking at sustainable heavy-duty trucks. So in this project, we're developing electrolyzer that you could use waste heat from the engine to actually electrolyze water, produce hydrogen, oxygen, to inject it in the engine that is running on ammonia to improve the combustion of the engine and reduce emissions. And finally, the final project is looking at optimizing at the network level hydrogen fuel transport, as well as potentially heating applications. Right, so I'll start now the introduction of what green hydrogen is about, really just some very simplistic definition and explaining the fundamentals. So from the word electrolysis, the word electrolysis is obviously from the electricity. So it means the decomposition of water using mainly electrical energy. But as you will see, but we could also supplement that also with thermal energy. So electrolysis is splitting the water, decomposing into hydrogen and oxygen. How old is electrolysis? It's one of the oldest electrochemical systems known, in fact. So it's known back all the way back to the 1800s. And in fact, one of the earlier fuel we used was hydrogen, and it was used in combustion over 200 years ago, before obviously we moved to fossil fuel combustion engines. But obviously hydrogen is still used to power and propel our spacecraft to go and explore the space. So it is a proven technology. So it's been there, particularly alkaline electrolyzers, as we'll go and explore a bit more details, is being known for over 100 years at a large scale. So it's quite established technology. It's produced very high purity hydrogen, so above 99.9%. Depends how much purification we want to do to the hydrogen, and depending on the technology of the electrolyzer, we can have 99.999% hydrogen. So we use this technology at the moment where purity is a premium, so some electronics manufacturing, or for example, when safety is concerned, where you don't want to store a huge amount of hydrogen, you can produce it on demand. The reason, obviously, we don't use it at a large scale and only roughly around about 5% or a bit less than that of the total global hydrogen production come from electrolysis is cost. So obviously, hydrogen is at the moment produced by methane steam reforming and other hydrocarbon reforming as the main source of producing hydrogen. And we'll look at that in details in the next few slides. But if we look into transit to use of renewables, then electrolyzers are one of the key technologies at the moment that can be scaled and look promising in terms of producing hydrogen from renewables. The technology itself is very compact, so it wouldn't have a high or large footprint. So if you look at the image here, that's around about 2 kilowatt electrolyzer. In terms of power, it's the size of 2 books next to each other. So it's not very large, but yet produce quite a high power output. And the way that these electrolyzer systems work, they are modular, so they're made of cells, just like any electrochemical systems in batteries. You stack them together to get the power requirement that you need. The similar thing here. So in this stack, you have 10 cells. So you see those black lines, it's just a space between multiple cells. So each cell have an anode and a cathode, so positive electrode, negative electrodes. And by combining 10 of these cells, you increase your capacity. So if you double them, you will double your hydrogen production. Okay, so it's very modular, very scalable. And the way we quantify these systems is by talking about the hydrogen production rate or equivalent current per unit area, right? Because the amount of hydrogen produced is directly proportional to the current we're putting in. Okay, so let's talk a little bit about the energetics of the water splitting. So obviously the cost comes from the energy needed to split the system. And let's talk about the efficiency of the system. So as I said, so we have water as the feedstock. We provide energy, mainly electrical, if we're at lower temperature. And if we're operating at higher temperature, then we'll have to use electrical and thermal to split it into hydrogen and oxygen. So if we look at the high heating value of hydrogen, around about just under 40 kilowatt hour per kilogram. So if we are at the system level, electrolyzers operate around about 50 to 60 kilowatt hour per kilogram. So we're talking about efficiency between 70 to 80%. And if you look compared to steam methane reforming, the energy requirement is slightly higher. So it's around about 46 against the minimum here is 48 kilowatt hour per kilogram. But if you look at the cost, obviously the cost of electrolytic hydrogen is significantly higher, roughly $6 to $3 per kilogram of hydrogen, so roughly double. And the main reason for that is the form of energy. So at the moment, obviously the steam methane reforming uses heat as energy input, and that heat is provided from burning the methane itself. However, electrolysis is using electricity as the main energy source, and that electricity at the moment mostly generated from obviously methane and other fossil fuel, burning them. So obviously those processes to burn the fossil fuel, to convert them to electricity, to transport the electricity is inefficient. And that's why the costs end up double as we're looking at wheel-to-wheel system. But as we transit to renewable sources, the cost of the hydrogen forecast to grow, to get lower and lower. So if we look at today's, in the UK, today's steam methane reforming of hydrogen, because of the significant recent increase of the cost of methane and the continuous drop in the cost of renewable energy, at the moment, if we compare the actual cost in terms of energy to produce them, the cost will be equivalent in terms of producing hydrogen by both methods. So as we increase the temperature, operating temperature of the system, so we're talking about sub 100 degrees C into close to 1,000 degrees C, what happened is we're shifting the energy demand from mostly electrical to electrical and heat. So we're supplying more of the energy as heat and less as electrical. So we do that normally where we have a high heat source, waste heat. So for example, it could be coupled with nuclear reactors where you've got a lot of thermal energy, waste heat that you could use to produce steam and run those electrolyzers at much higher efficiency because you need much lower than electrical energy input. So if we look at the low temperature system, so the stack itself, so where the reactions taking place, where the water splitting happen, as I said, typically we're at the system level, depending how much our production rate or how much our current density is. So the higher the current density, the higher obviously the increase on the demand on the energy because the system becomes less efficient. But if we look at the stack, so this is the electrolyzer purely, and this is the system. So you look at the electrolyzer system is just under 50 kilowatt hour per kilogram hydrogen. And if we look at the system, we're around about 56, 58 kilowatt hour per kilogram. And the reason for that increase is mostly due to actually the electrical conversion. So if you look at that, yes, there is a balance of land consumed for heaters, there is dryers of hydrogen, purification, and so on, but the majority of that energy actually goes to the conversion of the electrical energy from AC and high voltage to DC and lower voltage. You've got transformers, they're not inefficient, they are inefficient. You've got the conversion of AC to DC, again, is inefficient. So that where some of the efficiencies come. Additional efficiency. So if we look at the electrochemistry, really, as I mentioned earlier, it takes place in two electrodes. So you've got an electrode that is positive, we call here the anode, with a higher potential, and that's where water get oxidized and we evolve oxygen. And the other electrode we call the cathode, or the negative terminal, and that's where the hydrogen get evolved, where the water get reduced. And to keep the charge neutrality, you've got to have ionic current flowing between the anode and the cathode, between the two. So that type of ions that are transported really dictate the technology of the electrolyzer. So if that is, for example, liquid alkaline solutions, therefore you have hydroxide ion moving between the electrodes. In this technology, we call it alkaline electrolyzer. If this is hydronium ion or proton moving across from one electrode to the other, we call this PEM, or proton exchange, or acidic environment. And you will see later on, and if that is a solid oxide ion, if it's an oxide ion that is moving between them in separator, then we call that a solid oxide electrolyzer. Okay, so let's look at some of those technologies that we have. So we'll start with the alkaline, the oldest technology. Here, as I said, this technology is very mature. It's been there for 100 years. It's still got significant room for improvement and to go further. So the very simplistic design of the system is, as I said, you've got an anode and a cathode, and then you've got a circulating alkaline electrolyte next to each electrode. So you have two streams of electrolyte circulating, and you have a diaphragm separator in the middle, obviously to stop the hydrogen and the oxygen that we're producing from being mixed together. So that diaphragm is effectively a porous sponge, right? It's a porous polymer, and it's filled with zirconia, and it's got small pore size that are flooded with that KOH electrolyte. So it allows the ion to move across that separator, but it reduces the gases crossover. So typically those electrolytes are operating at atmospheric pressure to keep those pores filled with electrolyte, but they could operate as a pressurized system, but it has to be equipressure. So the hydrogen chamber pressure and the oxygen pressure should be equal, so that then you're not pushing the electrolyte through the pores from one side to the other, and you don't then have a huge gases crossover. The main advantage of operating in alkaline media is really the ability of using transition metal oxide at the anode. So because it's alkaline media, metal oxide are stable, i.e. they won't corrode and leach into solution, and they have relatively decent activity. Still an order of magnitude lower than that you will get in from precious metal, but still quite active enough. The other advantage, obviously, for the cathode side, for the hydrogen side, you can use nickel or stainless steel, again, very cheap materials, as well as the component of the system. And therefore, the main advantage of such a system, because it uses abundant material, is its low cost. But obviously, while it is at low cost, we need to make those cells bigger and add more cells, because at a given efficiency, the rate or the current production is lower than if we were using precious metals. So if you look here at, for example, commercial systems, so you're seeing here, that is a stack. So you see it's relatively large, typically in the 1 meter or 2 meter square areas. You've got the hydrogen and the oxygen gas liquid separators there, the main alkaline tank, and this large unit here is a transformer to convert, obviously, the electrical energy from high voltage to lower voltage suitable for the electrolyzer. So you look here at the diagram. So you've got alkaline system, alkaline tanks, pumps circulating. So one goes to the to the anode to produce oxygen, which typically is vented to the atmosphere, not used. The other one to the hydrogen, which then goes to purification and compression. And because we're circulating the liquid electrolyte, the alkaline solution, it also works as a coolant. So we can cool it through heat exchanger before it gets to the tank, and therefore keep the stack at the desired operating temperature. As I said, this technology been there for a long time, and it's been demonstrated as a large scale. So this is around about 2 meters here across diameter, and we had plants of hundreds of megawatts being installed globally of those systems over at least been operating for 50, 60 years. So if we summarize the main characteristic of alkaline system, so we start with the current density. So how high the production, if you like, of hydrogen per unit area, the intensity of those systems or the productivity. So it's relatively low, so 0.2 to half ampere per square centimeter, but they live for a very long time. They're very stable. As I said, the main advantage of using alkaline system is actually, while we can use non-precious metal, they're still stable. So we've got a very long lifetime. As I said, it's a mature technology. We have a very large area electrode. The single stack, so that is one stack, they are still modular. At the moment is around about 2 megawatts. So if you want to, for example, have a 4 megawatt or 6 megawatt plant, you have to install 3 of those electrolyzer systems. Capital cost is around about $600–700 per kilowatt. And as I said, they have to have equi-pressure on both sides, typically either atmospheric, but certainly below 30 bar, and has to be pressurized, both the hydrogen and the oxygen. The main limitation of this system really is the cold startup to minimum load. Because they have a high thermal capacity, we're talking about a huge volume of liquid electrolyte in the system, it takes significant amount of time to heat them up to go to the operating temperature we want them to operate. So that means we take us around about 20 minutes to start that system from cold. And this is particularly a challenge if we're going to couple those systems with renewable electricity, because obviously if we have a lot of intermittency, it means we have a lot of downtime waiting for the system to warm up to operate. The other limitation is the minimum load. So those systems have a minimum load of 15%. So on a 1 megawatt, for example, system, the minimum we will be able to operate is 150 kilowatts. Okay, so if it's below that, then we won't be able to operate the system to keep it ticking. So we'll have to switch it off. So in that case, one way to address it, if we were to couple that with renewable energy, is to then reduce the stack size and have multiple stacks to reduce our minimum load that we need. However, that comes at an increased cost, as you will see later, because obviously there is economy of scale. The larger the system, the lower the cost. Okay, I'll move to the next known system or commercial system, the PEM system, or polymer electrolyte membrane water electrolyzers, or also known as proton exchange membrane water electrolyzer. And as the name suggests, in this case, we have proton exchange or polymer exchange. So we have a solid electrolyte. It's a polymer. Typically, it's perfluorinated polymer to give us good oxidation stability and long lifetime. And that polymer then have tethered functional group, usually sulfonic group, so quite acidic group. And when those are fully hydrated, then the proton can shuttle and diffuse through the pores. It's obviously nanopores in that system, so the proton or the hydronium ion can transport rapidly through these nanopores, while the gases won't be able to or have very low permeation rate. So the advantage of that then is that we can make a thinner membrane, so 50, 100 micron thick, instead of, for example, 500 micron in the alkaline separator. So they're much thinner, lower permeable to gases. And because obviously we do not need to circulate the electrolyte at the cathode, because we only need water as a reactant at the anode. So we only pump water, very small flow rate, just what we need for the reaction with a small amount of excess to carry on the reaction. That water then evolves of oxygen and hydronium ion, which then permeate the membrane and go to the cathode to produce hydrogen gas and release small amount of water that have been dragged across. So the advantage of that, then the system have a very fast response time. The membrane is impermeable or have very low permeability, so the minimum load can go much lower than 15% that we saw in alkaline, can go down to 5%, because we don't need a huge amount of current to counter any gases permeation through the membrane. So those are the main key advantage of using PEM. What are the challenges and the limitation? Well, the challenges are it's able to perform very high current density, very high energy density, but that comes at the cost of using precious metal catalysts. So typically we're using platinum at the cathode, and more limiting is actually the iridium ruthenium oxide that we have at the anode, which we will discuss further down the presentation when we talk about these challenges in terms of scale up. So if you look at a NEL, for example, PEM system here, so again, 2 megawatt system. So you can see it can be installed in 2 ISO containers. If you look at here, this is the transformer, the power conditioning, significant size of the system. This is the cooling of the system. So this system can operate up to 3 amp per square centimeter. So around about between 2 to 3 amps. So 4 to 6 times current density we saw in the alkaline. So huge amount of heat to get out of the system. We need large cooling, but the actual stack itself in all that large container is just simply this unit here. So you can see it's very, very compact. The rest is just balance of plant, conditioning of the gas. So for example, pressure, swing adsorption to remove water and so on. So as I explained earlier, so in the system more simplified, the water is only being fed to the anode side of the system. Oxygen typically is vented, and then the hydrogen stream, there is no water circulating. You've got hydrogen coming out with small amount of water being dragged across the membrane. You trap the water, you have some buffer. If you want a very, very high purity, 99.9999%, then you have a deoxidizer to remove any traces of oxygen, a dryer, and then a storage. So to summarize, what are the key characteristic of such a system? So as I said, high current density, 1 to 3 amp per square centimeter. Similar operating temperature to alkaline, 80 degrees. Also long life, because we're using obviously precious metal. Long lifetime of the stack. Area not as big as alkaline, particularly because we don't need it, because the current density is much higher. Stack capacity, again, around the 2 megawatt size. Cost is higher because obviously we need precious metals, but also some of the component and the electrical contact where we put that catalyst need to be made out of coated titanium or tantalum. Again, that has to be coated with precious metal to stop it oxidizing. It can produce hydrogen at differential pressure, so the oxygen could be at atmospheric, the hydrogen could be compressed. It needs pure water, but you could see we have at least a quarter waiting time compared to alkaline systems. So only have 5 minutes from cold to start up. And this is mainly because obviously we have lower heat capacity. We're only circulating small amount of water at the cathode to increase the temperature of the system. It's using a solid electrolyte. And because of the low gas permeation through the solid electrolyte, then our minimum load is only 5%. So you could see it'll have more advantage into coupling with an intermittent energy source such as renewable. Okay, now if we move to more emerging technologies, the anion exchange membrane and the solid oxide fuel cell. So the principle of anion exchange membrane technology is really similar to that of PEM. So it is a solid electrolyte, but instead of conducting hydronium ion, we're conducting here a hydroxide ion. So we have then the advantage of the alkaline environment, but obviously the advantage of using solid polymer with lower permeability. So the polymer, the membrane separator, is typically hydrocarbon, but could be perfluorinated. It's got tethered group mostly based on quaternary ammonium or amine based, so positively charged nitrogen-related groups, which then have the ability to conduct hydroxide ion when it's again fully hydrated. So the advantage of the system, as I said, is because it conducts hydroxide ion, is then we are in a similar alkaline environment. But the difference is it's not truly alkaline environment, because we're talking here about solid electrolyte and we're trying to compare it to a liquid electrolyte. If you recall, in the alkaline system, we typically use around about 7 molar alkaline, so quite a high caustic concentration. So while the pH of this system, obviously you can't talk about pH because it's solid electrolyte, but the equivalent pH we're talking about between 10 and 11. So it's much, much, much milder alkaline conditions. And the thing is, the material stability and activity is dependent on the alkaline concentration. So while we could still use transition metals, they're less active under this condition and they're less stable if we just feed water. So obviously the alternative then is then to use some what's called supporting electrolytes. So effectively still use alkaline solution feed and just use that solid polymer to improve the gas permeation. The challenge with that, obviously, if we were to use higher alkaline concentration and higher temperature, that the quaternary ammonium group that is in the membrane will degrade from those high alkaline concentrations. So these are the current summary challenges of those alkaline systems. They have a potential, but still under research and development. So if you look at the operating temperature is lower, 40 to 60 degrees, to really suppress that, minimize the degradation. Current density is higher than alkaline, up to twice as high, particularly because now we have a thinner membrane, so we still have some energy saving compared to the thicker alkaline porous membrane. But if you look at the lifetime, it's significantly lower than PEM and alkaline systems. As I said, it's not mature, it's still quite in a small production. So we're talking about not even 0.5 meter square systems, quite smaller systems, we're talking about kilowatt systems rather than megawatt systems. And there's only a handful of companies who produce this, one of which is Enapta system. So if you look here, that's effectively 2 meter here. So they really have a very small system, and their vision is to stack these 2 kilowatt systems. But if we're talking when I go to megawatt and gigawatt system, you could see that that might become quite expensive rather quickly. And if you look at the energy requirement is not lower than the other two systems, particularly because we're not using high alkaline concentration. So we don't have a very high activity from that catalyst that as much as we have when we have a high alkaline concentration. But obviously, because of the good gas separation and we're not using liquid electrolytes, so we have a relatively faster startup and similar minimum load to that of PEM. There've been advancement, so people trying to improve. So this is the voltage or the efficiency of the system, and this is the current density or the rate of the reaction. You could see work by us and others looking to improve that system and try to get it. So if you look at the blue line here, that is the latest performance of PEM, and the red line is of AEM. So in theory, we are having similar performance to PEM. But the reality is that this is actually while the performance is similar, the lifetime will be significantly lower. So the only way for us to achieve similar current density here or similar rate is by using significantly thinner membrane. So if you think about hydronium ion and hydroxide ion hydrated, hydronium ion is much smaller. So the energy what we need to move hydronium ion in a membrane is roughly at least half of that to move a hydroxide ion. So for us to be able to actually achieve similar efficiencies and similar energy requirement to move it across, in this case, we have to halve the membrane thickness. And that comes at a cost because that will deteriorate the mechanical property of the membrane, will increase gases crossover, and reduces the lifetime of the system. So it still have challenges to go. And what probably be ideal is that the alkaline system will typically operate at a lower current density, and because it can afford to do so by adding more cells because it's a cheaper system, while PEM system will operate at higher current density because it have more expensive material and more active catalyst. Similarly, remember how I mentioned earlier, the catalysis of, for example, evolving oxygen from water is particularly challenging as we move away from high alkaline concentration. But there have been, again, recent progresses. We're looking at binary and ternary and multiple mix of catalysts, and you could see huge significance from the activity here in poor alkaline concentration here. So you have 0.01 molar. So this is typical catalyst used in alkaline system, very, very poorly performing here when you dilute the alkaline as expected. But new catalytic system shows significantly higher activity, which is promising. However, the stability over very long lifetime, 60 to 80,000 hours, is still obviously far away target. The other type of emerging technology is a solid oxide water electrolysis. As the name suggests, we're using a solid conductor, so solid typically made of metal oxide. So one common example is yttrium or yttria stabilized zirconia. So you've got zirconium oxide and you dope it with small amount of yttrium, around about say 3–5%. And what that does, it creates oxygen vacancy. So then oxygen ion can hop through that solid conductor. But because it's obviously a solid conductor and we're talking about oxide ion moving across it, the diffusion or that permeation rate is very slow, right? It's energy intensive. So we have to go to quite higher temperatures to have that system or the ability to move that oxide ion efficiently through that conductor. So typically those systems operate above 600 degrees C. We're talking about 800 up to 1000 degrees C. The main advantage of operating at such high temperatures is that the kinetic become obviously very rapid because you have it such a high temperature. So you could use non-precious metals similar to alkaline system. You could use nickel, for example, on the hydrogen side, and stainless steel, potentially depending on the operating temperature. And then you could use metal oxide, mostly perovskite structures, metal oxide at the oxygen side. And those could include transition metal, nickel, cobalt, and iron. So one of the common one is barium strontium cobalt ferrate or lanthanum strontium cobalt ferrate. Obviously, the lanthanum is a rare earth metal, so we need to be aware because some of those perovskite could use rare earth metals, but obviously there are some substitution with more abundant, such as barium elements. So those systems really, because of the very high operating temperatures, are not meant to really coupled with renewable, because obviously it takes a long time to get them to the temperature. They will degrade quickly if we cycle them a lot, so thermally, so switch them on and off, because obviously you have different materials, different thermal expansion. So as you heat them up and down quickly, they will delaminate, create mechanical stresses, and it will fail. The other challenge, obviously, the very high operating temperature makes the sealing of such a system also challenging. So they don't typically operate at higher pressures. So if we look at typical solid oxide systems, so current density is reasonable, up to an amp square centimeter. This is temperature 700 to 1000 degrees C. Lifetime is not very high at the moment, below 20,000 hours. Area is very small. Obviously, there is major challenges in terms of manufacturing those ceramic and solid oxide as the thin layers at a very large scale, right? Because of the thermal stresses and the manufacturing process, you have to heat them to very high temperature to synthesize them and make them. So try to get equal heat distribution, uniform machining at such a large area is a challenge. And that's one of the reasons why we have a high cost. So a lot of this high cost is actually the need of the high thermal temperature processing and manufacturing of the system. So that's why it's a smaller system, it's a smaller area. They're very efficient. If you look here, energy requirement, 40 kilowatt hour per kilogram. So if you remember, so we're close to the thermal neutral value of hydrogen at room temperature, sorry, the high heating value. And as I said, big part of this system is split that we supply most of that portion of the energy through heat, through the steam. It takes a long time to start, over 10 hours. It's understandable. You have to go from room temperature to very high temperature, 700 to 1000 degrees, and you've got to run that slowly to minimize stresses. And obviously it has quite a high minimum load to keep it at the desired temperature because of the high heat loss. Okay, so if I move to some of more the technology we're looking at now that we think also have potential to reduce further the cost. One of the technologies is membraneless or undivided cells. And in these systems, what we're looking at is controlling the flow of the electrolyte to achieve the gas separation. So get away completely with the electrolyte. And you remember in PEM system, for example, I said they could leave 60 to 80,000 hours, and that mostly actually dictated by the electrolyte degradation, by the polymer degradation rather than the precious metal catalyst. So one way to do that is having, for example, flow through systems. So you've got the flow, and if you have a porous electrode, you're forcing the gas bubbles produced, so you can have hydrogen on one side, oxygen on the other side, and achieve that separation without a membrane. Obviously, there are some challenges around that in terms of, let's see if I can get that video to work, around the separation, the distribution of the flow at those electrodes goes to the meter square size. So they've been looked at some modeling and some optimization of the system, try to get uniform distribution in terms of the gases and the bubbles between the two electrodes to achieve that separation. But obviously, as the system gets bigger and bigger, you start having challenges in making sure you've got uniform flow across the whole electrode, and then you'll start having some gases accumulation, which then you have gases mixing and reduce the purity of the gas being produced. Other systems being looked at, also rotating electrochemical systems. So if we start spinning those electrolyzers, it means we can have very high mass transfer rate. We have a very rapid removal of those gas bubble that is being produced at the surface, which then it means we are able to operate at much higher current densities, which then means we will reduce the cost of hydrogen we produce. Okay, if we talk about then now, what are the opportunities and the challenges in terms of scale up? So obviously globally, particularly with over the last 3 years, we saw a huge increase in the demand on hydrogen and the interest. So if you look at this figure here in 2016, globally you have around about 40 megawatt of electrolyzers installed. End of last year, that is increased to 200 megawatts. So there's a significant increase in the uptake of electrolyzers for hydrogen production at large scales, a lot of that coupled with renewable energy. And if you look, the majority still alkaline systems, with PEM obviously catching up. But what are the challenges of going to such a scale? So obviously, if we look at the forecast of how much electrolyzers we need, we're talking about hundreds of gigawatts. So International Energy Agency estimate 180 gigawatt by 2030. So it's a significant amount of increase from a megawatt systems to hundreds of gigawatt systems. And if we're talking about 2050, we're talking about 850 gigawatts. So we're talking about few orders of magnitude increase in the production of those electrolyzers. And at the moment, the majority of those systems are actually made by hand rather than automated manufacturing process. So you remember when I mentioned about the PEM system that needs iridium oxide, for example, at the anode. So that, for example, the material scarcity and cost become, again, a significant challenge. So if you look at the iridium cost, for example, over the last year, it's actually gone from $50 per gram up to 200. So went 4 times over a very, very short period of time because, for example, of a sudden hike people on terms of demand for electrolyzers and other applications. And part of the challenge is that iridium is actually a rare earth material, and we don't even actually directly mine it. So it comes as a second product from mining platinum, and we have a very low content, around 1 part per million of the Earth's crust. So if we look at our annual production of iridium, so if all the iridium we produce come to make electrolyzers, the maximum capacity it will make is around about 3.5 gigawatts per year. So if we're looking by 2030, if we accumulate all this 3.5 gigawatt, we'll have a maximum of 47 gigawatt worth of electrolyzers. And if you compare this to already announced project of 54 gigawatts and promised projects of another close to 100 gigawatt, you could see that we're going to start having problems scaling up those systems, particularly if it's PEM. So because the cost of materials will go up, the technology then become way too expensive to scale. If you look at the EU, they're promising 40 gigawatts by 2030, the UK 10 gigawatts. So you can see there's a lot of promise of a very large system increase, but that will make a huge squeeze on those precious materials, even on non-precious materials such as nickel and cobalt. We saw a significant increase in the cost, for example, from demand on electric vehicles. So, okay, so that's one challenge in terms of the materials, but obviously on the other hand, there are some benefits to be had when we go scale up in the system, when we use the larger systems. So both in alkaline and PEM system, there is economy of scales. As this electrolyzer stacks gets bigger, then you have less component, less balance of plans, the manufacturing cost goes down, therefore you can have significant costing anywhere between 20 and 40%, depending on the size of the system and the technology we're using. So if we talk about now the hydrogen cost, so in practice at the moment, hydrogen costs 90% of the hydrogen, between 80 and 90, depending obviously on the electricity cost, of the hydrogen costs we have from electrolyzers comes from actually the electricity cost. And the system, the capex cost, contribution to the hydrogen cost is very small. It's below 10%, depending on the electrolyzer technology. And the main reason for that is, yes, while the capital cost is high, the system have a very long lifetime, 80,000 hours. So the contribution, therefore, is low, provided that we operate the electrolyzer a sufficient amount of times, at least more than half of the time. Okay, so you could see, obviously, the longer we operate the electrolyzer per year, or the percentage of time, more than half of the time, then the capex contribution to the hydrogen cost become insignificant. Equally, obviously, depending on the electricity cost, you could see a hydrogen cost significantly influenced by the electricity cost. It's, as I said, it's 80–90% of that cost. But also you could see how much we're going to operate that electrolyzer is really dependent on the size, as I mentioned earlier, because of the intermittency of renewables and long startup time, for example, in alkaline electrolyzer and high minimum load. We need to think carefully of the size of the system to ensure that we have maximum utilization and not having an expensive system that is underutilized. The other thing to bear in mind, so on the current model, so electrolyzers coupled with renewables and mostly operating at nighttime where the electricity is cheap and abundant and switched off during the day or during the high peak. So you could see as we increase the number of electrolyzer operating hours, it means we need to operate at the moment at the current model at times where the electricity price is very high, right, all the time. So in practice, what we do is we don't do that. We switch it off, so that way we operate them roughly half of the time. But if we're looking at using them offshore, so in a faraway location, we're probably looking at operating them all the time, using all the output to convert it to hydrogen. So let's look at offshore hydrogen. So as I said, offshore is a very rich resource, particularly, for example, in the UK, we're talking about floating wind. You could be also obviously using floating solar, you could using tidal. But in this example, I'm talking about floating wind. So you can go deep offshore, and the main advantage of going deep offshore is you have much less intermittency. You have almost continuous wind supply. So the downtime from the wind is very, very small, which means we can operate continuously the electrolyzer. And therefore, we could move, for example, to alkaline-based electrolyzer where we don't have to switch on and off. The other thing is obviously because you have that large platform for wind turbine, you have plenty of space to include the electrolyzer system. As I said, so a container will be something like this dot size on that platform. So you need 6 containers, and that will, for example, supplement the 15 megawatt capacity of that floating wind turbine. So we can convert all that capacity into the system. Obviously, that can be networked over a larger wind farm. But then the challenge really in these systems comes, where do we store that hydrogen we're making? So obviously, one option is you can pipe it inland, depending how far you are, but it is much more economically viable to send the energy through chemical energy through hydrogen rather than through cable, particularly as those wind farm size goes into the gigawatts and gets bigger. So we can send it as pipes, Or obviously, depending on the distance of the intended use and where you are, there will be a range of solutions. And that's are some of the scenarios we're looking at. I'll come to that in the next slide.
Professor Mamlouk, due to time constraints, if you could just
yeah, wrap up. I have one more slide.
Sure,
Okay.
thank you.
Yeah, so where do we get the water? Well, we mostly get it from seawater. So we desalinate it here. Some people looking at directly using seawater as the electrolyte without purification. But if you look at the cost of the desalination and the energy cost is sub 1%, it doesn't make sense to actually at the moment to use direct seawater because of the high corrosion environment and energy requirement. But one thing to bear in mind, if we couple with renewables, that we might be affecting this 60 to 80,000 hours reliability. So that's my final slide here is I want to say that we have a different solution to depends where you are. So if we are in the UK in north of Scotland, we have a lot of gas network here. So the solution is potentially piping it and linking it to industrial cluster where you're producing CO2 and you can capture it and then send here hydrogen to provide the high heat for those industrial processes. Other part of the UK have good electrical grid, so we can send electricity directly. Other solution, for example, in Australia, you could convert that into liquid hydrogen, or for example, to ammonia offshore and then ship it. So depending on the supply, the demand offshore, there are a range of solutions to do that. So to summarize, alkaline electrolyzers are more established technologies, doesn't require precious metal, but harder to integrate with renewables. PEM has a faster response, more compact, can produce hydrogen at pressure, but require precious metal, which might be challenging for scaling up, particularly around the iridium. Most of the cost of the hydrogen produced, 80 to 90%, is the cost of the electricity. And as renewable electricity cost goes down, makes hydrogen, green hydrogen, more viable. And finally, hydrogen has from offshore has very high potentials because it's a good source of way to store the energy from remote locations. I'd like to thank you for your attention and the funders for supporting my research work. Thank you.
Thank you, Professor Mamlouk, for the talk on green hydrogen production. And I would like to open the floor now for any questions.
Ask a question?
Yes, please go ahead.
Yes, Professor Mohammed Mamlouk, thank you very much. It's a very nice and inspiring lecture. I am working in a chemistry lab, and you know the scale of fundamental chemistry research. So how do you work with chemists who work with milligrams and grams, maximum grams of materials? I was interested by the catalyst part of your work. So how do you conduct research with the chemists to develop new catalyst or supported catalyst, and what are the challenges in your field? And also a second question is related to the recycling of all these systems that produce hydrogen.
Yeah, absolutely. So in terms of the first catalyst, the electrocatalyst, yes, I do work with a lot of chemists. So it depends on really, as I said, we have projects spanning the science and the engineering. And you rightly saw so most of the catalysis work is more on a milligram to a gram scale, because obviously it's synthesized in the lab, there isn't that scaling. So we do that testing on electrolyzers, what we call a single cell system. So maybe up to 100 centimeters square by one cell. But we also do an industrial research, for example, on larger size polymers. We do consultancy work with industry. And then we look at, for example, 10 to 5 kilowatt system, so much larger system. And then we have a facility at the university where we're testing at hundreds of kilowatts. So we have effectively, that's a commercial system connected to the grid and then can connect the produced hydrogen into the gas grid. So we have different scales really at and research at different points and the different facility and different people working on it. But there is a lot of useful learning in terms of having the broader picture. So for example, if you're making certain catalysts using certain material, you know that it can be scaled because you understand how the complexity of the larger system, then you will say, okay, you know what, this route is not viable or this synthesis route is not going to work. In terms of your other questions, in terms of what I see the challenges of the materials. So as I said, the main challenges in my view of PEM is it's because it's acidic environment, you can't use precious metals. So you have to use precious metals and those will be expensive. Yes, you're right, they can be recycled. And this is one way looking at things, but because the time is running out, our mining capacity is limited and those systems will live for a long time. So yes, so we will only have a range of solutions. Remember how I said it depended on the intermittency application. So PEM will play a role, but it can't supply all our hydrogen demand. So we're gonna need to have other electrolyzer technology. And this is why I favor looking at alkaline environment or alkaline similar environment to be allow us to use those non-precious metal so we can scale up all those systems without having constraints on the materials. In terms of the design and the recycling, this is just emerging now. We're having design for recycling. So far, we only focus on the performance, on the durability. So we talked about, for example, 60, 80,000 hours because the capital cost is high. You want those systems to last that long. So that way we use mostly perfluorinated, for example, polymers. But now there's a drive to move away from perfluorinated polymers to use more friendly polymers. But the reality is if you do so, use hydrocarbon, you're sacrificing your lifetime and then you make the system too costly.
Okay, just one comment. Is it possible to make a catalyst and get it tested in your lab?
Absolutely, yeah. I'm open to collaboration,
Okay.
of course.
Thank you. Thank you very much.
Pleasure.
All right, Dr. Shane, I think, has a question as well.
Sure.
Yes, thank you very much. Nice talking. I'm Shane. I'm working at the CAF. So I have one comment. In the last slide, you introduced the reverse osmosis water using combined with any existing electrolyzer. Currently, the auto process using polyamide, they have the removal capacity 99.8%. Whatever we have general seawater quality, we have more than 400 ppm of the total salinity that cannot be used for any existing electrolyzer. Even the ES paper show, but I doubt the reliability of the data. Anyway, so NEOM City, the NEOM City project in Saudi Arabia, gonna use thermal-based desalination water product instead of using reverse osmosis product water.
Yeah.
So mostly the thermal-based water provide the water quality that requires the 80 mega ohm of pure high quality water. That's my comment.
Yeah, so you could use obviously multiple processes. Obviously, thermal is more energy intensive. So if you have a thermal source, you could use it to desalinate water. So when I say reverse osmosis, so you could have multiple membranes to get to the purity you need, or you could obviously use the traditional way where you supplement the reverse osmosis with ion exchange system and to get to the purity level you want. But it's really when you're looking, you need to look at the energy of the whole system. So obviously thermal, as I said, will have high demand. So you need to look at the total energy of that system. As I said, if you have some thermal source, that's fine. But if you're looking in deep offshore location, you will not have that thermal source easily to use. Obviously, you could integrate some of the thermal waste heat from the electrolyzer, but that is depending on the operating temperature of the electrolyzer that you're using.
Thank you.
Thank you. If we do not have any more questions, I would like to move on and invite the next speaker. Thank you, Professor Mamlouk, for your talk. All right. And next, I would like to invite Professor Mitsumasa Iwamoto. He is a professor emeritus of Tokyo Institute of Technology, a fellow of the Japan Society of Applied Physics, the Institute of Electronics, Information and Communication Engineers, and the Institute of Electrical Engineers in Japan. His current interests focus on organic electronics, mainly on the electrical, optical, physical, and dielectric properties of thin films, monolayers, liquid crystals, and molecules. So I would like to hand the floor over to Professor Mitsumasa Iwamoto.
Thank you for your, introduction. So first I want to share my slide, okay? Can you hear me?
Yes, yes, doctor, we can hear you.
Okay, I want to start my presentations, okay? So today my talk is Maxwell displacement current and optical second Harmonic generation in organic materials and dipole energy as a source of triboelectronic power generator. Because I was working in the field of electron insulation engineering and also organic electronics field for more than 40 years. So in that field, the materials and devices are so important and the characterization techniques are so important. In that sense, in our laboratories, we have developed new techniques, Maxwell displacement current method and also optical second Harmonic generation method. So recently, I used this idea to the triboelectronics. So triboelectronics is now the new emerging technologies, I guess. This is a very clean energy. So okay. So for recently, I wrote a book based on my research histories, okay? Title is same with my presentations. And this topic, in these books, many new technological terms, Maxwell displacement current, thermally simulated current, and optical second Harmonic generation, and so on appears. And you can find the ideas, all of the ideas here. So this will be interesting if you are interested in new triboelectric applications. Okay, so today I want to focus on these stories. First, I briefly introduced TSC, MDC, and also dipolar polarization as an energy source. Okay. And finally, I want to show that how we can distinguish electrostatic charges and also the dipolar energies and so on. And finally, I want to conclude. Okay, then I want to start. What is thermally simulated current? So please look at, so you have better to see. Okay, sorry. So please look at this electrical circuit. This circuit is very simple. Only samples are sandwiched in a closed circuit. So if we hit these samples, we can see that current flows. This current we call the thermally simulated current. So from this trace of the current, we can study what is happening inside of the materials. So the idea is very simple, and it has more than 50 or 60 years ago already, this technique was very popular. And what is happening? So of course, you can expect that the dipolar depolarization and also electron detrapping and ion carrier motion and so on are happening there. But if we, for the case of the dipolar depolarization cases, you can imagine that the first materials are polarized at the P0, and then in final stage, P equals 0. But very important parameter exists. This is a tau. Tau is a relaxation time, and this relaxation time depends on the materials. Please remember relaxation time tau. This parameter is so important for the applications of dipolar triboelectronics by using the dipolar energies. Okay, so in the depolarization processes, in isothermal depolarization processes, this equation describes these situations. every people know that the polarization decays with exponentially decaying these terms. But if we depolarize materials by increasing the temperatures with a heating rate better, in that case, the TSC current appears. This current is a TSCs, and it's a very strange curve appears. One peak appears. So this curve is very special. So if we analyze these curves, we can study the polarizations and also the relaxation times and so on. So we have already know from these curves, we can speculate the total polarization charge and also the residual charge, this hatched part. And also from the peak temperatures, we can estimate the activation energies and also the relaxation time. So by using these techniques, we can study the macroscopic physical parameters of materials and so on. This idea can apply to the organic monolayers. Please look at these situations. So if we spread organic molecules on the water surfaces and by compression, then we can expect the current flows outside. But this case also, we never use batteries, but current flows. This is a Maxwell displacement current, okay? So from these curves, we can study the dipole moment of the materials and so on, okay? I have already done about more than 30 years ago, I have developed these techniques. And this technique can also apply to other systems. If molecule has, for example, the azobenzene dyes, in that case, you know that the cis-trans photoisomerization occurs in molecules. So by UV and visible light irradiations, molecule change the conformations. As a result, we can see the current flows alternatingly positive and negative directions. The charge flowing through the circuit is the same during the UV radiation and visible light irradiations and so on. So this idea, based on these ideas, I applied to the molecular switching devices and so on. Okay, this is the ideas, but it was already more than 30 years ago, this one. But now, very important point is MDC is a short circuit current. So we never use batteries to generate MDCs. But if we focusing on the MDCs, what happens? And looking at the materials, we know that the current flows in the external circuit. This means material system is very similar to the systems that are working by batteries, so such as solar cells and so on. So I reconsider the MDCs, and this is a key point for the application to the tribal electronics. Please look at these situations, okay? In analyzing to analyze the depolarization processes, we assume that the charge induced on the electrode and the polarizations are always same. P equal Q, P equal QE. Q is the induced charge on electrode, and P is the polarization charge. So always this relation is satisfied during the TSC measurement. But if we use the current flowing through the circuit and we input the load resistance here, okay, then you may expect if current flows, potential drop appears. So due to the potential drop, other things may happen. So this is very important because now Q is not equal to P. So focusing on this one, this is very key point. So if we take into account these situations, the depolarization process is described using this equation and these equations. So by solving these equations, we can understand how induced charge Q changes and high depolarization changes with respect to time. So the solution is a little bit difficult, but not so complex. Only two relaxation time appears. But the important one is in an MDC experiment, like a short circuit experiment, okay? That the Q equal R always with time. But if we put the input the load resistance to the external circuit, okay, then Q and R are changes differently. This is a very important findings, okay? So that means that you can understand that if current flows through the load, we expect that the potential drop appears like this one. And also, we can expect that the power is transmitted from the due to the depolarization like this one. So important finding is that the power maximum appears at this conditions. That means if material relaxation time tau equal to CSR. CS is the capacitance of the materials and R is the load resistance. In that case, we can get the peak position here. This relation is very important, okay? So taking these ideas, we now can estimate how about the dipolar energy we can take out. So this is the general values for instance, the permanent dipole, mu equal 1 divide, and n is like this one and like this one. And we can expect that if we polarization energy is around 70 microjoule is coming out. This is the estimations. And if we introduce, if we and if the relaxation time is 1 second, in that case, power is like this one, 8.6 microwatt. And if tau is 10 millisecond, then the power is around 8.6 milliwatt, like this one. So this is very small powers, but very important one is that around, if we can generate around these values, we can use it as a LED energy sources. And also we can, if the power is like this one, then we can operate the quartz oscillators and so on. So by using the frictional force, and we can expect these situations. So we have prepared the polyimide, using the polyimide, and we use the cottons here, and rotating these systems. Now that the friction is happening here. So due to the frictional forces, that the dipoles in materials are polarized and depolarized, oriented, and also depolarized again and again. So as a result, current flows. So you can see that this is a temperature dependence around these temperatures. So that's corresponding to the TSCP position temperatures. So we can expect that a very huge current flows like this one. So, but the frictional force is 2 millinewton meter, so very, very soft, very soft. But we can see current flows. So based on these ideas, we can we store the energies, and then in the stage of the without rubbing cases, LED lamp is off. But if we continuously rubbing, then we can see the light is here. So in this way, we understand that by frictional forces, by cyclic frictional forces, by giving cyclic frictional forces, we can use it. LED is on and off like this one. Okay, so it's very important. So now from these situations, we can this situation is describes using the equivalent circuit. So you can see this is very important. So that this situation is by using the current source. A is the electrode area, and P0 is a polarization terms, and tau is a material relaxation times. Okay, this is a current source, and this is a GI, internal resistances. So this is the equivalent circuit corresponding to these systems. So we understand this system is working by using this circuit. So we put here, and we can take out the power energies. Okay, but perhaps the question comes: general rubbings. Maybe people think that this charging is due to the electrostatic charging is due to the electronic charges, and also the dipolar orientation is not so significant. So maybe that the potential built by rubbing is some of the due to the electric charges and also the dipolar alignment is. But how we can distinguish these two terms? Of course, we can distinguish it, because if we use EFI SHG and SHG techniques, then we can distinguish these situations. Okay, I want to briefly explain this part. Maybe you know the SHG. What is SHG? Because if we incident the laser beam with a wavelength omega, then most of the light is passing through, but 2 omega light is coming out. This is the second harmonics. Okay, so this second harmonics is due to the polarizations here, due to these terms. Okay, P0 is a spontaneous polarizations. This is a linear polarization term, and this term is nonlinear terms. This term is very important, and we know this is a SHG sources, but this is a 3 omega, okay, like this one. But if we focusing on the, people are always focusing on these terms, but if we focusing on more one term, if one term of this term is DC field, then in that situation, this term is the second harmonic generation terms, and this term also the second harmonic generation terms. So if we focus on these two terms, difference of the two terms, we can distinguish electrostatic charges and dipolar orientations. Okay, you can see. So as I told you, when we prove the dipoles due to the dipoles, we focus on these terms. And if we focus on the electrostatic chargings, we focus on these terms, because one term of the electric field is DC field. So, and also chi is depending on the wavelengths of the material. So this is so the peak position is different. So by focusing on the difference of the peak positions, we can distinguish the dipolar contribution and electrostatic charge contributions. This is the images, okay, for the case of the rubbed films. For example, in general, this is the polyimide film. By rubbing, by using the PET films, we did experiment. The blue, this purple color region appears. This is due to the electrostatic chargings, okay, like this one. Green part is no charging, but this part is due to the frictional force. Rubbing appears like this one. But in the same way, we can distinguish positive charges and negative chargings. And by changing the laser wavelengths, we can distinguish the electronic charging and dipolar charging in this way. So in this way, we know that from the PET films, the polyimide films, dipolar polarization appears due to the rubbing. And also, finally, I want to show one experimental result about the PET films by rubbings. This case, we have checked the electrostatic charges. We use EFI SHG methods, so we can understand the decaying processes. So if we can detect the dipolar repolarization process by using these techniques, now we can study about the we can apply it to the drive electronics. So to use this system as dipolar energies, development of the materials is so important on focusing on the dipolar relaxation time of the materials. Okay, so this part is very important. So I want to conclude my talks. So MDC flows short circuit due to the depolarization in materials and external stimulation, heat, pressure, light, and so on. Material systems that generate MDC can serve as dipolar energy source. This is very important. And this system can be modeled using equivalent circuit with a battery source. Battery source means that this is perhaps the current source is much better. And also dipolar energy is generated by loving and available as drive electric power generators, because as I show you that the LED is bricks, okay? And by using the SHG and EFI SHG techniques, we can distinguish the origin of the energy sources by loving. So that's electric charges or dipoles. So I want to conclude my talks. So thank you for your kind attention.
Thank you, Professor Mitsumasa. And if you guys have any questions, I would like you to just use the raise hand button on the WebEx platform.
Okay. Please. It's okay.
If not, then I would, yeah, we have a question here, and Mr. Yoganandan Govindaraj.
You mean?
Sir, good afternoon. I'm Yoganandan. I'm working in Hokkaido University. So this is just a very general question, not related to the exact presentation. Sir, as you know, here in the Sapporo, because of the cold, we use mostly thermal wear or sweater. So because of that, we experience highly the static charging. So we always fear sometime to even touch the metal, or sometime to go to open the door also, because of the release of static charge. How do you give any solution, sir? How to simply overcome this, or do you have any suggestion?
Of course, there are two ways to use such things. One thing is that the electrostatic charge is available as a power source of the drive electric generations. For using the electrostatic charges, we must move motion. Dynamic motion is so important.
Yeah,
But
I
when we
agree.
use dipolar energies, okay, that we don't need to we didn't do the dynamic motions, only that in materials dipole must move. Okay, this part is different. So in Sapporo, the temperature is very low. So perhaps the dipolar motion is perhaps not so smooth. I don't know.
All right, thank you, Professor Mitsumasa. Now I would like to invite our next speaker, which is Dr. Shahid Rasool. Dr. Shahid Rasool is an associate professor in the Faculty of Engineering and Environment at the University of Northumbria in Newcastle. He leads the Material Informatics for Energy Conversion Storage Research Group. And Dr. Shahid Rasool has been developing a new line of world-leading research frontiers investigating wastewater treatment, electrochemical CO2 reduction, photocatalytic water splitting, and solid-state batteries. Dr. Rasool is actively collaborating with several industrial and academic partners worldwide, including Oxford University and University of South Wales. Industrial partners include Tata Steel, Airbus, Shell, UK, and Suez. Dr. Rasool is a member of Multidisciplinary Low Carbon Fuels EPSRC CO2 Chem Network, Supergen Solar, Supergen Bio, and UK Solar Fuel Network. So his talk will be focusing on the recycling of lithium-ion batteries for circular economy.
Thank you very much, Zawar, for such a kind introduction, and good morning to everyone in Qatar and in UK or wherever you are. So I can see that some people are from Japan, so definitely it will be quite late in the afternoon over there. There is, I think, around 8 hours of difference from UK. So thank you so much again for Dr. Shakur and his team. And it is always a pleasure to be part of such kind of live discussions we have. In today's talk, I'm going to talk about recycling the lithium-ion batteries, especially for circular economy models. And I would be bringing this discussion that why this is important to work on the recycling of the batteries. Right. So all over the world, including the developed world and even in developing world, there is a lot of requirements and demand for electric vehicles. And for electric vehicles, the demand for batteries is going many folds every year. So although we see that electrification of the transportation in around the globe, it will bring some of the greenhouse gas emissions to rather lower levels. But at the same time, you know, we are scientists and we need to look at the holistic system that how the electrification of the transportation and also how the battery manufacturing will have its own impact. So the electric vehicle and its batteries will have huge impact in terms of not only the materials, but also from the manufacturing point of view. For lithium-ion batteries, there are three main elements which are used for manufacturing of batteries. One is lithium, the other one most probably it's cobalt, recently has been used as iron, and also graphite for the anode materials. So all of these three materials, they are in huge demand, and also the price and the cost of these materials have been rising quite exponentially. To give you the overview of this, that majority of the lithium, it comes from Argentina and Chile. And for the mining of lithium in these countries, you need lots of water for mining. And we should know that both of these countries, they are arid based countries. What does that mean is that they do need lots of water for their agriculture and some other requirements for all the people over there. So it's a huge requirement from water point of view. Then lithium is also produced by the materials through pyrometallurgy, and mostly the pyrometallurgical processes are done in China and Australia. So when you do the pyrometallurgy, what does that mean is that you need lots of energy, and accordingly there are lots of carbon dioxide emissions for the refining of the metals or lithium extraction. So overall, if you see that you need lots of energy and lots of water, and furthermore, you know, if you are bringing these materials from, for example, in terms of cobalt, 70% of the cobalt is imported from Democratic Republic of Congo. That is 70%, just a small country. So the transportation and other thing. So if you are using lots of energy, if you're using lots of water and you're using energy for the transportation, it does bring lots of impact in terms of environmental impacts, economic, ecological, and social. And ultimately, you know, this is a holistic system which has its overall carbon footprint or greenhouse gases emissions. The battery sector, the battery material sector has been under discussion for a long time due to the ethical issues, ethical mining issues, especially from, let's say, if it comes from Congo or some other countries, where cartelization by the mafias for the mining for these materials has been done, and people are quite underpaid what they work for. So there are ethical issues, and all over the world recently, you know, the supply chain issues for the lithium-ion batteries have become a bigger problem. Why this is so? If you look at the global processing and lithium ion battery market, Asia is dominating battery ecosystems. What does that mean is that about 80% of the world battery cathode manufacturing capacity is in China or around China. 75% of world's cobalt refining capacity is within Asia, in either Japan, Korea, or in China. And about 60% of world's lithium processing capacity is around in this area. What does that mean is that around 90% of the raw material flow is through China. So the Far East part of this globe is dominating the battery market. So what does that mean is that the other countries, including the Western countries out there in UK or even in North America or in Africa or other parts of Asia, they still need lots of capacity in terms of materials, in terms of manufacturing. And you can see that 5% of the world's lithium and 6.5% of the world's cobalt is only recycled or processed in US, Canada, and combined Europe. So you can see that the scale, you know, 90% is being kind of supplied by one part of the world, other 5%, 5 to 10%, where mostly it is used, it come from the Far East towards West. So what does that mean for the UK? So since I have been working on lithium and battery recycling for some time now, and majority of the perspective from today's talk will be around UK. In UK, we need by 2040 about 200 gigawatt hour of cell pack manufacturing production capacity in. And what we think is that there will be around 450,000 tons of batteries, which will come to their end of life in next 20 years or so. In UK, we do not have much battery processing or battery manufacturing, I told you earlier. And still, you know, even though we are moving towards battery manufacturing, however, our dependency on foreign countries will lead to insecurity of supply chain and for future production. So there are some potential rules. For example, you know, if 80% of our batteries, they go for the landfill after the end of their life, and then it means that, you know, about 20,000 ton of household batteries every year being dumped into the landfill. What does that mean is that we don't have much bigger manufacturing capacity. We don't have many material resources. What if, and we are dumping lots of batteries in the landfills, which has its own environmental impacts. It is a no-brainer that the UK and around the countries around UK, they need the recycling of lithium-ion batteries industry as soon as possible. So these are some of the potential routes we need to work on. So what is happening on the on the battery manufacturing side? For example, I am at Northumbria University, which is based in Newcastle, around this part of the country. We have Nissan, which is Envision AEC, another name for Nissan. They have a capacity of about 2 gigawatt hour from 2012. Now, Britishvolt, that is another big manufacturing battery manufacturing company, again in the northeast over this part of the country. They have plans to develop 20 to 30 gigawatt hour of batteries in next 2 to 3 years of time. And also Nissan or Envision, they are going to expand from 11 gigawatt hour to 25 gigawatt hour in next couple of years. So the battery manufacturing is on rise around Northeast, and especially in terms of its gigafactories. However, the material supply is a big problem. Either it is lithium, nickel, cobalt, or manganese on cathode materials, or even graphite on the anode materials. So we need lots of lithium resources, cobalt resources, so that we can recycle that. So this is a complete cycle. For the circular economy model, what we are trying to pursue, the policymakers, all the stakeholders, that you should go for this one. For example, if you have end-of-life batteries, you do the battery recycling and processing and produce black mass. When we say black mass, what does that mean is that you have all of these metals. And also if you can reclaim graphite. So then key metals extraction is done and reuse and new battery production. There is another way where we can work on. For example, there are some of the batteries which come to end of life, but there are some batteries that which are not really useful for the electric vehicles, so they can have their own secondary applications in terms of stationary charge store application. So this is the recovery of the black mass from the end of life batteries. Why it is beneficial? You can ease the supply chain pressure. It will be a circular economy because, end of life batteries, they are given a new life. The materials are given new life to be used again and again. And also there will be lots of reduction in carbon dioxide emissions. The trade export purposes will be sorted. You can even increase the battery production capacities, and obviously if you do recycle and if you own your own materials, transportation costs and some other costs could be avoided, and those will be affordable batteries, right? So what is the project demand from battery recycling point of view? For example, as I said that by 2040 you will need about 200 gigawatt hour of batteries. And if you look at the prices of nickel, the price of nickel, for example, in last 1 year, it has increased 7 times, and it is roughly now 19,000 pounds per ton. In terms of cobalt, it's about 45,000 pounds per ton, and lithium is around 64,000 pounds per ton. So what does that mean is that some people are calling these metals as kind of green gold, that these prices are going to rise again and again, and also the prices for the transportation or the energy costs are going to rise. So there is a clear business proposition for the UK to go for the recycling. So how the recycling processes are done? So first of all, you get the retired EV batteries or end-of-life batteries. Most of the times, these batteries are recycled in China. This is very surprising, to know that in terms of recycling of lithium-ion batteries, even not only the manufacturing, but also recycling of battery capacity is mainly available in China. So and some European countries like Belgium, they have some recycling capacities. What happens from the UK, all the retired batteries are sent over to either Europe or China, and then the retired EV batteries, they will be disassembled after discharging and bringing them to a safe position, and then they will be shredded. All the battery materials, either and all the different types of batteries, whether it is cylindrical type, whether it is pouch type or prismatic or different chemistries, what they will do is they will shred those batteries, all of them together, including the anode, including the cathode, including the electrolyte. Everything will be shredded, and then there will be two processes used, either hydrometallurgical route or pyrometallurgical route. In both of the cases, hydrometallurgy or pyrometallurgy, lots of energy is required and lots of water and other resources are required, and ultimately these processes become quite energy intensive and lots of carbon dioxide emissions happen. And the recovered material, they are not of really good quality, and then again, even though you get the recovered materials, still they are supplied and used for the manufacturing. Right. So we have done some techno-economic analysis for UK, that what if we have different types of chemistries, LMO, LFP, NMC, NMC 622 or NCA. We have done the scenarios for United Kingdom, and we have tried to do that. What if use hydrometallurgical recycling, pyrometallurgical recycling, or direct recycling? Direct recycling, here we mean that you separate the electrodes and then try to recycle the black mass out of that. In pyro and hydrometallurgy, you shred the batteries, everything comes together, and then you try high energy intensive processes. So we compared the direct recycling of lithium-ion batteries with hydrometallurgical and pyrometallurgical recycling techniques. So what we have seen is that if you do the techno-economic analysis, there are mainly chances that if you go for the direct recycling, there is net profit you can make after recycling. However, if you go for the hydrometallurgical or pyrometallurgical, and especially if you include the rising energy prices within the UK and Europe and other parts of, even this will become even more difficult for pyrometallurgy and hydrometallurgical routes. So what we see is that direct recycling of batteries without shredding, you separate everything altogether, either manually or automated processes. There is a huge profitability chance from battery recycling point of view. So what we have been proposing recently at Northumbria University, my research group, that what if we get retied batteries, either from Nissan in pouch cells or cylindrical, we disassemble it and we do the cathode and anode separation, and we do the air blading technology, which we have developed at Northumbria University, that you get the black mass from the anode and cathode separately, and then try to use and extract the metals from there for further use. And obviously, for remanufacturing from this technology will provide low cost and also lower CO2 emissions for battery recycling. Right. So what is our technology? Basically, what we do is that we disassemble the battery packs. We get the metal foil, either it is anode or cathode. Anode will be graphite coated on copper, and cathode will be lithium cobalt oxide or LFP or NMC on aluminum. So you do the separation after after getting the stack into anode and cathode, and then we have designed a process that is called A-blade technology, which separates the black mass from the sheets. And this is a direct approach, and it runs on ambient temperature, and it has minimal impact on the powder material or the material itself, because of the separation of and direct recycling of the batteries. Right. So this is a kind of Nissan battery pack disassembly. So here you see that Cowlis or lithium recycling solution. There is a local company where we are working with. So my team members, they are working with them, and this is the Nissan battery. This is the battery pack, and then different battery modules. You discharge it, and then this is one module, and then the electrodes are separate like this. This is the normal Teslas or other electric vehicle car batteries, which, for example, they are using 18650 or 21740 batteries. So you can disassemble the batteries, and you can remove the black mass. This is the anode material, which has graphite on copper, and this is the cathode material, that mostly this is LFP on aluminium metal. Right. So we are working in northeast of England, that is becoming hub of lithium-ion battery manufacturing in terms of Britishvolt or Nissan. So we think that we need to work together for providing a long-term commitment of our research, and this is a kind of new area of work for us and also for the UK's market. So we are looking for some kind of collaborations around the world so that we can work with people. So what our focus right now is that we develop relationships in automotive, energy storage, and industrial sectors with lithium-ion use expanding. And this is not limited to UK. For example, Nissan, it is a Japanese company, and majority of the designs, majority of the materials, majority of the research is done in Japan. So we would be very interested to work with other people, either it is in Nissan or Britishvolt or EMR. This is European Metal Recycling Company. And this is a huge company which mainly working on the metal recycling, and they do the mining, and then they do the refining as well. So we're working towards creating partnerships so that the lithium-ion battery recycling projects and this scenario becomes more available and accessible to all. And also we are working Johnson Matthey. Johnson Matthey is a big material manufacturing or material synthesis company within UK, which work on precious materials like platinum or some palladium or some other materials. Right. So this is the scenario where different people are working around the UK and around the globe. For example, Nissan, this is working within UK, Glencore, EMR, Lithium Cycle. This is an American company or North American company. Fortrum, they are working on recycling a lithium battery. This is one of the company where we are collaborating with them. Veolia, that is a French company. They have started working on electric battery recycling. And then there is Duesenfeld battery recycling, that is in Germany. So this is a European or more North American concept where different people are working. So on this particular project, there are 3 researchers in my lab are working, and Venki, who is senior research assistant, and Rana Faisal Shahzad and Muhammad Usman Bhatt. So basically, this is the team who are working on lithium-ion battery recycling solutions. And this project and this research is mainly funded by the Northern Accelerator, UKRI, or Lithium and Battery Manufacturing, NWMG Group. So this is all about our work on lithium-ion battery recycling. These are some of the reference, and thank you so much for listening. I hope that I convince you that we need to move forward for the lithium-ion battery recycling. Thank you.
Thank you, Professor Shahid. And if anyone has a question, please Please oblige. So I think, sure, go on.
Yes. So if no questions, so that's okay. And I'm very interested that if we have people from around the globe here, and I would be very interested that if we could bring some collaborations together, especially on this topic, because I see that there are large research gaps for the recycling of lithium-ion batteries, and if we could bring some partnerships around that, it would be great.
All right, thank you, Dr. Syed.
I have a question. So, with your, thank you very much, first of all. It's a nice lecture. From your research developments, so how these companies did these companies started to create their lithium batteries with holistic view, starting from the design and thinking about the recycling. Do you work with these companies and propose a solution that is already applied?
Yes, so thanks so much. That is very interesting question. Yes, I'm working with these companies, and there are two interfaces we are working with them. One, we are trying to push that instead of pyrometallurgical and hydrometallurgical route, you need to go for the direct recycling. Okay, so one thing we are doing that. The other thing which you brought, and that is very important, that is the design. So right now, all of the battery packs or all the battery manufacturing, they do not design the batteries and battery packs for recycling. So recycling is not really in the mind when they are designing those batteries. What we are trying to push through from Northumbria University is that you need to design the battery packs, modules, and also the cells in such a way that they should be easy to disintegrate, they should be easy to separate, and then could be recycled. So British Volt is just next to us, and I'm working with them. And as I said, that lithium recycling solutions, WMG, that is Warwick Manufacturing Group, and other partner where I'm working with. So two things: direct recycling. The first thing is, to convince them this is very important. You need to recycle. Otherwise, it is not sustainable. Other thing is, second thing is the direct recycling, and third thing is that we need to design the batteries from such a point of view that we are going to recycle.
Excuse me, you are teaching or you do research only?
Yeah, so I am teaching and I'm doing
okay,
research.
So it's a question also of chemical and chemical engineering education. Yeah. So is this in any course about these ideas? Is it implemented at the university? Do you teach how to think design of materials and their recycling? This is an important question because we teach the fundamentals of physics, maths, chemistry, but never to create something, but never to handle it when it is at the end of life. So this is perhaps an important question. And
this is very, very important point. And Professor, this is becoming more and more relevant. So we have a Faraday Institute, Faraday institution that is a UK government's funded institution. It is kind of digital or not it doesn't have a physical building, but it is a kind of distributed and digital institution. So they have introduced these kind of concepts. And for example, from recycling point of view, I'm going to be deliver some of the lectures on recycling of the batteries through the Faraday institution. So this is becoming more and more kind of relevant, and probably we need to bring more into curriculum. But as of now, there is not much curriculum available all over the world, not only in UK. Even if you look in top US universities, still it is not part of the curriculum, and we need to stress on that. Your point is very much valid. Yeah,
it must be triggered somehow.
It should.
Thank you very much.
Thank you so much.
Thank you.
All right, thank you, professors. And I would like to move on and invite our next speaker, Professor Mohammad Khaja Naziruddin. He is a professor of chemistry at the Federal Institute of Technology in Lausanne, in Switzerland. His current research at the Federal Institute focuses on perovskite solar cells and light-emitting diodes. He is the inventor, co-inventor of over 90 patents and has been consistently been ranked amongst Thomson Reuters highly cited researchers and listed among the top 10 researchers in the perovskite solar cell research field. He's directing and managing several industrial, national, and European Union projects. He has been appointed as a world-class university professor by Korea University and an adjunct professor by King Abdulaziz University in Jeddah. He has been elected to the European Academy of Sciences. He is also a fellow of the Royal Society of Chemistry and a fellow of the Telangana Academy of Sciences. He has won the 34th Khwarizmi International Award and is a laureate in fundamental sciences. So I would like to hand over the floor to Professor Khaja now.
Thank you for your kind introduction. And I would like to take this opportunity to thank the organizers for inviting me to share our recent developments on perovskite solar cells. The previous talk is very pertinent for this solar cells where we need storage of the batteries. So the title of my talk is Development of Efficient and Stable Perovskite Solar Cells and Modules. You will see what is perovskite and how we are modifying and how we are getting high efficiencies. So I'm working at EPFL, Switzerland. So my name is Naziruddin. My EPFL address is given here, the email address. You can contact me if you have any questions. This is our campus. I just briefly mentioned this is a very nice campus. It's located on the site of Lake Leman. So this is our library, and this is our Congress Center. It's a very beautiful Congress Center. And just want to show you the beauty of our campus. Now I come to my topic, the perovskite solar cells. What you see on the left side is a silicon solar cells, which everybody is using, which is widely the total market of this solar cells is over 96% of solar cells. What we use is based on the silicon. It has a high efficiency and very stable performance, but however, it's a energy intensive and technologically very intensive topic. On the contrary, what we are working is on the right side, it's a perovskite solar cells. It's a solution process, and the deposition of these materials are below 150 degrees temperature, in contrast to the silicon solar cells, which requires 1400 degrees temperature. So in this material, what we are doing is modifying these 3D materials or three-dimensional perovskites and the low-dimensional perovskite. I will give you the more details as we go on. So these materials are encapsulated between the hole transporting material and electron transport material. Now, depending on the absorption properties of these materials, it can be used as a solar cell applications, or it can be used for the light emitting applications. So by changing the cations and anions, you will see in the next slide what I mean by cations and anions, you can modify these materials for either applications. So what is perovskite actually? The perovskite is a typical formula of perovskite can be given ABX3. A is a type of cations, which can be inorganic cations similar to cesium, or organic cations like methylammonium or formidinium. B is a metal cation that can be lead 2+ and tin 2+, and the X is a halide. It can be bromide, chloride, and iodide. The next slide, you will see the properties of this different combination of the cations and the halides and the metal cations. But in my study, I will focus only lead as a cation, metal cation, and formidinium as an organic cation, iodide as a X. So these materials, when you mix together, that's a lead iodide and methylammonium organic cation iodide, they form a three-dimensional perovskite as shown on the left side. You can see by my cursor is moving. This is called three-dimensional perovskite structure where iodide is connected through all the lead atoms. So this material has a very interesting property which are highlighted on the bottom. Very strong light absorption in the visible region. That means it absorbs all the visible light from between 400 to 820 nanometers. The tunable band gap. This tunable band gap is the one which I will show you the next coming slides, where you can change the absorption properties either by changing the organic cations or by changing the halides or by changing the metal cation. Small excitation dissociation energy. These materials, when you shine the light, it creates the charges, positive and negative. These charges are already dissociated. They are not bound together. That's called a very small excitation dissociation energy. As I mentioned before, the properties of this material, they absorb all the light in the visible region below 800 nanometers. And they have another interesting property which is shown on the right side of the panel, where if you look at the comparison of the three main material absorber materials, gallium arsenide, that's a blue light, and the silicon solar cells, that's a dashed line purple. The perovskite is this red line. So the sharp onset of these materials gives you the opportunity to combine with the silicon solar cells to give you a tandem solar cells with the efficiencies reaching over 30%. So this I'm not going to cover the tandem solar cells. So in this topic, in this presentation, I will cover only the perovskite solar cells. As I mentioned before, the band gap tunability is highlighted here. So if you look at the methylammonium lead iodide perovskite, this has a band gap between 1.7 to 3. And if we change the metal lead to tin, you can see how you can shift the band gap of these materials to lower energy. By having the mixed halides like a bromide and iodide mixed together, and then the mixed cations, you can further fine tune depending on our requirements. The one important material which you will be seeing in my presentation is formidinium lead iodide. So this material has a very low band gap. Its onset is around 1.5. It absorbs all the visible light and it gives a very high efficiency, and certified power conversion efficiency of these materials is over 25%. You will see the data. If you replace tin by lead, and it gives you a very low the energy absorption, that's so you can use this type of lead and tin even for tandem configurations. Similarly, if you replace organic cation, that's a methylammonium or formidinium, to inorganic cation, cesium, you can increase the band gap significantly. So the difference between these cations is that the inorganic cation is extremely stable compared to the organic cations. But however, there are problems with the inorganic cation. It has two different phases, alpha and delta. So in order to stabilize the alpha phase, you have to do several modifications, additives, and this can be a very interesting topic for students who are interested to do their research on this topic. So these are the tunable materials which I mentioned in my initial slide. Similarly, I'm just showing the spectral properties as I mentioned before. So just changing the cesium cation, cesium has a large band gap, to methylammonium goes to slightly redshifted, and formidinium more redshifted. So these are the cations modifications which gives you the band gap tuning from 1.48 to 1.73. Similarly, halide tuning, which I mentioned before, but here I'm showing the spectral properties. You can see the shift of going from iodide to the bromide. In between, you can have a different absorption properties. Again, within the organic cation, it's shown here. Extreme left, you have a pure methylammonium iodide, which gives absorption maximum around 770 nanometers. On the extreme right, we have a formidinium, which gives around 810 nanometers absorption maximum. So these are the, within the cations, you can see the tunability of these materials. So now after going through these materials, so what are these materials useful? So you can use these materials for solar cell applications. In solar cells, there are two main configurations. One is described here, it's called PIN, and the second one is called NIP. So the materials are the same, absorption materials are the same, except in PIN configuration, the light is passing through a selective hole transporting layer in the PIN configuration. If you look at the NIP configuration, the light is passing through the ETL layer. So this is a transparent conducting oxide. So this is the light passing window. So these two configurations, so the one condition is in PIN configuration, hole transporting layer, HTL, should be transparent. In NIP configuration, ETL layer, electron transporting layer, should be transparent. So these are the two configurations dominated in the perovskite solar cell community. The NIP is the highest efficiency, certified 25.7% certified at Newport. And the PIN is quite useful for the tandem configurations, which I'm not going to discuss in this talk. Now, if you look at these perovskites, so the energy level scheme is shown on the right side, C. So this is the absorbing material, perovskite. On the left side, you have an electron transport layer. On the right side, you have a hole transport material. When the light is shined on these materials, you create charges, positive and negative. So these charges are extracted selectively into, for example, take the positive charges. They are extracted selectively into the hole transporting layer. And similarly, electrons are extracted into the ETL layer. Now, if you look at the beauty of this design of these charge transport layers, the hole transporting materials can be gone here. But if you look at the hole transport, the positive charges in the ETL side, this ETL layer blocks to the holes. Similarly, electrons are blocked by the hole transporting materials. So this way you channel these carriers in two directions, and these carriers are extracted on the contacts. So on the below, you see the typical cross-sectional image of solar cell. So it's the deposition techniques. We have several layers. One is called compact TiO2, titanium dioxide layer. Then followed by, we have a mesoporous TiO2 and tin oxide layer, which is shown here. Then we deposit perovskite composition by depending on the different cations and anions. Perovskite composition with its 600 nanometers thickness. We have a hole transporting material, spirometad, and gold as a contact. Using this configuration, we reach 24.3% efficiency, and which is certified at Newport 24.77. This is the efficiency which we certified at Newport. Similarly, we made a small modules with 7 by 7, 6.5 by 7 centimeters, and the efficiency of these mini modules is 22.9. So now if you look at the beauty of this one, this is a very small cell, 0.16 centimeters square, 24% efficiency. Going to 45 square centimeters, we reduce the gap between the small cell to a large mini module very significantly. Similarly, we can also use, instead of glass substrate, we can also use a flexible substrate. Okay, now I come to the outline of my talk. These perovskite materials are very nice. You have seen very high efficiencies, but we have difficulties with this perovskite stability. So how can we improve the stability of these materials? By interface engineering. You will see a couple of slides on the interface engineering and the compositional engineering of perovskite layers. All these efforts are to increase the stability of the perovskite materials. Now, development of charge transport material, you have seen I highlighted the charge transport materials. So we want to improve the properties of the charge transport materials to improve the performance and the stability of these materials. And finally, I will give you the cost analysis. If we install 100 megawatts of the perovskite production line, how much it costs. Now, so in this slide, what I'm showing is on the right side, you see the absorption properties of the three-dimensional perovskite. I mentioned in the beginning, the three-dimensional perovskite, it absorbs all the visible light. On the contrary, there is another class of material. It's called the two-dimensional perovskite. It absorbs only below 550 nanometers, very small portion of the visible light it absorbs. Now, how do we get this two-dimensional and three-dimensional perovskite? And this is the three-dimensional. Come back to the left side. This is the three-dimensional perovskite. When we form this three-dimensional perovskite, there is a cavity which forms, and this cavity takes the cation. And the cation size is very much dictates the dimensionality of this perovskite. If the cation size fits into the cavity, it forms a three-dimensional perovskite. However, if the cation is larger than this cavity, then we slice these materials into different load dimensions. It can be n equals to 1, or it can, so now n equals to 2, n equals to 3. Now you have an opportunity to tune these materials even in the dimensionality. So this way, the cations I have highlighted here, I'm not going to discuss all of these cations. I take one example, phenylethylamine or fluorophenylethylamine, you will see in my presentation. But now highlight the properties. So this three-dimensional perovskite absorbs all the visible light, very useful for the solar cell applications, but the stability is poor or less. On the contrary, two-dimensional perovskite, it absorbs very small portion of the visible light, but extremely stable performance. So what you will see in my presentation is combining this three-dimensional perovskite into two-dimensional perovskite, making it more stable and high performance. Now we have to characterize these materials. So here are the XRD data and visible absorption spectrum shown here on the right side. So take the reference sample, three-dimensional perovskite. It has a typical peak in the XRD 2 theta, that's around 14. Now the two-dimensional perovskite characteristic is 2 theta is around 5. That's on the top. Now by combining the 3D and 2D, you can see the characteristic peak of the two-dimensional perovskite and similarly characteristic peak of three-dimensional perovskite. If you look at the absorption spectral properties as shown before, the two-dimensional perovskite absorbs below 550 nanometers. On the contrary, three-dimensional perovskite, that's a black line, absorbs all the visible spectrum. By combining the 2D and the 3D, you can see the red the line, which in the onset it doesn't change, but in the visible region, that between 400 to 550, you can see slight enhancement in the absorption properties. Now you can also monitor characterized by exciting this material from the two sides, from the top side and the bottom side. Now if you look at the black line, that's we are discussing two types of material. One is that's a cesium, formidinium, methylammonium, lead iodide bromide. So this is a mixed halide, mixed cation perovskite without any two-dimensional perovskite. If you excite from the top side and you see only one emission peak, the black line here coming around 760 nanometers. Now we deposit layered perovskite, that is two-dimensional perovskite, on the top of three-dimensional perovskite containing cesium, formidinium, methylammonium, lead iodide bromide. It gives you a new peak which is around 520, as I mentioned before. Similarly, it has a small peak because the excitation light penetrates through the two-dimensional perovskite into the three-dimensional perovskite. Now what happens if these two cells excited from the bottom side? They are overlapping, clearly showing that this two-dimensional perovskite is localized on the top. So this is clearly the layer by layer deposition of these materials. Now if you look at the UPS data on the left side, and now we build the energy scheme here. This is a perovskite absorption material, and the two-dimensional perovskite, the HOMO level of the two-dimensional perovskite is consistent or well aligned with the three-dimensional perovskite. But the LUMO level is significantly higher, so that if the charges are created here, positive and negative charges, the positive charges are extracted without any barrier into the whole transport material. On the contrary, electrons which are generated in the perovskite, they try to come to this place interface, and they will not recombine, but they are driven towards the ETL layer. So this way we have increased the electron positive charge separation, reduces the recombination significantly on this interface. How do we know that one? If you measure without this two-dimensional perovskite, the VOC of this cell is 1.09, and by incorporating this two-dimensional perovskite, you increase 1.14. The power conversion efficiency increased from 18.6 to 20.08, and the champion cell is around 20.75. Now that's a efficiency increment, but look at the beauty of the stability. So here we are showing two types of cells. One, the black ones are without two-dimensional perovskite. The red lines are with the two-dimensional perovskites. Now within the red lines, you have two types of graphs. One is a blank and another is a filled one. The blank one is stability data measured up to 800 hours under argon atmosphere, and the filled ones are the perovskite solar cell encapsulated and then measured under ambient conditions with the two-dimensional perovskite, the stability data is almost overlapping. On the contrary, without two-dimensional perovskite, under argon atmosphere, it's decreasing significantly, and outside with encapsulation also decreasing more significantly. So the take-home message is these two-dimensional perovskites are protecting your three-dimensional perovskites significantly, giving enhanced stability, at the same time enhancing the power conversion efficiency. Now, can we change this? This is a methylammonium iodide as a two-dimensional perovskite. Can we further modify this cation? So I have taken two examples here. One is a fluorine substituted phenylethylamine, and another one is a pentafluorobenzylamine. Why did we select fluorinated cations? The fluorinated cations are hydrophobic. Perovskites are hydrophilic material. So we want to increase the hydrophobicity so that we can enhance the stability by avoiding the humidity coming from the atmosphere. So these are the two cations we have selected. So we made the two-dimensional perovskite independently, and the green line is a fluorophenylethylamine cation containing two-dimensional perovskite. The purple one is pentafluorobenzylamine cation two-dimensional perovskite. Similarly, we deposited on top of three-dimensional perovskite. So this is a black one is a three-dimensional perovskite, and the blue one is with the fluorophenylethylamine, and the red one is pentafluorobenzylamine cation. Now, if you look at the efficiency, this is a blank where we have a open potential 1.09, and the efficiency is 20% efficiency. Now, if we replace this cation, fluorophenylethylamine, the efficiency increased to 21%, and the VOC went from 1.09 to 1.13. Now, if you look at the pentafluorobenzylamine, and the efficiency, the VOC increased from 1.09 to 1.15, and the power conversion efficiency increased from 20 to 21.65. And similarly, the stability data is shown here. So the stability of the pentafluorobenzylamine is significantly enhanced compared to fluorobenzylamine and the pristine 3D perovskite. And similarly, we have taken another class of cations is shown here. And these cations, some of the cations, they form two-dimensional perovskite, some will not. So is shown on the B. And particularly the para ones forms a two-dimensional perovskite. Para ones is shown on the figure A. This is the para diethylammonium benzyl cation. It forms a two-dimensional perovskite. The remaining ones, they don't form. However, the ortho one gives highest efficiency, is shown here, 22.45, and the best efficiency is close to 24% efficiency. And this is not forming a two-dimensional perovskite, but it's passivating the perovskite surface, three-dimensional perovskite surface, by binding to the perovskite surface. So not having a two-dimensional perovskite is not a disadvantage, but you can also passivate this type of cations, which forms a very nice interface layer between the 3D and whole transporting material. So the data is shown here. These are typical IV curves, forward and reverse scanning. Power conversion efficiencies are close to 24%. Now I come to the compositional engineering of perovskite layer. That's a interface engineering where we are putting this two-dimensional perovskite between the perovskite and whole transport material. So the composition, as I mentioned, A is a methylammonium many groups are using, and formidinium also is being used, or combination of these two. The guanidinium is another cation. So if you look at these three cations, has a 1 amino group, 2 amino groups, and 3 amino groups. So the purpose here we have selected is maybe having extra amino groups can interact with iodides, so therefore you induce the hydrogen bonding and then stability. However, if you look at the size of the this is called so-called Goldsmith tolerance factor. If the size of the cation falls between 0.8 to 1, it forms a cubic three-dimensional perovskite. If the size is too large, then it doesn't form three-dimensional perovskite, and too small also doesn't form. And the guanidinium is slightly larger, and it comes on the borderline. But however, it's very difficult to form a pure three-dimensional perovskite using guanidinium. Can we combine a small amount of guanidinium? It can be 25% and 75% methylammonium. So by combining the larger cation and the smaller cation, So you can see in a unit cell, you can accommodate up to 25% of guanidinium. The efficiencies at that time was around 20%. It's not very high, but it's significant at that time. And now if you look at the stability, having 25% of guanidinium incorporated into methylammonium cation, so the stability is increased significantly up to 1,100 hours compared to the blank, which is a black line. And now if you have a different ratios, 12 and 14 is shown in this graph. The configuration is the same as before I mentioned, NIP, where ETL layer, perovskite, and whole transport material. Now I come to the composition where we want to add the additives. Why we want to add additives? So one of the instability of the perovskite is mostly coming from the ion migration. Can we stop this ion migration by bringing different ions into the perovskite composition? That was the logic why we want to incorporate ionic liquids into the perovskite. And now, since we are incorporating these ionic liquids, can we functionalize? And the functional groups here, we have taken a perfluorinated alkyl group. So the purpose again here is to create the hydrophobicity and create more ions so that you can reduce the ion migration. So if you look at the XRD data, which is very indicative, the reference sample, and particularly this peak, which is, well, let's check this one, E figure, and this peak at 12.6 is a characteristic peak of perovskite decomposition and forming the lead iodide. Now, if you look at the this peak, the blank is have a significant lead iodide. That's due to the decomposition of the perovskite. Now, if we use 1% of this ionic liquid under same conditions, the decrease has the formation of lead iodides decreases significantly. Now, if you use 2% of this ionic liquid into the perovskite composition, the decomposition of the perovskite and formation of lead iodide is significantly decreased. That's a green line. Now, if we use a 4% of this ionic liquid into the perovskite composition, so there is no formation of lead iodide, showing that these ionic liquids are preventing the degradation of the perovskite. Now, this is a demonstration. This is a reference sample, solar cell on the back side, on the front side without any ionic liquid. We use 1% of this ionic liquid, which I showed before, on the solar cell from the front side and back side. You see the difference is significant. That means 1% of this ionic liquid is 2 months at 50% humidity, protecting the perovskite methylammonium lead iodide. Now, what is happening actually? Is this ionic liquid, where is this actually located? So then we did the focused ion beam measurements, taking one grain, digging from the top to bottom. Now, if you look at this is a guide for the presence of fluorine binding energy, which is around 689. This is fluorine binding energy as a reference. Now, if you look at our perovskite grain, and we dig from the top to bottom, and 0 nanometers, we see the peak presence at 688 due to the fluorine binding energy, and up to 25 nanometers, the peak is, this is a blue, so presence of fluorine binding energy is there, and below 50 nanometers, there is nothing, showing that this fluorinated ionic liquid is somehow forming a shell on top of perovskite grains and protecting the perovskite from further decomposition. The efficiencies are shown here, which is reasonable, around 19-20%. And this is not very important. What is important take-home message here is creation of a hydrophobic shell on top of perovskite grains to enhance the stability. So this is the stability data, and the same XRD data is shown here with the 60 degrees temperature heating, the formation of lead iodide without ionic liquid, and with ionic liquid, suppression of this formation of lead iodide. I take one more example. This time I'm taking ionic liquid with the functional groups for polymerizable ionic groups. So these ionic liquids you can put into the solution and then heat it at 80 degrees, they polymerize, self-polymerize. So perovskite solar cells, when we manufacture, we do in a glow box under controlled conditions. For industrial applications, maybe it's wise to go for the outside application. So here, so far what we have seen, the data is based on perovskite solar cells manufactured in a glow box conditions, under controlled conditions. This data which I am showing is perovskite solar cells manufactured under normal conditions in a laboratory conditions outside and the efficiency is 15%. That's the efficiency which you get. It's because of the presence of oxygen, humidity that decreases the power conversion efficiency. By using this polymerizable ionic liquid and using a standard methylammonium lead iodide as a reference sample, power conversion efficiency increased from 15 to 17%. By changing the cation from methylammonium to formidinium, the reference sample without ionic liquid is 17%, and with ionic liquid, the power conversion efficiency increased to 19%. All this data is the solar cells are fabricated outside atmosphere conditions. Now, if you look at the stability of the similar ionic liquids, on the left side, which I'm showing you is a polymerizable ionic liquid, which I have shown you the data, and a similar ionic liquid without any double bond. Just to focus on this double bonds, here we have a double bond, here there is no double bond, so it will not form a polymerizable group, polymerizable ionic liquid. Now, having this double bond which polymerizes gives you extremely stable performance up to 2000 hours, and the decrease in power conversion efficiency is less than 10%. Using similar ionic liquid which doesn't have the double bonds to polymerize decreases the power conversion efficiency to 40% of its initial efficiency. That's the beauty of this type of ionic liquids, the polymerizable functional groups. So I take the last example on the additives. So lead iodide is a metal which can coordinate with the donor groups, and here is the donor group, the cyanide, and with the different alkyl chains and two types of donors, one side cyanide groups and two cyanide groups. In these configurations, we want to identify which one is the best. And if you look at the C3, this molecule with the one cyanide group with the three carbon atoms in between, this gives very highest power conversion efficiency and extremely stable performance. Why this is happening? When we mix lead iodide and methylammonium iodide, this ionic liquid, the cyanide groups is a coordinating functional group. It coordinates, binds to the lead iodide, and the perovskite crystallization is slightly reduced, and this way you form a compact perovskite composition that gives enhanced power conversion efficiency and stability reduced because of the reduced defects. So this work is published 2 months back, and you can have a reference here. Now I come to the charge transport materials. So these are the electron transport material and the hole transport materials. So if you look at the charge transport material, titanium dioxide, tin oxide, zinc oxide, these are the three inorganic oxide materials widely used as electron transport materials. And if we look at our solar cell efficiency, the TiO2 having as electron transport layer, the power conversion efficiency is decreasing upon shining the light up to 1000 hours. And if you take the pure tin oxide as electron transport layer, that's a red dots which are overlapped with the blue dots, but just focus on the red dots. So the difference between the tin oxide and titanium dioxide is highlighted here. Tin oxide shows a very stable performance compared to TiO2, which is decreasing the power conversion efficiency. Now, if I take the blue lines, which is a combination of TiO2 and tin oxide. So both are overlapping similar to the TiO2, similar to tin oxide layer, showing the take-home message from these studies is TiO2 as electron transport layer is not doing very good performance and stability point of view. It's because when we did the analysis, the delamination of the perovskite and the ETL layer is happening in presence of TiO2 as the electron transport layer. If we deposit a thin layer of tin oxide on top of TiO2, this layer the interface is stabilized and the corresponding power conversion efficiency remains intact up to 1000 hours. So the beauty here is either we deposit only tin oxide as electron transport layer or TiO2 but passivate with the tin oxide layer. This is regarding the charge transport layer, electron transport material. Very recently, we also developed nanoparticles. That's single crystalline TiO2 compared to nanoparticles. These studies are based on the nanoparticles, and now we developed a single crystalline TiO2 material. So the difference in the energy levels is shown in the figure A. Very small difference in the conduction band, but the HOMO level is the same. The perovskite is the energetic scheme is shown here, and the spirometallurgy as a whole transport material. So what is the difference between single crystalline TiO2 nanoparticles and the nanoparticles? And if you look at the data as shown in the B, nanoparticles has a fill factor of 81. The VOC is 1.1. And if you take the single crystalline TiO2 particles, and the VOC is 1.21, and the fill factor is 84. So this is the one parameter which I'm highlighting, because the power conversion efficiency is a product of open cycle potential, fill factor, and current. So remaining parameters I'm not focusing because they are almost similar, but I'm focusing only on the fill factor. Why we have changed the fill factor significantly? It's because when we measure the microwave conductivity of these materials, electron transport material, so the conductivity of the electron transport layer increased significantly when we change from nanoparticle to single crystalline TiO2 material. So this gives you enhanced fill factor, and therefore the power conversion efficiency increased significantly from 22.72 to 24% efficiency on a smaller cell. Now we made a mini module shown before as well, and with this module, so if you look at the VOC, we have 9 cells here, 9 cells interconnected with laser scribings of P1, P2, P3. You will see in the next slide more details, and we can get 10 volts of this small cell, and then the power conversion efficiency is 22.87. So this work, you can find more details in Nature Nanotechnology 2022. The reference is given below. People who are interested on the scribings, so the details of how we interconnect this perovskite solar cell with the different laser scribings. So you can see first we do the TCO coating, then P1 scribing, that's separating the cells. Then we deposit ATL layer, followed by the perovskite deposition, whole transport material. Then we scribe P2, and we eliminate, we remove all this P2 scribing using these materials. Then we deposit gold as a contact, and then we scribe the P3 so that all these interconnects are working. As shown here, you see 9 cells giving 10 volts shows with high fill factor. So the interconnects are working just perfect. Now I move towards the whole transport material. So whole transport material is, so for all the literature, the high efficiency solar cells are using spirometallurgy as a whole transport material, which is shown on the right top side. Now, this whole transport material has a low mobility. So you have to increase the mobility in order to extract the positive charges from the perovskite and from positive charges coming to the whole transport material to the contact gold. So in order to increase the mobility of the positive charges, we have to dope with the cobalt-3 complex, lithium TFSI, tertiary pyridine. This is the normal practice in perovskite solar cells, whole transport materials. All these dopants creates a positive charges in this material, around 10%, and created positive charges, doped whole transport material increases the mobility of the positive charges from the perovskite into the whole transport material. But the problem with this type of whole transport materials with the dopants is sometimes the dopants, they provoke instability in these materials. And also this is quite expensive and complicated synthesis. So this material is very interesting for scientific research, but not for industrial applications. So here is shown clearly these 3 materials, how the doping works. So this is the HOMO level of your whole transport material. By using these dopants, so you remove 1 electron and it becomes more conducting. But as I mentioned before, the dopants provoke instability. It's because of hygroscopic nature of these dopants. So the dopants are increased. For this is without dopants, 77, that's contact angle. Now with the dopants, you see the contact angle is decreasing. Can we develop whole transport materials that doesn't require dopants, and also they have a better interface, better compared to the spirometallurgy? And before I have shown you the 2-dimensional perovskite to precipitate the interface, and here we have come up with the functionalized whole transport material, where we have these methoxy groups and sulfur. And these are the DFT calculations. Dr. Filippo, who is expert in these calculations, he did these calculations. And the thiophene, bithiophene, interacts onto the surface of the perovskite, binding with the perovskite defects. And this type of materials gives efficiencies close to 20%. However, this is still doped material. Now, can we design a molecule which doesn't need dopants? So here is the one class of materials we have designed, which is a disc type of material. It's called triazotrexene. And similar to the previous concept, where we have a thiophene groups to adsorb onto the surface. So we have included these three arms with the three types of thiophenes: monothiophene, bithiophene, and trithiophene. And the purpose of this disc molecule is to interact one on the top like a columnar shape. So once if they adsorb on the TiO2 on the perovskite surface, the positive charges has to tunnel through this disc type of columns. That's the logic of this study. Now, if you look at the data, KR355, this is monothiophene containing molecule, and the power conversion efficiency using this type of whole transport material is 8.8% efficiency. Now, if you take the KR321, which is shown on the bottom, we have a 3 thiophene groups as a side arms, and the power conversion efficiency is 19% efficiency. And bithiophene is called KR353, which is shown here, and the power conversion efficiency is 15%. Now, how does it reflect with the spirometad? The spirometad has a similar efficiency as KR321. What is the difference between these three molecules? All these three new whole transport materials are used as such from the lab to perovskite solar cell without any dopants. And the spirometad efficiency is with the dopant molecule. So this way, you can see the first time we reported the dopant-free whole transport materials comparable to doped whole spirometad whole transport material. Another class of materials we identified is this work is just online. Is the phthalocyanins. Phthalocyanins are extremely stable performing molecule. They are quite useful in industrial applications like dyeing and food additives. So these materials are quite nice. So, but they have a not well aligned the HOMO level with the perovskites. So we modified the HOMO level of this phthalocyanins by with the different substituents. And also the central metal plays an important role. So here we have taken only two metals, zinc and copper. So instead of complicating the whole study, the take-home message is, so take the spirometad, the power conversion efficiency is 21. That's our reference. Now we take the zinc as a whole transport material, zinc phthalocyanine with the butoxy as a, with the butoxy as a substituent. The power conversion efficiency is 20%. It's very close to the spirometad. And compared with the copper and the zinc, copper 57, that's a zinc, and copper, these two lines, the zinc is giving 20% efficiency, the copper is giving 16% efficiency. So from these slides, what the take-home message is, among the copper and zinc, zinc is the best metal, and among the substitute groups, the functionalized alkoxy groups versus butoxy, the butoxy gives high efficiency. I just want to highlight one more point here. This is so far I haven't discussed the IPC, and here it's very important that I should discuss this. The black line is based on the spirometad, and if you look at the red line, that's based on this type of material. Some of these materials are having color, and that color is absorbing, and that color is reflects the decrease in the power conversion, small decrease in the power conversion efficiency when you use in a perovskite solar cells. Now, so this is very recent our study where we are using a two-dimensional perovskite as a whole transport material and a passivation layer. Instead of all these organic materials which we want to use as a whole transport material and gold as a contact, can we remove all this material, then use only two-dimensional perovskite as a whole transport material followed by carbon, graphene, can act as a hole transport material as well as contact. So this is a highly stable performing configuration. As I mentioned before, there are two configurations, NIP-PAN, and this is a configuration which is called hole transport material free carbon perovskite solar cell. And this particular configuration gives very high efficiencies as shown here, say 18%, and the stability is significantly higher with the 3D and 2D with the carbon as a paste. However, the efficiencies are not comparable to hole transport material containing materials, which is over 25%. Here it's still, we are significantly behind, but the stability is significantly enhanced using carbon as a contact. Now I come to my last section, that's a cost analysis. So what happens if this work is just online, this is ACS Energy Letters. If you design 100 megawatts perovskite solar cell manufacturing process in different locations, how much it costs? So the options are given here. So compact layer of TiO2, mesoporous TiO2, perovskite, spiro, the contact gold we have removed, and copper or chromium. This is one option. And the option 2, spiro and silver ink as a contact, spiro as a hole transport material. This is a 6 point, I give you the cross later. The option 3, we remove the TiO2 and put only tin oxide, perovskite, spiro, and copper as a whole contact. This is option 3. Option 4 is again tin oxide instead of TiO2, tin oxide, perovskite, and silver as a ink. Option 5 is the last slide which I showed you, the carbon as a paste hole transport material. So we remove the hole transport material, compact layer of TiO2, mesoporous TiO2 layer, perovskite, and carbon as a paste with the two-dimensional perovskite. So the material cost per 100 megawatts, so price per square meter is $5.9. With the option 2, it's a $6.6. With option 3, it's a $2.7. Option 4, it's a 3.4. Option 5, it's a 8.1, because here the carbon we are using very thick layer. So that's a costing more. Now, doing this type of analysis and the minimum selling price, that's a sustainable price, minimum sustainable price is $0.35 dollars per watt peak. Now this price can change depending on the power conversion efficiency. And here is the relation between the power conversion efficiency versus MSP. So imagine if we produce perovskite solar cell with a 20% efficiency, the MSP can be around 0.35 as shown here. And this is the curve relationship between MSP and the cost. That's a levelized cost of electricity in different locations. We have taken arbitrarily Switzerland, Poland, Spain, Egypt, depending on the conditions. And the levelized cost of electricity ranges between, that's a 0.3 cents to 0.5 cents kilowatt hour. Now this levelized cost of electricity again depends on the installation, and this is with the installation costs. So it depends on the power conversion efficiency. So you have seen the power conversion efficiency versus levelized cost of electricity. And similarly, we calculated the energy payback time in these locations between less than 1 year up to 2.5 years, depending on the location and the cost estimations. So we can judge this, the energy payback time can be typically 1 year or slightly above 1 year. The average is 1.5 years. Now this is a yearly energy output. This is based on the installation of the location. With this one, I would like to come to the conclusions. I have demonstrated clearly the surface specification of three-dimensional perovskites by using two-dimensional perovskite to increase the stability of the perovskite solar cells. We have fabricated high-efficiency solar cells with unencapsulated devices with remaining 95% of initial efficiency. And I showed you the nanocrystalline TiO2 nanoparticles versus the nanocrystalline materials efficiency, increasing the fill factor. This data also I have demonstrated. So I would like to thank all my PhD students and postdocs and collaborators. Some are left and some are new people are coming. I haven't updated this one. And these are the funding agencies. And this is my group. And I thank you for your attention. My time is up. I will be happy to answer your questions.
Thank you, Professor Naziruddin. And we would now like to extend to the for the questions. So if anyone has any question, they can raise their hand, and we'll put them through. Okay, thank you.
Zawar, I have one
for your
question
time.
from Professor Naziruddin.
Sure.
If you allow me.
Sure. Sure.
Professor Naziruddin, thank you very much for accepting our invitation and delivering a very informative talk. So, by the way, what is the most significant challenge in the perovskite solar cells nowadays? And what are the smart strategies to overcome? Some of you have already explained. And what are the other people they are considering the smart strategies to overcome the efficiency and the stable performance?
Perovskite solar cells are very nice technologies. A solution processable, low cost, is I showed you this techno-economic analysis. And the efficiencies are comparable to silicon solar cells. Silicon solar cells have a 26% efficiency, perovskites 25.7. So they are very comparable. But the difference in these two technologies, silicon solar cells can withstand up to 30 years of performance on outside conditions. Perovskite solar cells has not been demonstrated. It's because of its a weakness in the stability towards the humidity. So the studies which are going on around the world is how to increase the stability by putting various substituents and dopants in the perovskite and encapsulation. So coming direct to answer to your question, enhancing the stability is more important in perovskite solar cells. Efficiency we reached very high.
Okay. Thank you very much, Professor Nazir. Thank you very much.
Thank you, Professor Nazir.
Okay.
Now, thank you. So for our next speaker, I would like to invite Dr. Ricardo Balbino Santos Pereira. He has a PhD in aerodynamics and wind energy from TU Delft. Dr. Ricardo has more than 10 years of experience in the field of wind energy and marine renewable science. He has worked as a consultant for industry, carried out conceptual prototype design, experimental lab work, and developed analytical and computational tools. He has worked as a lecturer over the last few years, developing the online course Technology of Offshore Wind Farms at the TU Delft. And currently he is responsible for the IST course Offshore Wind Energy.
Hello, can everybody hear me? Can you hear me?
Yes, we can hear you. Yes.
All right. Okay. Well, first of all, thank you for the invitation. It's a pleasure to be here. I will try to give my best also because I'm a little bit sick today. So I apologize in advance if my voice is kind of weird. So, my talk today, and I realize it's not the specialty of most of the people here, it is about offshore wind energy or wind farms, and specifically that we want to go a little bit beyond our energy production, because this is what the future is pointing to us. Now, what exactly does that mean? So first, I will give you a little bit of an introduction and tell you about this concept of wind farm control. So the concept in which we look at the farm as an integrated system, and not just turbines individually, let's say, and talk about the loads versus energy paradigm. Then something about the current challenges that we have in trying to make the wind farms of the future more efficient and more useful, actually, for humanity and society in general. And then I present a couple of studies, if I have time, so studies that were done with previous students of mine that I think are particularly relevant. So maybe something quickly just about myself, as Dr. Zawar was already mentioning. I did start my university studies in Lisbon University in aerospace engineering. Then I went to the Netherlands to do a PhD on wind energy and aerodynamics. And well, since then I've been a lecturer at both Lisbon University and the TU Delft, and most recently, just this year, I have joined an offshore renewable energy institute here in Lisbon called WAVEC. But the point is to tell you that, as I aim to show here with this slide, that I have worked on all sorts of scales of problems. So let's say from a very small airfoil scale up to rotor scale and farm scale. So addressing, mostly aerodynamics, but also control, and also something to do with the structures itself. Now, what wind farm control? What is the problem? What are we talking about? So, what you see here on the top left is probably the most infamous picture of wind energy, of offshore wind energy, because what we see here is the turbines, so the row of turbines there. But in this specific day, the weather conditions or the meteorological conditions were such that you could really see the wakes of the turbine. So the wake is the region of the turbine that is behind the turbine, the region of the flow that is behind the turbine, I should say. And what we see here clearly is that when the wind speed is aligned with the row of turbines, so we see here like 1, 2, 3, 4, 5, when the wind speed is in the same direction as the line of turbines, then of course the turbines that are downstream will be affected by the turbines upstream. Namely, the turbines downstream will see a smaller value of the velocity and higher turbulence, and so they will produce less power. So this is the problem. So what can be the solution? Well, the solution, of course, has to be integrated farm control, which means basically that you can have a control action, so you can have a control command, if you prefer, that is different for different turbines in the same park, and which might allow you to maybe sacrifice a little bit of power on some of the turbines, but overall increase the total power production of the farm. This is the main idea when you talk about farm control, that you look at it as a whole system integrated and not just individual machines. So what does this mean then in practice? Well, the idea is that we must depart, so we must get away from your classical so-called greedy control. So greedy control in the sense that typically the turbine, so each turbine in the farm would always try to be getting as much power as possible. This is why we say that it's greedy, because it's just trying to get all the power from the wind it can. Now, as I mentioned, the idea with wind farm control is that we can perhaps get more power in total, maybe at the expense of losing some power on a specific turbine. Now, there are two main ways that people think about this farm control, in this collaborative control. One is called turbine derating, which basically means that you operate the turbines upstream at a slightly smaller power setting and slightly less loads, which means you extract less energy from the wind, which means you leave more energy for the turbines behind. However, the most popular way that people are thinking about farm control is actually what I'm showing here on the right. This picture is I believe, a bit more relevant, because this is showing the concept of wake steering. So wake steering, what does it mean? Well, like the name is implying, it means that you try to steer the wake of the turbine away from the downstream turbine. So example, if you have here this green dashed line, this is the wind direction, and you put your turbine, you force it to be misaligned. So you force it that it has an angle with the incoming wind speed. And what this will produce is that this the wake, so the region behind the turbine with a reduced velocity, is actually deflected. Is actually not traveling in the direction of the wind speed, but actually it is deflected. And ultimately you can use this to steer the wake away from the turbine number 2, from the turbine that is downstream. This is more the idea that we are, or the more popular idea in wind farm control than what we're actually looking at here. Now, but wind farm control, as I mentioned, it's a bit beyond just the energy production, because we always must keep in mind that there is a compromise here between loads and energy, because obviously if we produce more energy, this means that we have also increased loads and load fluctuations. So in other words, we bring more fatigue damage to the machines. And this is especially relevant if, well, nowadays, because we are in 2022. So this means that there are a lot of wind farms that were installed 20 or 25 years ago that today they reach the end of their supposed to be operating life. And as such, the question becomes now, what is the level of fatigue damage? If we such that should we decommission the installations, or can we prolong the lifetime a couple of more years? So the issue of fatigue damage is definitely fundamental and driving our actions in terms of wind turbine control. So it's really, I mean, we want to get more energy, but we also want to keep the loads down. So it's kind of the paradigm here. Okay, now regarding the modeling of the wake itself, I will spare you the details. I will just tell you that the wake is characterized. The wake of a turbine is characterized by a decreased velocity magnitude in the wake, like we are seeing here, and an increased level of turbulence. And well, neither of those are actually good for the turbine that is behind, for the downstream turbine. So usually there are a couple of ways that you model the velocity deficit. The Gaussian model is actually more widely used, is this one illustrated here. And as for the turbulence modeling in the wake, usually the Crespo-Hernandez model is used, which I'm also showing here. Now, more interestingly, maybe, is other challenges that we have for wind farm control, and specifically the aerodynamics related with it. One, of course, has to do with the wake deflection. So, of course, if the idea is that we can, on purpose, misalign the front turbine and actually steer the wake away from the downstream turbine, well, then, of course, we must know how much of a deflection is obtained for a certain misalignment that we impose. And well, I've been working on this. I leave a couple of references of previous studies of my students in the end, if you are curious. Yeah, but this is one of the main topics that is, let's say, open for study as far as wake aerodynamics in the farm goes. Now, something that is very important, of course, coupled with the aerodynamics, is the structure, because the structure must resist the loads that will be present, right? Now, what I'm showing here is mostly figures from my colleague from the Porto University, from Filipe Magalhães. And what I'm showing here is a couple of methods that are used. So basically, the idea is that if you install accelerometers throughout the turbine, namely at different positions of the tower and positions of the blade, you can actually look at, of course, the motion of the blades, of the structure as it vibrates, and ultimately you can say something about the natural vibration frequency, or the resonance frequency, right? Now, the interesting part is that over time, as the material will degrade, namely for a composite material, when you start to have delamination of the different sheets, then you will see that effect on the natural frequency itself. Because of course, if it's softer and delamination leads to a softer structure, then you will see that effect on the vibration frequency. So ultimately, this is a non-intrusive method of saying something about the fatigue damage that will be happening on the turbine. So you can understand why it is so interesting. So it's a remote way of sensing the fatigue damage without having to stop the operation. Now, and then there is the control part, because wind farm control has the aerodynamics, the structures, and the control. And the control part can be both at the turbine level. For example, turbine control challenges can be for a floating machine, for example, as we are showing here, in which you will be having the back and forth motion and you want to compensate that, for example. Or you can be talking about the wind farm control specifically, which can mean defining different control actions for different turbines within the same farm, like we mentioned before. Now, these control actions itself can be based on a bunch of phenomena, namely based on the turbine age, based on the instantaneous demand for electricity, based on your maintenance strategy. So all these factors will play a role in deciding what is exactly the best strategy for your farm. Quickly, if I still have time, I'm going to show two case studies. So one is from yaw-based control maximization. So yaw-based control yield maximization, meaning trying to get as much power as we can. This was for a row of 8 turbines in a row, and we were using the NREL code Floris, and we were looking at 3 different wake deficit models. The results, we are showing here. So as an example here on the top, we can see an example of what the flow field will look like. So this is turbine number 1, T1, T2, T3, so turbine 4, turbine 5, turbine 6, etc. Wind is coming from the left-hand side. And we have the velocity magnitude here, okay? So we can really see, first of all, the wake effect. And we can also see that the turbines are at an angle, and because of that, the wake is also not following directly the wind direction. So this tells us something about how the wind field or the flow field looks like. And we did this study for different configurations of the farm, namely different spacing, considering different wind speeds, considering different turbulence intensities, wind directions, etc. And the conclusion that we came to is that there is definitely room for improvement, a lot of room for improvement. Up to 30% more power can be obtained, depending, of course, on the conditions, on the inflow conditions, and on the turbine layout. So this was just quickly going over what we can do with wind farm control for energy maximization. Now, another study I want to briefly tell you about, also as I know it was already discussed today, regarding hydrogen production from offshore wind farms. Now, I know that there are a lot of people and a lot of studies addressing this. The reason why I'm telling you this is because the study that we did was using data, so more specific to the Portuguese, as I'm Portuguese, to the Portuguese case, namely the Windfloat Atlantic is the first floating offshore wind farm that we have here in Portugal, and we were considering 2 sizes of the farm to do a bit of a sensitivity analysis. Now, the real interesting part about this study is that we managed to match the production of hydrogen to curtailment events, meaning curtailment when the price of electricity is very low because there is too much availability or there is little demand. Then it's in this instance that you actually go and produce the hydrogen. This is the main idea here, and we did it. And long story short, if you're curious, I will just show you, or you can check the paper later. But the one number I wanted to leave you with is that, so maybe the graph here on the bottom, this is showing us what is the H2 production cost for different ratios between the hydrogen power plant and the wind power plant. And it seems that it's around 35% that minimizes the costs of hydrogen production, meaning if you'd have a 100 megawatt wind farm, probably your hydrogen farm, which would minimize the hydrogen production cost, would be 35 megawatt. Yes, so as a conclusion, let me just tell you that wind energy is indeed key to the economy decarbonization, but we must look at it in an integrated way, especially because of its intermittency. Now, wind farm control does promise more efficient, more sustainable, lasting operation of farms, and we believe it will be only more and more relevant. Presently, it's not yet implemented, wind farm control. This is not only because of the operator's conservative approach, but also because there is some uncertainty on the wind farm aerodynamics and structures response to these proposed control strategies, namely to the yaw misalignment control strategy. So this is what I had for you today. I hope you enjoyed, and here are some references which I shared already, but I can leave them here again. So with that, I open the floor for questions. Thank you. Hello?
Thank you, Dr. Ricardo. Just waiting if anyone has any questions, they could refer them to you.
Hello?
Hello? Hi.
Yes, hello. I have a question regarding the stability of the systems. There are issues with the lubricants in the system, in the turbine. So, are there any research you are doing in this area and the stability of the lubricants?
The stability of the lubricants.
Yes, exactly.
I'm sure that there is research in this area, but it's not my field. No, I do mostly aerodynamics, control, and structures. So material science, which is indeed the topic of this conference, is not exactly my strong suit.
Okay, thank you. Thank you.
Sure.
All right, I think that was it, Dr. Ricardo. Great talk. I enjoyed it, and yeah, we should see. We have a team member in Portugal right now, so I think he will get in touch with you. So thank you for the talk.
Sounds good.
And
No problem. My pleasure.
all right.
Right.
And now I would like to invite Professor Fatma Montebor. She is a full professor at Instituto Superior Técnico, the Higher Technical Institute in Lisboa, Portugal, at the Department of Chemical Engineering. Her scientific activity focuses on new functional coatings for surface protection and for energy storage. She coordinates the electrochemical energy storage research team and a master program in energy storage. She has been involved in several national and international projects in collaboration with many partners. She has been awarded with the EFC medal and has received a doctor honoris causa degree by the University of Mons. She's also co-founder of the company Charge2C NewCap that fabricates supercapacitors. She's also the vice president of research and international affairs at the Higher Technical Institute and member of the management board. So, Professor Fatma, the floor is yours. Thank you.
Good morning. First of all, I would like to check if you can hear me well. Can you?
Yes, we can.
Okay,
Yes,
thank
it's
you.
very
And
clear.
you see my And you see my presentation in presentation mode, right? Thank you so much.
Yes, yes, we do. All right.
Okay, perfect. So thank you very much for introducing me. It's really a pleasure to be here today. I want to acknowledge the invitation for presenting my perspective work here in this workshop. I think it's a great opportunity. So I'm very happy and very glad with this opportunity, and I thank the organizers for the invitation. So today I will speak about coatings for high power electrochemical energy storage. Can you see my presentation moving down?
No, we can't see the presentation moving down.
I think I have a problem here. I have to disconnect one of the screens. I think it will be better now. And now is it fine, right?
It's okay, take your time.
Yeah, I'm sorry, this is the question of working with different Okay, so can you see it moving now, right?
Yes.
Yes. Okay, so I work with coatings.
Sorry
yes.
for interrupting. We can see the slide. Can you just put it on normal slideshow? Yeah, just the normal one, yes.
Okay, perfect. I'm sorry.
Perfect, yeah, we can see it.
Okay, thank you so much. So, well, some of you already know me, and you know that I work with coatings. And in this specific case, the coatings that I work with, they can be used for different purposes. So you know that the multifunctional coatings are layers that we can apply on the surface of a certain material. And by designing these layers, we can and we can confer to the surface different functionalities. So we can use coatings for surface protection, for example, for corrosion protection. And this is very important, for example, in the transportation sector, in the oil and gas industry, for offshore applications, for the electronic industry, etc. We can also design functional coatings that are used for biomedical applications in order to improve the resistance of the materials that are used, for example, in implants. We can use coatings for heritage preservation, and we can use coatings for electrochemical energy storage and for hydrogen production, for example. So I am a person that have been working in the coatings area for many, many years, and today I will introduce you to some coatings that we can use for electrochemical energy storage. So, So why is energy storage so important? So we know that energy storage nowadays is everywhere. We do need to have energy wherever we are. So it's critical for our lifestyle. And in order to afford energy in any place, we do need to store it. And then we can use it independently if we have the source of production near us or far away. So we can store energy. It's important to store energy and to use it when it is necessary. And of course, this is very much aligned with the Sustainable Development Goals, especially with the SDG 7 that is related to affordable and clean energy. So how can we store energy? Well, we can store energy in different forms, but today I am very much concerned with the electrochemical energy storage. And we can store energy using batteries. So batteries are something that are devices that are very familiar to all of us. If you count the number of batteries that you have at home, you will be surprised because you can easily count some tens of batteries that you have at home. around you, in your pockets, in your laptops, mobile phones, etc. So batteries are part of our daily life. So batteries can store typically a high amount of energy, but they provide modest power. So they are good in delivering energy in a slow way. And we also have supercapacitors. Supercapacitors are devices that store a small quantity of energy, but they can deliver this energy very fast. So it means that they have high power. If we look to this plot, you can see here different energy storage devices. And you see that in the vertical axis, you have the energy that you can store, and you see that batteries and fuel cells are the ones able to store a higher amount of energy. And in the horizontal axis, you see the amount of power, and you see that the devices that can store more power are the capacitors and ultracapacitors. And you see that some of these devices, like the redox supercapacitors, can also store a good amount of energy. Of course, that our ultimate goal is to move to the corner where you can really have devices that store higher quantities of energy and also providing high specific power. So this is this area of the Dragon plot here is still an open gap, and we are all looking for strategies to improve supercapacitors and batteries performance in order to fill this quadrant in which we can combine simultaneously specific energy, higher quantities of energy, and also deliver this energy at a very high rate. Of course, that for most of the devices that we have nowadays in the market, so lithium batteries, ultracapacitors, etc., this is still not possible, and it's really a very difficult task to achieve this combination of performance. So, coming back to batteries and coming back to supercapacitors, because these are the state-of-the-art devices that exist in the market for electrochemical energy storage. So supercapacitors, as I explained, they deliver energy very fast. They store small amounts of energy, but they can deliver it very fast. And typically, the supercapacitor is characterized by a squared voltammogram and by a triangular charge-discharge curve. So it means that the voltage over the time follows a triangular shape. On the other hand, in batteries, we have something a bit different. The voltammetric curves, which means the current as a function of the potential, typically shows very sharp peaks that are due to redox reactions, because batteries store energy thanks to the existence of chemical reactions. And then the charge-discharge curves, it means the dependence of the variation of the voltage with time follows follows a curve that has some plateaus. We call it spider leg. So you see that there is always a plateau in the curve when we have a battery type material response. Of course, then by playing with the materials that are used for assembling the electrodes of these devices, because any electrochemical energy storage device has electrodes, as a positive electrode and as a negative electrode, and materials are the key constituents of these electrodes. Thus, by playing with the chemistry of the material and with the properties of the material, you can tune the response of your electrode in order to have a response that is closer to a supercapacitor or a response that is closer to a battery. So it means that we can tailor the electrode materials in order to vary their response from what is typically a supercapacitor response to what is typically a battery response. And between these two extremes, the supercapacitor and the battery, there is an empty world. Okay, so basically all this region that I show here in green and orange is still an empty world. There are no devices, or almost no devices can provide these intermediate responses. So nowadays the market is dominated by the supercapacitors, the ones in blue, and by the batteries, the ones in brown. And here in the middle we have an empty gap. And industry is really looking for solutions that can fill this gap, because there are many needs, many applications that require metrics that are neither metrics from a supercapacitor nor from a battery. So sometimes we use a supercapacitor, but it is not the best solution. But also a battery is not a good solution. So frequently, when looking for a device for a certain application, we may not have the right choice on the shelf. And so we are working on the development of these intermediate solutions that are tailored to meet the needs of the application. So in order to develop these solutions, we need to pay attention to different things. We need to pay attention to the storage, the electrochemical energy storage mechanisms, so the mechanisms that govern the way our energy is stored. We also need to work with electrode engineering aspects, how we combine the materials, the architecture of the layers, the electrode architecture, phase design, defect control, doping of the material, formulation of composites, and combination of synergistic materials, for example. These are aspects to take into consideration when designing a new electrode, a new material for electrochemical energy storage. And then, of course, we do need to know for which application this electrode will be assembled. So, because the applications, they require different responses. For example, if you want to control a wind turbine, the so-called pitch control in a wind turbine, you do need very fast response. So we do need something that responds very fast and provides good energy density. For example, nowadays wind turbines, and my colleagues spoke about them, they use lead-acid batteries for pitch control. And this is not so good because lead-acid batteries have a slow response. And then there is need of devices that have a time of response and also enough energy density to meet the demand of the wind turbine. And for example, in an electric car, in order to increase the chargeability, in order to charge your car in a faster way, we also need to adapt the system and to introduce devices that allow to inject energy in a fast way. So these are examples of what we have to consider when developing our electrochemical energy storage device. And when we design new materials, we have to consider all these aspects that are essential for designing and providing a functional solution tailored to meet the requirements of the application. So one opportunity has to do with coatings, especially with electrodeposited conductive coatings. Of course, that when you design a material for electrochemical energy storage, the first requirement is to have a fully conductive material. So the resistivity of the material shall be extremely low, and we need to maximize the conductivity of the material. And thus we can use electrodeposited conductive coatings in order to design new electrodes for electrochemical energy storage. So we can design new materials for electrodes by using, for example, electrodeposited coatings. This is very fast. It's a very simple way to produce electrode materials. We can combine different metals and different materials in order to obtain synergistic and consecutive redox reactions, but we also have some problems. Capacity fade is something very common when we use these materials, so we need to find strategies to minimize these capacity fade issues. If the coating is damaged, for example, if it is scratched or if there is loss of adhesion, we have electrode malfunction, and then we have a short circuit. And of course, if the capacity decreases too fast, then our cell fails. So we do need to pay attention to all these degradation phenomena, and it's very important to create new architectures based in hybrid materials that show increased capacity. Capacity is the amount of energy that the material can store, that have very highly reversible reactions, mechanical stability, smart repair, and smartness. These are important properties when designing a coating for electrochemical energy storage. I'm showing you here some examples of different coatings that we have tested for electrochemical energy storage for positive electrodes. We have, for example, cobalt oxide layers combined with a graphene oxide, electrochemical reduced graphene oxide nanoflakes. This kind of coating provides a very good capacitance, which means that it has a very good electrochemical response. It's very good to store energy, and the presence of graphene, for example, increases the resistance of the material when there are mechanical stress in the material. We can also design different layers. We can combine different metal compounds, and we created some nickel hydroxide, cobalt hydroxide layered films, and by this way we can have a response coming from different metal compounds, and we can increase the amount of energy that the material can store. And we can also combine different nanoflakes, in this specific case, manganese oxide nanoflakes that were deposited on a 3D coating made of metallic forms. So these are examples of electrodepositive coatings that we use for positive electrodes. So, of course, that to maximize the amount of energy that the electrode can store, and in order to tailor our matrix, we always need a high surface area with nicely organized 3D architectures, and of course, we do need the right porosity. And for that, we have been working with 3D high surface area metallic nanoforms that are basically a coating that is deposited on a metal current collector, over the current collector, so we can create an electrode without using binders and without using strange additives. We can create the active material directly on the current collector with very good adhesion, and we can form this type of structures that you see here in this page, and we can create this nanofoam-like material, which is basically a structure made of columns that form over the material as hydrogen is released from the surface. So we call this process the formation of foams under the dynamic hydrogen bubbling template. But basically what we achieve is this type of coating. So it's like a big forest, a very a nicely organized columnar structure. You see here these structures, they seem like big trees, and between these trees we do have the pores of our material, and these structures, they have a very high surface area, which is very adequate to increase the amount of energy that this coating can store. Because at the end of the day, this is a coating, is a very porous coating, is a very high surface area coating made of an electrodeposited metal. And these type of coatings, they have extremely good conductivity. And they have also very good adhesion to the current collector. So we can easily construct an electrode without spending a lot of money. This is a very cheap process. It's very easy to scale up, and it's very easy to implement at the industrial scale level. And then we can do something even more interesting. So we create those trees, those big structures made of the metal nanofoam, and then we can decorate these nanofoams with other metal oxides. You see here what we did. So we had the original tree, so the original metal nanofoam, and then we created over it a very thin layer of manganese oxide over the original nanofoam. You see here these nanosheets. They are covering all the leaves and all the branches of the original structure, and we created a tailored material that has even higher energy density abilities. So we can functionalize your coating, our original structures with different metal oxides in order to increase either the energy density or the power density. And for example, here we see a deep view of the structure of the materials that we have deposited over the original nanofoams. So we clearly see here in this high resolution TEM image the original branches and then the decoration of these branches with those manganese oxide nanostructures that we deposited over the material. And furthermore, we can see that the capacitance of the material, that is proportional to the amount of charge that the material can store, varies, for example, with the size of the pores. So larger pores tend, in a certain range, tend to give higher charge ability. We also observe that the capacitance retention of these materials, when they are charged and discharged consecutively, it's quite good. It means that we can charge and discharge the material up to 1,000 times without having a significant capacitance loss. So it means that we have a very stable material that stores energy in a very stable way. We can also tailor and we can also define other properties of these materials. For example, we can produce materials that are more crystalline or more amorphous. So by playing with the electrodeposition parameters, we can also play with the structure of the material. And this is very important because the structural properties, the crystallinity or the when the material is amorphous, we can have different properties, as I show here in this image. For example, when we have a crystalline material, we can achieve a very good write capability, which is the ability of the material to respond to high currents. We can have a very good write capability, and we can have a very good capacitance retention. And for example, when we work with an amorphous material, our capacitance retention is a bit more modest. So we can really see that these structural properties also control and define the matrix of the electrode. And for example, in this work, we demonstrated that some crystalline features over the material are important to obtain better matrix, better electrochemical response for our material. Also, it's very important to demonstrate and to create electrodes that have a nice relation between specific power and specific energy. It means that we normally want electrodes that deliver energy at high power, which means that we want materials that can sustain a high power demand. This is a typical Ragon plot where we see the variation of the specific energy or the specific power with energy. So typically the energy is lower, so the energy tends to decrease when the power increases. So at high power you get only lower energy. And this is something that we have to avoid. We don't want this. We would like not to have these curves. We would like to have almost horizontal curves. Still, these materials that are based on foams decorated with manganese oxide, they approach the conventional shape. But we can see here, for example, that our green curve, that is the material that we developed, is the one that provides higher energy for the same power. So if we keep the power, we see that some commercial materials deliver lower energy compared to the green ones that deliver higher energy. So we can really increase the amount of energy that you can deliver at high power. And this is quite an interesting result and a very promising way to increase the metrics of your device. We can also work with electrodeposited manganese oxides, and these are also very, very nice systems for electrochemical energy storage. In this case, we have electrodeposited manganese oxide over the current collector, and we have tested the properties of the materials obtained at different potentials. We have very nice triangular curves, and we have a quite nice response in terms of specific capacity. We demonstrated that the specific capacity of the material varies with the electrodeposition potential, and it attains a certain stable plateau, which means that at a certain point, the potential that we use to form our coating is no longer a problem, or is no longer affecting the performance of our material. But the most important aspect to show here is that these materials have excellent capacitance retention when they are consecutively charged and discharged. So we can charge and discharge the materials for thousands of times without having a capacity loss. And this is really very important because we want to keep the capacity of the material as stable as possible, so in order to avoid early degradation of the electrode. So, and these electrodeposited manganese oxide coatings are extremely interesting because we clearly see that the specific capacitance and the capacitance retention is practically constant over cycling, which is a very good result. I think I do have a very short time, so I will go very briefly through the next slides. But I can say that we can deposit different coatings of different compositions over different materials. For example, we have deposited nickel manganese hydroxide coatings on carbon nanofoams in order to create flexible electrodes and light electrodes. So we combine the carbon nanofoam with the nickel manganese hydroxide, and we obtain the material. I can show you here this plot that is a material that basically keeps a very stable response when it when it is cycled. So we can cycle this material for 3,000 times, and basically we do not observe any relevant changes or damages in the material over the time, which means that these coatings are very stable when these materials are consecutively charged and discharged, charged and discharged. So it's a very stable material. These nickel manganese hydroxide coatings deposited on carbon nanofoams. We also deposited iron oxide hydroxide coatings also on carbon nanofoams. This is a material that is very good for a negative electrode, and again we observe that these materials are very stable, as you can see here in this plot. The fresh material and the aging material, they have a very similar response. So we are really in the presence of very, very stable material with a very good capacity retention. And then we can assemble these materials, different materials, in the positive electrode and in the negative electrode to create asymmetric cells. And we can test these cells, and in this specific case, we use our iron oxide deposited on carbon foam and the nickel manganese hydroxide deposited also on carbon foam. We assembled an electrochemical cell, and we see again a very stable electrochemical response with very, very good capacity retention on 10,000 cycles. So we have a device that can work for 10,000 cycles. This is much above a conventional battery, and actually this device, it can go up some hundred of thousands of cycles, with very good capacity retention, with a very stable impedance response, and with a very nice energy density and power density correlation. So this curve is now more horizontal than the previous ones that I showed you. So we are really obtaining a curve in which the energy density varies less with the power density, which is a very good achievement. Finally, our work is a bit more than designing new materials, because we are also working with the scale-up of these materials and with the scale-up of these devices. We have created a spin-off company, which is now an independent company, and they have developed first they have developed small prototypes using the materials that we have created in the laboratory, and then they scaled up these devices to commercial devices that can be used, for example, in trucks. So this is more or less our roadmap. So we started at the laboratory research level by creating our nanoforests, nanotrees of materials, coating, a dendritic coating. Then we assembled small cells in our laboratory. Then the company made the first prototype, so small cells like a mobile phone cell, and then they moved up to larger scale modules with 24 up to 30 volts, and that are used, for example, for engine cranking in big trucks. Many of these materials and devices are already in the road, being tested in different trucks in Portugal and abroad. So some of these devices were tested in the United States or tested in China. So we are testing them in different environments, in different conditions. So this shows that the material that you design in your laboratory, a coating that was designed in the laboratory, was successfully scaled up to a commercial application. And so these are my concluding remarks. So these electrodepositive coatings, they pave the way to create electrodes that have increased energy density and high power rate. High surface area 3D architectures can be easily produced in the lab, and they can be tailored to optimize the electrochemical response. We can combine different materials with metal compounds. We can combine graphene or carbon nanofoams, and we can tailor the metrics of the electrode. And of course, to succeed on the scale up, we need really comprehensive studies on the individual electrode materials and on the cells to minimize flows and to fully confirm the reliability of the materials. And finally, I would like to acknowledge the contribution of the members of my team that are always supporting me, and also the financial support from different national and European projects for this area of research. Thank you very much. So I'm your disposal.
Thank you, Professor Fatma.
So Zawar, I have one question from Professor Fatma.
Yes, please.
Yes, sir. Go ahead.
Professor Fatma, first of all, thank you very much for accepting our invitation and sharing a very thoughtful presentation on the energy storage materials. You have been always very kind to us, and whenever we request you, you accept our invitation. So it is a great pleasure to having you with us today. And just for on my, the point of view, the electrodeposition of, the electrodeposition of, for example, manganese oxide on carbon forms or other. So can you a bit shortly, briefly explain the procedure? How can we deposit these coatings on carbon forms or some other, the mesoporous materials?
Yeah, so basically you need a carbon foam, which is a conductive substrate. So you always need a conductive substrate. And then you apply these coatings from permanganate, from an electrolyte, from a bus that contains the manganese precursors, set manganese permanganate. It's one good start. Of course, this requires a cocktail with some other surfactants and additives. We are preparing a paper on this, so I can then send you further details on the experimental procedure that I also don't know them all by heart, because this is a study of a PhD student, so I don't have all the details in my mind, but basically you start from a manganese containing solution, and then it's a potentiostatic process. So you apply a potential for a certain time and you form your coating.
Okay, Professor Fatma, just one more question. The same concept, you are applying this concept to the supercapacitor or some other. So can these concepts can be combined with, the battery materials or some the hybrid materials as well?
Yes, you remember the first slide I showed. I can share it. I can share it here. So in this slide, you can really move from supercapacitor to battery. So some of these materials are more like battery, like the ones that I showed deposited on carbon foam. The nickel manganese hydroxide was closer to a battery material. And also the manganese oxide only was closer to a supercapacitor. So by playing with the nature of the materials and by combining the right materials, you can move from the supercapacitor side to the battery side. So it depends on the proportion of the materials, and it depends on the materials that you put in your coating.
Okay, thank you very much, Professor Fatma. Thank you very much.
Welcome.
Okay. Thank you, Professor Fatma. I also have one question, if you don't mind. I think why did the research team decide on a leaf type morphology for the particles?
Because it gives you a very high surface area.
Mm-hmm.
And these leaf types structures, they give an excellent porosity as well.
Okay, understood. And you are currently investigating others as well, I hope.
Yes, we are investigating different materials, also nanoparticles and materials produced by other roots. So we are nowadays testing more than 10 different types of materials.
Because according to my understanding is that it's basically a matrix and you could design whatever morphology you could if you are a good architect.
Yeah, exactly. That's a good comparison. If we are a good materials architect, we can design compositions, architectures, crystalline structures, layered materials, etc.
All right. Amazing talk. Thank you for your time. And
Thank you.
this concludes our day 2 session for the International Conference on Chemicals and Materials for Emerging Technologies. So our evening session will start at 3 p.m. And thank you all for joining, and thank you specifically to all the speakers for contributing.
Thank you so much, Zawar. And thanks for Dr. Abdul Shakur. I would like to thank all the speakers and the participants for today. I would like to remind you all that we still have an evening session. It will start at 3 p.m. Qatar time, where we will talk about SDG 9, industry, innovation, and infrastructure. We will have speakers from all over the world, from US, France, Tunisia, UK, Qatar. So please stay tuned and see you at 3. For now, we will just share with you some posters video. So enjoy, rest, and see you at 3 p.m. Thank you so much.
Thank you, Noor. Thank you very much for concluding very interesting session. Stay blessed.
I have more duties.
For the new simplification, yeah.
But you can make more, right? So you can just give here to Farzana. She will do on behalf of you the same. Farzana, it's already finished.
Yeah, your work. Yeah.
This one we don't need much.
Yeah. In case, otherwise you just publish it.
So the one that I presented about combination, so you can. XPS and
You can do here. Leave samples to her. Whatever you want. Start communicate with her and try to finish it off paper. Keep in mind we need to keep the acknowledgement of the project who funded you, okay? Acknowledgement.
Yeah.
Yeah.
On this project, like every that I have in my reported.
So you will see the directive also. If you keep sampling only, we will do something on your sample, do the absorption also. And we
The new one actually here is like better than the one I use, but the one I use is very positive. The actually here is choosing 1, 2, 3.
oh, in the whole video. 1, 2, 3. Just names and titles if you can. Name and title, that's it. Thank you.
Yeah. And another one.
So she will take
I'm really all about the point.
and then try also the absorption. But we need bulk. Only you can see the absorption. Anyway, and then
You don't know what the modification or the combination. Put the sample and then you can run the right.
And you can transfer the data also.
You want the picture. Okay.
Videos what you make. We can keep the paper on. The document will submit.
All the people, including the one I put inside the SMS.
Yes.
Okay.
Good luck.
This is me.
Or you can keep because
Yeah, you can keep nice.
You bring from Ganesha?
No, I buy there. Foto category dan foto connection. So from this, you put it outside.
Wait a minute. There next to take all.
You have the board, the access now, right?
Yes, I took it.
Okay, I will leave. I will come back to this.
And who will take it?
I will try. I will try to be active.
Who is there? Muhammad Shami also, he sent a message that he won't be.
Why?
I don't know. Just 1 moment. Is not available from now. Next talks.
Which next talks? Yeah, for he means that this one, but not at 3 p.m., right? Next talks.
Then who will
Oh, okay. I think he means this the Fatima and
No, who will be the moderator? He will be there.
I ask him. I don't know. You will be available at. You want me to call him?
I will call him.
I tell him if he will be available at 3. But be a point. No, I don't know. What's the name. Actually, it's his speech. الو مرحبا دكتور معك نور. هاي دكتور. يس دكتور بدي أسألك أنت حتكون موجود الساعة 3 for 8. Yes, okay. So you will be the moderator for point, right? No problem. Just not okay. It's okay. I just wanted to ask that you be there. Okay. Great. Thank you. Bye. Okay, great. Yes, thank you. Thank you, Professor. Bye.
And I will give a certificate for the posters. And who will present me?
I don't know. You want me to announce? Okay, give me name. I will announce.
Then,
I will try to be free. Because yesterday I arrived home, like I parked the car 3 o'clock. So I will do my best. Thanks. You have to talk. I mean, you organize that. At least just show your face. Check and tell me. Okay. Because if you want me to say something, I need to prepare. So you want me to do this? To conclude and give the prize?
Yes.
Okay. We give the prize first.
And then come to say thanks to everyone.
And we will show the certificate.
Yeah, I will use it. You can share it.
Thank you.
No problem. Yes, so who is the clear? You can transfer all the data.
Yeah, actually, more than
No, but first give to someone. I want someone. Who is it? Anissa. Yeah. Sumaya.
Sumaya.
Sumaya and she was writing another paper. To give she's give it to Hannah. She will take care of you after. And I think what you can take care or someone has to be here.
Okay, I can start first. After that, I will refer you. Yes.
Okay. Yes.
But that's, yeah, it's not done. So for the dye, I want for the time and.
No, can I see which dye is working for you?
I'm on the. No.
I asked you.
There's you mentioned that this the for this I will be missing. The mode of this is special and permanently. This is not the obvious, but there is likely. Last time you reach dye, you are leaving some building. Only some of blue. Some of blue? Yeah. This is the calendar outside.
Not with the RGOC and right?
No, no. Here is RGO, but mostly I think of the RGO. Oh, it's not 100%, but it really change color and intensity into yellow. Yeah, separate and some of the detail. Now it's showing the color, right? Can we have a look on the final one?
No, this is the final round, but no color. Still color.
So what about the first one? It was the reflection really well.
No, it is for DNS report.
That is no detection. No, detection of DNS. In which of the guys?
Hi everyone, my name is Haya Haji and my colleague is Reem Haji. We are Qatari Chemical Engineering undergraduate students studying at Texas A&M University at Qatar. We have done this project under the supervision of Professor Mohammed Al-Hashmi, which is about high-performance, functional, smart thermochemical polymers for the chemical industry. Now, to begin with, we know that COVID-19 has changed the society and economy of the world, including GCC countries. In a post-pandemic recovery, regional GCC industries such as chemical and petrochemical place efforts to aggregate the growth of the economy. This led to an increased demand for the human resources. Laborers suffered from hyperthermia and their core body temperature exceeds 38 degrees Celsius. We know that Qatar had imposed the no working policy when the ambient temperature reaches around 50 degrees Celsius. The United Nations have concerns related to the workers' health. Also, the Sustainable Development Goal number 3 is about ensuring healthy lives and promoting well-being all at all ages. And so our aim for this project is shown in this video.
So from this to this thing.
Now, for our hypothesis, we believe that the polymer changes structural configuration depending on the energy provided to the system. At normal body temperature, the series of divalent donor between the triadyl acceptor will be in a stable alternate configuration. Hence, the thermodynamic polymer will be electric. However, at high temperatures, the thermodynamic polymer will be subjected to heat. The diaphragm will then adopt a less stable continuous configuration between diaphragms. In this case, the observed color will be red as seen from this picture. As you can see here from this video, that the polymer color changes from red to purple and becomes golden.
which is needed. Long time, but for now, so far, I like it outside that
The methodology we follow is by planning our thermochromic polymer by studying cross-coupling polymerization in the phase solution using palladium as a cathode. Successive extraction was performed using methanol, acetone, hexane, and purify the polymer. And finally, it was collectively carbonized. And here you can see the sample. Also, here you can see the sample.
But not translated, but we can
Good evening, all. Can you hear me well?
Yes.
Yes.
Good evening, all. I would like to welcome you all in our evening session and last session for this conference, the second international conference on chemical and materials for emerging technologies, where we will talk about sustainable development goals. Today's session will be considering goal 9, which is infrastructure, innovation, and advanced materials. I would like to welcome our moderator for today and our partner in organizing this conference, Dr. Mohammed Shahemi. Professor Mohammed Shahemi, he is a leader of the Surface and Interface Research Team at University of Paris, and he's also an executive editor-in-chief for Chemistry Africa Journal. And I would like to take this opportunity also to thank him for his great opportunity for collaborating with us to organize this conference. Professor Mohammed, the mic is yours.
Okay, thank you very much, Noor. Good afternoon. I'm in France, so I say good afternoon or good morning or good evening. Hello, everyone, wherever you are. We have had a great lecture this morning, and this afternoon too. We will have a nice lecture about addressing the Sustainable Development Goal number 9, industry, innovation, and infrastructure, as you have said right now, dear Noor. And we will start with a keynote lecture from Paris, from actually my laboratory. It will be given by Professor Benoît Pirot. He's professor of chemistry at Université Paris-Cité in city center. The talk will be about innovative flexible materials designed by 2D printing for personalized medicine. I would like to say that I know Professor Pirot for a long time, maybe more than 20 years, I would say. I don't have his CV, but I know his work very well. He's an expert of electrochemistry, bioelectrochemistry. During his early career, he got interested and collaborated with physicists involved in transistors. So he take advantage of remarkable collaborations with physicists interested in transistor for the development of smart biosensors and bioactive surfaces. Professor Benoît Pirot has published several papers, a great number of papers in this domain, and he's helped to the development of and the growth of SMEs within the lab in Itolis in Paris. So he's on both sides of the research and development, a researcher and a remarkable professor, but also he's keen of industrial development. And he's just a few words about his publication. He's published a lot of papers and received near 5,000 citation, and he has an H-index of 39. So Benoît, please, anytime if you are ready, the floor is yours. Thank you.
Yes, thank you very much for this kind introduction. I had a small problem of the speaker, but it seems
we hear you very well. We hear you.
Excellent. Perfect. So I'm going to share my screen.
Sorry. No, Noor, could you confirm that you hear Professor Benoît very well?
Yeah, I can hear.
Good. Thank you very much.
So, do you think that the audience can hear Professor Benoît?
Yes, yes, of course. Because they cannot speak with you now because all are muted. Yeah.
Okay. Thank you very much. Okay, please.
So thank you for your kind invitation to this e-conference. So I'm Benoît Pirot, and I'm going to present you indeed some way to print for sustainable development, at least for part of it, organic electronics, more particularly transistors, organic transistors, for sensing device, which could be applied to health monitoring. I'm from the BIOS group, laboratory Itolis, in Université Paris-Cité in France, Europe, in Paris. I can switch to the next slide. Yeah, it works. So here is the group of professors and assistant professors. We are in Europe, in France, then Europe, in Paris, are here in Paris, and in this quite nice building where you are more than welcome to visit us, to initiate collaborations, for example. Well, so I'm going to start by introducing, if needed, some concept of organic electronics. Then I will switch to some organic transistors, the way they function, were functioning, their architectures. Then some printing processes that can be used for making these devices, such as inkjet printing, and then the application of inkjet printing to earth monitoring and biosensing devices. If we look to the, well, let's say the development of the electronics during the last century, we see that it accelerated a lot, and that since the 40s, when the first field effect transistor was reported, up to now we switch from the, well, I would say macroscopic device to ultra, well, to nanoscopic devices in a few decades only. If we, sorry, I have some difficulties to switch from one slide to the other. I don't know why it's blocked now again. It works well, it worked well, but now it's blocked. Well, all right. And if you look to the development of polymers, polymers were developed, I would say, beforehand, of course, before, during it started before, during the last century. If we look to the time scale, it's quite funny because I would say that the last polymers that we know that we use every day were developed during the first part of the 20th century, and electronics after that, I would say. It corresponds. And actually it's funny because during this period here at the joint emerged, oh, sorry again, it's quite painful because I cannot switch easily from one, okay, slide to another. Yeah, so what I wanted to say is that as we can merge polymers, electronics and semiconductors together. And this was done at the joint between the development of polymers and the development of electronics to make organic electronics. What does it mean? It means that we are able to make semiconductors with organic materials. And this was first, as I said, reported in the 1950s. Conducting polymers were reported in the 70s. The first organic transistor was reported in 1986, sorry. And organic cells, photovoltaic cells, and OLEDs later on, but during the same period, I would say, in the late 80s. On the basis of polymers, like these ones, conjugated polymers, usually electroactive polymers. Even if for field effect transistors, as the one described here, polythiophene was not used as an electroactive polymer, but simply as an organic semiconductor, as silicon was at the time as well. So I'm absolutely sorry. I will switch to another keyboard to avoid that because I'm very far into my presentation now. Yeah, so if we look to the way organic transistors work. Here it is a bottom gate, sorry for the French, it is a gate, bottom contact transistor. It is made of a gate, metal gate, on a substrate, onto which you put a dielectric, an organic dielectric typically, then a source and a drain, that is two electrical contact, source and drain, between which you put an organic semiconductor on top. The source and drain are below, that's why we call that bottom contact, because it's at the bottom of the semiconductor. The electrical characteristics of such kind of organic field effect transistors are these ones. Here is the source drain current, or called drain current. Here on this x-axis, the drain voltage. If you don't apply any voltage to the gate here, there is no sufficient charge carriers here within the semiconductor. So even if you impose large drain voltage, you have no current. But if you increase slightly the gate voltage, then a field effect is formed, and then you attract, typically if the gate voltage is negative, you attract positive charges here within the organic semiconductor, here P3HT, which start to form a channel of charge carriers between the source and drain, and then your current start to increase, and it increases as a function of the gate voltage, low gate voltage, high gate voltage, and you plot the current as a function of the drain voltage for different gate voltage, and you get this kind of curve, which starts with a linear behavior here, ohmic behavior, and then deviates up to saturation here. You can even plot the current, drain current, or square root of the drain current as a function of the gate voltage. And then you get that kind of curve. Before that, you are able to form a channel of charge carriers. There is no current. And then at the threshold voltage here, you start to form a channel of charge carriers, and then it behaves linearly with the square root of, the square root of the current behaves linearly with the gate voltage. Here is the slope, which expresses the sensitivity of your device, and B, it is the threshold voltage, the voltage at which the current start to flow. Usually these conventional transistors work encapsulated, that is protected from water, protected from air, because the semiconductor may be not that stable in water, or in contact with water, or in contact with oxygen. The other kind of organic transistor is the organic electrochemical transistor. The general geometry is very similar, but the semiconductor and the gate, again, sorry, it is gate here, not the grid, are separated by not dielectric, but a slice, or simply, yes, let's say a slice of liquid electrolyte, typically water. And the semiconductor is no more conventional organic semiconductors that way, but in that case, but typically PEDOT, PSS, or any kind of electroactive polymer, because in that case, gates play the role of counter electrode, I would say, with which you can control the oxidation state of your semiconductor. When it's oxidized with a low gate voltage, it is conductive. And if you increase your gate voltage, you reduce the semiconductor, and then the current starts to decrease. But as you see, the electrical characteristics of such kind of transistors are significantly different from that of conventional field effect transistors. You cannot cut off the current completely, typically. Okay. However, the big advantage of this kind of transistor is that they can work in contact with an aqueous media, so they can be used for monitoring biological events directly in water, in aqueous electrolyte. There is, I would say, a third way. The organic electrolyte gated transistor that shouldn't be confused with the electrochemical transistor. There is no electroactivity in this case. The general geometry is very similar. Still a gate, an electrolyte, a semiconductor, source and drain, and a substrate, but this semiconductor must not be electroactive. This semiconductor must have a high molecular weight, must be highly hydrophobic and crystalline, dense, so that it is not electroactive at all. And upon polarization of the gate into this electrolyte, typically here negative polarization of the gate, you form double layers at the interface between the gate and the electrolyte and the electrolyte and the semiconductor. Gate electrolyte, electrolyte semiconductor. Typical double layers, very thin, very compact, which means that there is a high electric field, very high electric field through this very thin double layer, which means that the voltage drop between the gate and the channel is concentrated at each interface and not within the electrolyte, where we can suppose that there is no voltage drop, or very few compared to the strong voltage drop at these two interfaces. So the electric field sits at the interface, both interface, gate electrolyte and electrolyte semiconductor. Without any polarization of the gate, there is no current, because there is still no charge carriers between source and drain into the semiconductor. But if you impose a voltage to the gate, typically negative voltage, then electric field appear at this interface. You attract positive charge, that is holes, that is positive charge carriers into the semiconductor. It forms a channel and the current starts to flow with a very similar electrical characteristics than for the conventional here field effect transistors. Very similar, if not strictly similar. Very similar, but the big difference is that the threshold voltage in this configuration is usually very low, of a few hundreds of millivolts, not a few tens of volts compared to the conventional organic field effect transistors, which make this kind of transistor, the electrolyte gate transistor, fully compatible with operation in water. And I would say that in addition, this low voltage makes this device low energy devices compared to conventional organic field effect transistors. They can be used at low voltage with low energy in water. They are capacitance driven, which means that you control the current flowing between source and drain through the capacitance of your interfaces. The organic semiconductor electrolyte interface and the gate electrolyte interface, which are in series. So that equation. Which means that if you want to make a sensor with these devices, you have two possibilities: to functionalize the semiconductor, and it is possible, I will show you later on, or you can functionalize the gate. And both works. Both work. Depends on several parameters, but I have no time to go into such details here. Keep in mind that you can functionalize both interfaces, which is very convenient for chemists. So now that we know how these transistors, and typically the electrolyte gated transistor, but also the electrochemical transistor work, it's time to not to review really, but to show you that it is possible to fabricate such kind of transistors quite easily by printing technologies. And why printing technologies? Because it's convenient, because it's also eco-responsible in terms of material use, in terms of quantity of materials, in terms of energy needed to make these devices in lab, but also in the industry. As you know, very probably, if you want to make a pattern in a clean room through photolithography, you need something like 7 steps, starting from your substrate to end up with a pattern onto your substrate, because it is a subtractive process, which means that you need several materials, a lot of materials, and after that you remove most of what you put on your substrate. So you lose materials, you make a lot of waste that way. It is very powerful, it works very well for very laterally resolved patterns, but we don't need this so nice naturally resolved pattern every time. Sometimes it's sufficient to have bigger functions on your surface. And if you don't need precision at the few tens or hundreds of nanometer, you can use printing processes, additive manufacturing in general, using typically inkjet printing. Instead of 7 steps, you need just 1 or 2 steps. On your substrate, you just print your pattern, and probably it's going to be needed. You have to cure to sinter what you did. It makes a 2-step process, and it is an additive manufacturing, which means that you need less energy, you don't need any clean room to do so, much less material. You can print hundreds and hundreds of patterns with 1 milliliter of ink. You generate less waste as well, and it's less costly generally. Printing can be done using gravure printing, flexography, but we don't have these kind of heavy printing devices in our labs. Screen printing can be used. It is also a contact method, which means that your sample and the squeegee and the paste and the screen or are in contact with your substrate. It works well. You may have this kind of printing techno in your lab. However, it is a method which uses a lot of ink, which is usually very viscous. It's not an ink, it's usually paste. It works well, but the resolution is not that good. I will review that later on. You may also use fully digital, non-contact methods, such as the inkjet printing. It is a drop on demand, which means that you put your ink only where you want, where the patterns must be, and not anywhere else. If you look to some figures merit for screen printing, I will forget the gravure offset, or the original methods, but to focus on screen printing compared to inkjet printing. Screen printing use very viscous inks, very viscous. It's paste rather than inks. For inkjet printing, the viscosity is much less. Could be water. It could be water. The thickness with using screen printing is very, very thick. The layers that you make by using the screen printing are very, very thick because of this viscosity. On the contrary, with inkjet printing, it's very thin. The lateral resolution is medium to low for screen printing. I would say that is similar, maybe better slightly, but inkjet printing is not comparable with microlithography, of course. It's even not really comparable with gravure printing, but it's not that far. And you can use that in your lab, and you don't lose too much ink compared to screen printing. You don't use too much material compared to lithography, typically. You can use this inkjet printing process for small series for R&D in your lab. That can also be used for production in the industry. How it works? It is drop on demand, which means that you have a tank, an ink tank, then this actuator, it's a reservoir with a piezoelectric actuators on both sides, so that you can drive these actuators applying different potentials. These different potentials in black here are called waveform. So you drive your the deformation of your actuators with this waveform. There is several steps, let's say 3 stages or 3 steps to expel properly a nice, well-defined drop. This is done at more than kilohertz, several kilohertz. Okay, the celerity of the drop is of few meters per second between the nozzle and the substrate. Usually the distance is of, say, 1 millimeter or less. You must control the way the drop is expelled, and it is a science by itself, I would say. And you also have to control the drop spacing, the distance between the drops or your substrate, so to make not individual drops like it is illustrated here, but nice lines or simply nice patterns made of multiple, many droplets that fuse together on your substrate. Well, if you want to know more on this topic, please refer to this reference, which is excellent. You have to, of course, to take care of the rheology of your inks, that is viscosity, that is surface tension. Of course, you have also to take care of the energy, surface energy of your substrate, just to get nice patterns and not such kind of patterns if your droplets are not sufficiently dense, or that kind of patterns if your droplets are too dense, on the contrary. And again, I would say that is a science by itself. However, it works, but you should know how it works to print nice patterns. If you look to the result, I would say a drop on the substrate. You expect that upon drying, your drop end up like a disc of the material that was suspended in your ink. So drying makes a disc pattern, which is a disc in that case, with the same dimension of the, more or less, than the dimension of your droplet. If your drop is, say, 100 micrometer in diameter, then the disc after drying will be of 100 micrometer. It could be less using inkjet printing. I took 100 micrometer just for illustration. It could be down to say 10 or 20 micrometer. Okay. All right. So if you put many drops, then you are able to draw lines or any kind of pattern. The size of the drop is about 1 picoliter each. Okay. And I show this with the idea, well, that by hypothesis, this result, the line, the pattern that you want is result from an homogeneous deposit, which means that it dries properly with your ink drying homogeneously on your surface. That is what we can expect, but however, it is not always the case. I explain. If the droplet dries that way, that is with a constant contact angle, it dries, the radius or the diameter of the droplet decreases progressively, but the contact angle stay the same. It's going to make that kind of deposit nice, but difficult to obtain, because if your substrate is not that flat, if it's a bit rugose, which is the general case, the droplet will be fine. The contact lines here in green will be fine, which means that the drop will keep its diameter, but the contact angle will decrease progressively due to evaporation. And it will lead to the famous coffee ring effect. That is that kind of pattern at the end, and not a nice disc of your ink, but a ring all around, and maybe nothing inside, which is of course not what you want. It may be better illustrated here. It is even clearer with a concentrated ink. What is suspended in your ink will go, due to typically the Marangoni flux or Marangoni effect, to the side of the drop to make that coffee ring all around, and your deposit will not be homogeneous. So you must take care of that. But there is another way, or a third way again, which is the stick slip mode. If you can control the energy of your surface, if you can control the interaction between the particles in your ink. The stick slip mode is when your drop dries with decreasing contact angle and decreasing radius, and it makes this a smaller disc at the end, smaller than the size of your drop, which allow you to draw lines having a smaller, being thinner than the size of your narrower, not thinner, but narrower than the diameter of your initial droplets, which is nice. Again, please refer to the work of Vincent Noël, Justin Lemarchand, and colleagues if you want to better understand how it works. Now, some examples of printed organic field effect transistors. Here is the work of Giorgio Metana and colleagues who belong to the team. He simply print on a very thin, flexible, I would say even conformable polylactic acid foil using silver ink, a gate electrode at the bottom, and source and drain electrodes on top of the substrate. That way, to get these big here transistors, very flexible, very conformable, that can be used, and we will see some example later on, as a skin patch to monitor any biomarker in sweat, typically. Here is an example of printed organic electrochemical transistor. Please refer to the work of Magnus Berggren in Sweden for details on that. The transistors made of PSS in this case, because it's an electrochemical transistor, are printed directly on a PET foils. They are flexible, here not really conformable, it's relatively thick, but it could be. And it works perfectly well. Here is another example of an electrolyte gated organic field effect transistor, as I showed before, with a, I would say, a large here gate electrode, gold gate. It's a gold ink printed on Kapton foil. The source and drain, interdigitated source and drains here in between the gate areas, and we also print the well in PDMS. We print PDMS all around, and we of course print the semiconductor PBTT in here using inkjet printing, as you understood. These the size are relatively large here, but it could be crunched by say 10 very easily, and we did that. Of course, here is for an example only. The electrical characteristics of these fully printed devices are very similar to the one obtained with the non-printed EcoFET devices. Very similar, very similar. So it works perfectly well with printed device compared to non-printed conventional devices. Some applications, I will go maybe a bit faster. Here is the application of an electrochemical printed PEDOT-PSS transistor for monitoring neuromediators. Here, namely glutamate and acetylcholine. We included into the PEDOT-PSS some platinum nanoparticles using an organic shell so that this PEDOT-PSS with nanoparticles included is stable with time, which is not obvious, but it had to be stable. So we had to functionalize the nanoparticles with PEDOT, actually, well, with EDOT, the monomer. Then suspend these platinum EDOT nanoparticles in PEDOT-PSS. And we also included some enzymes, glutamate oxidase here, or acetylcholine, then choline oxidase to make an acetylcholine sensor here. Well, I skip details, but it worked very well as an electrochemical transistor for sensing, for monitoring enzymatic activity. Gaëtan Cheblin in Grenoble in France as well did, I would say, very similar work with an enzyme and even the mediator included not in PEDOT-PSS, but in kind of hydrogel on top of PEDOT-PSS for lactate monitoring, say in sweat, or making a skin patch. It can also be used for strain gauge. Here is a electrochemical transistor made of PEDOT-PSS, where Zhang and colleagues put onto which and colleagues put an hydrogel patch or hydrogel layer to keep humidity on top of the gate and top of the PEDOT-PSS channel to measure, be able to measure the strain applied to the device. So it is also something that can be used on skin patches to monitor motions. Totally differently, an example of logic gate, a NAND gate, not AND gate, made by printing. I forgot here, it was screen printing or inkjet printing, but they print some part, not all, but some part of their device, typically these carbon nanotubes, but not only, if I remember well, on their devices, to make a logic gate using a field effect, printed partly field effect transistor. Well, they of course print as well the silver contact, but also the nanotubes. And it worked well. I removed the example here, but it works well as a logic gate. Another way is to make a logic gate using electrolyte gated transistors, partly printed as well here. At least the semiconductors were printed here, if I remember well. So you can use electrolyte gated transistors to make logic gates in water. It is a droplet of water here, and it worked well, as you can see. Here is an example of a ring oscillator made by printing with some EcoFETs or ECFETs. Sorry, yes. Oh, EcoFET transistors with a nice gain, nice switch transition here. So, well, I could continue a long time. There is many examples of printed devices for electronics as this ring oscillator, for sensing as the electrochemical transistor or the electrolyte gate transistor. We exemplify this with by functionalizing a semiconductor with DNA into an electrolyte gated organic field effect transistor to sense DNA immobilization and DNA hybridization, even if it was not that satisfactory in terms of sensitivity, I should confess, but at least it was, and we are not, of course, the only one to do so. It was kind of proof of concept that we were able to functionalize the electrolyte semiconductor interface with an oligonucleotide in this electrolyte gated configuration. It worked. We were able to functionalize the semiconductor with the antibodies, antigens, or antibody-antigen recognition. Typically, here we functionalize our semiconductor with antigens. Then we put the antibody, and by a competitive decomplexation, we're able to remove these antibodies and then to sense by freeing up the surface the quantity of true analyte, that is the antigen, into the electrolyte of the transistor. We did so as with ions as well. I skip or I go faster because I have no time. We did so by functionalizing the gate as well, because I show you this interface is sensitive as well. And then we functionalize the gate with antibodies, with antigens, here with antibodies, with the same approach, competitive approach. We're able to sense here 2,4-D, which is a water pollutant, into the electrolyte of the the transistor. We did so with the ions as well. I skip. We also would say turn in a different way these transistors by showing that we are able to amplify a redox event occurring on the gate into a larger drain current. We did so by bubbling, say, oxygen on the platinum gate, and we demonstrate that it was possible to amplify the current gap coming from the reduction of oxygen on the gate here. Upon oxygen, it increases. Without oxygen, it decreases into a much larger drain current. When I say much larger, it means that the amplification is, say, of more than 100. And we apply this to the monitoring of the respiratory cycle of some photosynthetic microorganisms, such as cyanobacteria. We put the cyanobacteria into the electrolyte, and we follow in the light, or in the dark, the production of oxygen or the consumption of oxygen by a current on the gate, but most importantly, an amplified drain current. When I say amplified, in that case, it's up to 1,000 times bigger. Typically, when we immobilize the cyanobacteria directly on the gate electrode of this transistor, we got amplification ratio of more than 1,000 between the gate current and the drain current. And it was stable. But, well, what we did with microorganisms could be done on other organisms, I would say. Why only microorganisms? Why I switched to how we can use organic field effect transistors or organic electrochemical transistors or organic electrolyte gated transistors to monitoring skin, to monitoring health. Here is an example. It's not us who developed that, of a part of a sensor obtained by printing. This pressure sensor was partly obtained by printing, screen printing, if I remember well, and part of the electronics were printed as well, because as you can see, it is not a conventional substrate. It's not a conventional board. It is a polyimide Kapton board onto which some tracks, but not only the tracks, were printed. And then some other electronic parts were picked in place on this plastic board. Here, to monitor the pressure below a compressing bandage. First, another example as well of printed sensors for skin or health monitoring. Temperature sensor, a pH sensor. Here is the temperature sensor printed with the gold ink on Parylene C as substrate. Here is the pH sensor printed with polyaniline, a reference as silver chloride reference, which can be printed onto a PET substrate. To put this device into what? Into a dressing for monitoring a wound, possibly remotely, wirelessly. We are doing so with several sensors put together into a dressing or below a dressing or into a dressing. Here monitored with an Arduino Uno, but we are working to monitor this by a dedicated software and a dedicated device. On this plate, the PI poly plate, you can see here a pressure sensor, humidity sensor, and a pH sensor. And we did as well a lactate sensor, which is not present here, but we print all that. It's fully printed, fully flexible, even conformable. It works well. I'm not sure that I have time to demonstrate that it works, and actually the movie doesn't work, sorry, but it can be the pressure sensor here and the pH sensor and the humidity sensor are perfectly functional. Sorry for the movie doesn't work right in the morning. Yeah, well, okay. Here is the result of the pH sensor, still below that dressing. By just monitoring the voltage of our polyaniline electrode compared to a reference, we're able to monitor the pH of my skin, about 5, which is what is expected. Your skin pH is quite acidic, between 4 and 6, not more. If it's more, it's prone to infection. We also monitor, sorry, we had no sufficient volunteer here, so we took a glove, but we are able also to monitor the humidity below a dressing, so the humidity of a wound, because as you may know, a wound must stay wet for a good healing. It must not dry. That's the reason why we develop such kind of sensors, printed sensors. So to conclude, because my time is over, I think the printing can be used for organic semiconductors, can be used for metallic tracks, can be used for dielectric, can sometimes even be used for the substrate themselves. We are able to print polyimide. Any kind of soluble or sustainable materials, nanoparticles, microparticles. They can be used to fabricate large number of electric devices, transistors, strain gauge, pressure sensors, but also antenna, even thin film batteries. I didn't talk about that, but you can print thin film battery that way. It's easily accessible for R&D in your labs. It is relatively low cost. It consumes less energy than having a clean room in your lab. It is additive, not subtractive, so you lose less material, you need less material. It makes less waste. The cost is, I would say, that the lateral isolation is relatively low. And there is many parameters to control, it's true. Thank you for your attention. My time is over. Sorry if I was too long. And I can answer to any question if you have time. Thank you.
Thank you very much. Thank you very much, Benoit. It's a great lecture, very inspiring. So the lecture is open for questions if there are any questions in the audience. Dr. Kishore, do we see any questions? Okay, Benoit, I have maybe two questions.
Yeah, please.
The first one, you have shown very nice pictures of the huge complexity in drawing one line, one black line, and it's a question
Yeah.
of weighting. So is the formulation, I suppose that you change the formulation depending on the substrate on which you're going to print. So what are the adhesion issues to have a very nice black line you draw on the with carbon, for example, with carbon nanoparticles?
We are working and developing carbon nanotubes inks. You should control the interactions between your particles into the ink. Usually there are suspensions.
Okay,
Sorry?
The substrate must be very flat, or it should be...
It depends. It depends. It is also a question, as you propose, a question of porosity, of
roughness,
structure. It all depends on the surface energy of your substrate. Indeed, there is no general. At least we are not able yet to define general behaviors. There is many things to address each time we formulate or reformulate in ink, but we are looking for some parameters that could help printers to formulate and properly their inks. But there is, as far as I know, no general parameters. There is many parameters, not general rules. I would say no general rules for the control of the quality of your deposit. But yes, the surface energy must be controlled. Sometimes it needs to be really flat. Sometimes, on the contrary, it must be robust. It depends on your material. It depends if you are printing metals from metal nanoparticles. If you are printing metals from salt of the metal, it depends if you are printing organic materials. It depends on a lot of things. We work on paper, which is very porous. It makes something very tricky. We work on plastic. We also work on silica.
Okay, I want to take the advantage.
Different. Please go.
I want to take the advantage of the you're talking about paper, because a few 2 years ago I cited the paper from a Chinese group on biosensors or sensors for environmental sensors for printed on paper. So what they want is to develop sensors that you can burn after the applications, one use application. So are your smart surfaces, or maybe your group is working towards the development of disposable electronics with printed on paper, and after you finish, after one use, single-use sensors, you can throw it or destroy it or burn it, or because you mentioned polylactic acid, so I mean maybe you work on biodegradable smart sensors.
Not really, but I can answer to your question. We start working on paper typically for that purpose, to be able to say that our devices were easily how to say destroyable. However, paper is not only cellulose. It is not only paper. If you want to print something on paper, as when you write with a pen on a paper, it is not really paper. There is many other things, and even plastics on your paper sheet.
Yeah, of course.
If not, yeah, and it makes paper not so easy to recycle in reality. So, well, we switch to other substrates. PLA, yeah, typically, or other substrate. Paper, in addition to that, is, except if you put a quite thick layer of plastic on top, paper is very porous. So your inks go inside more than on. The lateral resolution is degraded, the drop spread, and you lose your lateral resolution. It's quite hard. So you can print on paper. You can say that you print on paper, but actually we don't print really on paper. We print on a layer of kind of plastic which is put on top of your paper or commercial paper. It's this is the reality.
Okay. Thank you very much. We are running out of time. Thank you very much, Benoit. It was a very pleasure to attend your lecture. Thank you very much, and have a good afternoon in Paris. So I'm going to move to the next session, next speaker, Dr. Christopher Schack. He's from Pennsylvania, from Drexel University. He's going to talk about MXene. I don't know how you can say MXene or MXene, 2D transition metal carbides and nitrides. And Dr. Christopher Schack received his PhD in 2018 from Notre Dame University in the domain of chemical and biomolecular engineering, and a BSc in 2013 from Princeton University. He received numerous awards for his work, including the Fulbright Scholarship in 2016. He's actually at the present time research assistant professor at Drexel Nanomaterials Institute. His research cover chemical kinetics, materials synthesis, 2D materials. Dr. Schack's work has led to a direct change in the definition of both MAX phases and MXenes. He has pioneered work into solid solution MXenes and has applied MXene work into many fields, including electrochemical energy storage, electromagnetic interference shielding, and biomedicine. A very broad topic. So anytime, Dr. Schack.
Wonderful. And so you see my screen in presentation mode, right? Or do you see my screen in the standard mode?
Yes, we can see your video and your presentation.
Perfect. Wonderful. So my name is Chris. It's a pleasure to be here. I'm very appreciative to the organizers of this conference. It has so many wonderful talks. And I'm fortunate to follow the previous talk because I don't have to go too in-depth into rheology of inks. So it makes my life a little bit easier. So what I'm going to do is I'm going to briefly talk about what MXenes are, why they're important, and then I'll get into some specific applications. If I can. Okay. So MaxScenes were discovered in 2011 at Drexel University. So it's one of the newer classes of two-dimensional materials. And unlike most other 2D materials, MaxScenes have metallic-like connectivity. So unlike most conventional 2D materials, which are semiconducting or really non-conducting, MaxScenes have conductivities up to above 20,000 Siemens per centimeter. They have a hydrophilic oxide hydroxide polar surface. So what this means is they are readily dispersible in water. So they don't require any surfactants, additives, or any crazy chemistries to get them to be inks, actually. They're strong and stiff, so they have over 20 to 30 gigapascals of strength, Young's modulus of over 300 gigapascals, which is the highest of any solution process 2D material. They can be transparent in thin films. So if you put down a thin enough layer of MaxScenes, they will be thin optoelectronic conducting devices. They're readily dispersible in water. They interact significantly with different EM waves or different radiation in general. They have a tunable work function that depends on both the chemistry of the structure and the surface chemistry of MaxScenes. And so we'll talk about that more in detail later on. But one of the things that is nearest and dearest to my heart is MaxScenes have a huge chemical diversity available. So there's over 100 stoichiometric MaxScenes predicted, more than 30 discovered, and then there's an infinite number of solid solution MaxScenes, so we can very readily tailor the properties. If I go quick enough, I'll be able to touch on solid solution MaxScenes a little bit, but I'm not going to get ahead of myself. So before I get into all of the properties of MaxScenes and go more in depth into the specifics, MaxScenes have been used for a large number of applications. So as I was introduced, I work on a number of these applications, but generally day by day, whenever I'm following different research articles, more articles come out focused on different new novel applications of MaxScenes. So they originally used in 2012 for electrochemical energy storage. So as rapid supercapacitor devices, and I'll show you why that was used in that sense. But because of their mechanical properties and conductivity, you can use them to make multifunctional composite materials. Due to their high EMI shielding, you can use, or due to their high conductivity, you can use them for EMI shielding as spray-on coatings even. They've also been used for a wide variety of other applications. This is by no means comprehensive: catalysis, water filtration, antibacterial. So we actually published a paper on deactivation of COVID using a variety of different MaxScenes earlier this year. You could use them for photothermal therapy, for gas sensing of hydrophilic gases, or spray on optoelectronics or antennas like you see here. So you can imagine it's an incredibly diverse range of applications. And this is in part due to all of its properties. It has many properties that make it very unique among the two-dimensional field. So in the previous talk, there was a lot of discussion about kind of exact formulations and how to get carbon nanotubes and carbon materials to disperse in different solvents. MaxScenes are actually readily dispersible in water. So we don't have to use any complex formulations. Just due to the synthesis method themselves, they will be readily dispersible in water. Now, depending on your flake size and your concentration, you change the rheology of your MaxScenes. So then you can use it for a wide variety of different solution processing material applications, whether it's spray coating if you have a very low rheology, or doctor blading to create thin liquid crystalline films. MaxScenes can be dispersed in a wide variety of solvents, so many different polar solvents, so ethanol, NMP, DMSO, for example. What you're seeing here is a spin-coated device made of Ti3C2 MaxScene put onto a glass slide. And then whenever you have MaxScenes put down, they're very conductive and stable for multiple years. So this was actually printed in 2017. We still have it floating around our lab, and it's still conductive today. So I'm going to go rapidly into a couple applications to just show some of the properties of MaxScenes. So one of the huge benefits of MaxScenes is not only that it's electrochemically active, but it is a pseudocapacitive material. So instead of being an electric double layer capacitor, it actually has a pseudocapacitive redox capability that occurs. But if you notice down here, because this is a two-dimensional structure with these nice galleries, you can actually very, very rapidly at, you know, what is this, 100 or 10 volts per second charge and discharge MaxScenes. And so depending on the thickness, you can change this. And if you produce hydrogels or other more porous structures, you can get incredibly rapid charge and discharge. And so this is incredibly valuable for supercapacitors. The electrochemical energy storage field of MaxScenes is incredibly broad, and it encompasses nearly every kind of energy storage ion, whether it's sodium, potassium, lithium, sodium sulfur, lithium sulfur, zinc ion batteries, and so on. This includes water and salt electrolytes and many others, which unfortunately I don't have enough time to go into today. So MaxScenes are also very optically interesting. So while many different two-dimensional materials like hexagonal boron nitride or graphene kind of have a set optical properties, MaxScenes, because of their chemistry and diversity of chemistries, are actually very different depending on how you want to produce them. And due to this, I showed you a transparent conductor already, but you can use them for photothermal therapy with near IR lights. You can use them as a surface enhanced Raman spectroscopy to increase your gas sensing ability or to increase your detection to below millimolar to micromolar quantities. You could use them for metamaterials, for light to heat conversion, or for different biomedicines to have controllable release of different drugs just based on shining lights on them. And to give you an example of how different these actually look, I'm a big fan of seeing is believing. It's possible for me to show the EM spectra and say it spans across the entire spectra. But if you don't actually see it, it's hard to believe. So what I'm showing you here is 9 different carbide MaxScenes. This is not a comprehensive set of MaxScenes by any means, but you can see qualitatively that the reflectivity of the films goes from green to purple and gold. And so the difference between these two is just another layer of titanium carbide or switching the transition metal from titanium to niobium. And you can see whether it's in transmission or reflectance, you get these different colors. And this is due to its plasmon resonance. So quantitatively, what you can see here, so here's Ti3C2 again, this green one, where it has a plasmon resonance centered around 780 nanometers, whereas Ti2C is over here at 550, whereas niobium 2C is over here around 1,000. So by kind of modifying these different chemistries or the structures slightly, you can change your optical properties to whatever's desired. And so you can see the extinction coefficient here, it depends very much on both the chemistry and structure itself. So while niobium 2C would be great for light to heat conversion, for example, or photothermal therapy, because it has an incredibly high extinction coefficient, others like MO2Ti2C3 have almost none. So you can imagine that will be very good for an electron transport layer instead. So by looking at these fundamental properties, it allows us to really delve into different applications that we may not know just by looking at the chemistries themselves. So I'm not going to go super in depth into the electromagnetic applications of MaxScenes as they are increasing kind of all the time. And so I showed you already antennas. We're using them for EMI shielding. You could use it for infrared radiation or IR camouflage, different kinds of detection, energy storage, and you can use very interesting dielectric properties to make very interesting kind of devices. But what I want to focus on specifically on this is just the range at which MaxScenes are interacting with EM electromagnetic kind of waves. This is over a huge different kind of frequency range, and it again depends very much on the chemistry and structure of the MaxScenes themselves. So I'm going to focus on only Ti3C2 for the next slide, but you can imagine every single MaxScene interacts with EM waves in a different way. You saw just with the optical properties themselves that they're all different, and so they're all different with optical properties, electronic properties, chemical properties, mechanical properties, and so on. And this makes them an incredibly versatile field of materials. So the EMI shielding field was a relatively conservative field. You would use metals or metal wires or deposit different kinds of metals, so namely copper, some other materials, and that would be EMI shielding. Now, because MaxScenes are highly conductive, like I said, 20,000 Siemens per centimeter or above is possible. If you spray down thin coats of MaxSeene, you can get the same kind of EMI shielding capabilities as even metals. And so you can do this at below skin depth levels for different metals. And this makes MaxSenes incredibly valuable. This is actually an older slide. And so we actually found out recently that some carbonitride MaxSenes will actually vastly exceed this EMI shielding capability significantly. And we also found out, I mentioned earlier on, the MaxSenes are electrochromic. And so if you apply a charge, you're changing its optical properties, but you're also changing its EMI shielding properties. And so we have a paper that was just accepted, which should come out soon, detailing this in more depth. And so you can see, I put a line here for the 40, I believe 50 decibel, which is 99.9999% EMI protection of EM waves. So I hope I've convinced you so far, briefly, that MaxSenes are an interesting class of materials in general. So now what I want to talk about is their manufacturing, synthesis, and how you actually make them, and why these have the potential to leave the laboratory and not just kind of languish in our research lab where we discover cool stuff. So I'm a chemical engineer by trade. So for me, one of the primary important things is that whatever I'm working on has the potential to be scaled up and has the potential to leave the laboratory and make an impact on our society. So there's kind of 3 steps to MaxSeene synthesis. The first is production of what's called max phases, or in some cases, some non-max precursors, but layered precursors in general. And so this is showing you the difference in the structures to get of an M2AX, M3AX2, M4AX3, M5AX4, and the difference here is just the number of transition metals with carbon and or nitrogen. So the M elements can be a wide variety of early transition metals, so titanium, niobium, vanadium, hafnium, tantalum, and many others. X is carbon and or nitrogen, and A is typically aluminum, but we could also do silicon or gallium. Now, production of max phases follows standard powder metallurgical approaches. So anyone who's worked in powder metallurgy, anyone who's taken a materials science degree knows you can make this at massive scales. You can do it in absolute tons per synthesis batch. There's no limitation on making ceramics in this sense. So there's no scalable limitation for max phases themselves. Now, if we look at the max phase structure, a little bit, this rotating one, what we're going to do is we're going to selectively remove these red atoms. So we're going to selectively remove them using a variety of different approaches, whether it's using HF, molten salt, you can use alkali extractions. There's now electrochemical approaches. There's halogenation. There's many approaches being discovered kind of day by day. And so it's a growing field. And what this does is this selectively removes these A elements, this red element layer, and that leaves us these big sheets of 2-dimensional materials held together with van der Waals forces. So this is what you're seeing here. So this is many sheets of MaxSeene held together with van der Waals forces, and you can either use that in this form. So if you want to use it for gas adsorption or for batteries, for example, you could use it in this form, or we are actually using it for wearable artificial kidneys now. Or you can delaminate it using a variety of different approaches, whether inorganic delaminants like lithium or sodium. You could use organic ones, so tetramethylmodium hydroxide. You could use a number of different solvents, so DMSO, or you can sonicate it itself. And what this will do is this will separate our MaxSeene layers, and it'll actually then make a stable colloidal dispersion in water or the other solvents that I mentioned. Now, you can imagine looking at these. So we've already talked about the scalability of synthesis of max phases, but nothing that I spoke about here is a bottom-up approach. It's all top-down approaches. So I can mix 100 grams of powder in with HF. I can mix 1,000 grams of powder in with HF. I can mix 10,000 grams of powder in with HF. There's no limitation of this in terms of standard chemical engineering approaches. Obviously, there's some technical things you have to work out as you get larger and larger volumes, but chemical engineers know that. And then the delamination approaches, again, there's no fundamental limitation. It's another top-down approach where you're adding lithium, which you can dissolve tons of lithium chloride in water, and you're intercalating it this way. So I'll show a little bit more about the scalability, But before we get into that, let's talk about why it's actually important. So whenever you're producing a material, whether it's a new 3-dimensional material, a 2-dimensional material, 0D, 1D, you have to be able to determine what you can use it for. If you can only produce milligram quantities, there's no reason to use it for environmental remediation or energy storage. It will never be feasible for that. But if you can make tons of this material, like tons, hundreds of grams, kilos, literal tons, then you can start looking at these kind of more material intensive applications, whether it's energy storage. I mean, we're all carrying our cell phones around with us. So you can imagine if I could only produce a milligram of the cathode or anode material, you couldn't use it for batteries. You have to be able to produce hundreds of thousands, millions of tons of material to use it for energy storage. Same is true of construction. Same is true of environmental remediation. And so MaxScenes, because there's many different levers that allow us to tune it, and I'll talk about a few of those, allows us to access this entire field. If we want to make incredibly highly conductive MaxScene that's nearly defect-free, we can do it. If we want to make super cheap, high volumes of MaxScenes with low cost, we could also do that. I'll talk about those two approaches. Now, in terms of synthesis of MaxScenes, like I mentioned, it's scalable. So this is just a flow diagram that we use in our laboratory for production. But I want to move past this kind of diagram and show you what this looks like in real life. So I showed you the reactors on a previous page, but so this is 1 kilo of the max phase, which we then turned into 1 kilo of our MaxScene, and we turned it into 160 liters of concentrated MaxScene solution. So to put this in perspective, 1 kilo of MaxScene allows us to make 5 million supercapacitors. It allows us to cover 225 square meters of a 45 decibel EMI shield, or to do 5.4 meters of EMI 45 decibel shield on cotton. It allows us to access these very large applications that most other 2D materials can't get to just by virtue of scalability of synthesis. So I will talk quickly on a couple things we can tune to actually change the properties. So I mentioned in some cases you want electronics grade material. So in that case, you need very large flakes, or if you want to do single flake studies, because we're scientists, you would want to make these very large flakes. So we can make 30, 40 micron MaxScene flakes from solution process. This is not from a bottom-up approach. This is from top-down, using a soft delamination approach we developed. Or if you use the standard approach, you get smaller flakes between 3 and 5 microns. And so you can choose which one is important for your application. In every case, it's not necessary to make super huge flakes. In some cases, having smaller flakes is actually better. So electrochemical energy storage, having smaller flakes makes it so your ion diffusion goes faster. And so in that case, it might be better to have larger flakes on the bottom as an electron transport layer and smaller flakes on the top to actually have the electrochemical energy storage. Now, another approach that you can do, and we actually just recently published this earlier this year, is you could actually take multi-layer MaxScene and delaminate using a 3-roll mill. And so you can imagine with this approach that it introduces more defects, and you're not going to get purely single flake MaxScene. But if you're using it for additives for composites, that's not necessarily important. It's not as important then for me to get only single flake MaxScenes. Having a few multi-layer flakes doesn't necessarily affect it, and it makes it a lot cheaper and quicker. And so you can imagine by changing our synthesis and changing how we're producing our MaxScene, it gives us a lot of versatility in actually choosing the best way to make MaxScene for our material. Now, let me see if I can get this video to play. So what we have here, and this is utilizing kind of our larger scale MaxScene synthesis, is we could start making skeins of different fibers. So we can make kilometers of different fibers. And this allows us to access a lot of really, really cool applications. Let me go to the next slide. And so I'll show you another one. So if you want to spray coat our MaxScene onto textiles, for example, you can use any conventional paint sprayer. We're using one from a hobby shop right now. and it's just going over and spraying on the Maxine, and it dries almost immediately on cotton. Or you could see, you could dip coat different fabrics or fibers. So I'm taking a Maxine solution, I'm just taking a conventional cotton t-shirt and dipping it right in. So I put a tape over it, so we have our DNI logo, as well as covering our t-shirt. And so you can see, by making these materials at these larger scales, it gives us this huge versatility that most other 2D materials can't do. So I made a completely Maxine coated t-shirt in 30 seconds. And so you can see our model. So Adam here is 6'3" wearing our t-shirt, and then that's the same t-shirt after Maxine coating. And so we can very rapidly produce this stuff. So why exactly are we interested in this? So for a lot of these flexible or wearable devices, you actually require larger amounts of Maxine. So if you're doing any kind of smart textiles, you have to be able to coat both the fabric or the fibers themselves, depending on what you want to do. So if you want to print on antennas onto a suit jacket, or have sweat sensors or biosensors incorporated directly into your clothing, you need to be able to produce this at scale in very fine resolution. If you want to do, like I said, printed supercapacitors, I showed we can produce 5 million of these in one go. You can make really any kind of electronic devices. So there's a phenomenal research scientist, Hussam Al-Sharif at KAUST, doing Maxine-tronics, where he's making electronics purely out of Maxines, which is absolutely phenomenal. So there's many really, really cool applications you can do. So now I'm going to switch gear kind of quickly to show off a little bit more of the versatility of Maxines. So I mentioned earlier on that we've pioneered solid solution Maxines. And so because Maxines have this tunable chemistry, it allows us to even go farther. Instead of having just these pure stoichiometric phases, we can then go into tailoring the properties exactly based on its chemistry. So I'm going to point you to this one, where we have the titanium vanadium M2X Maxine, and you can qualitatively see it's going from purplish, so titanium rich, to greenish, so vanadium rich. And if you look at the plasmon resonance here again, what you're seeing here is actually kind of a unique feature of Maxines. So it has two plasmon resonances, one related to titanium and one related to niobium. Moreover, you actually see that the plasmon resonance is shifting. So it means the electron density, or the local electronic state of the Maxine, of the M element, is changing based on its kind of neighbors. And so that's really cool. So as I said, these are plasmonic devices, they're electrochromic devices, and this allows you to then tune all of these different optical properties, electronic properties, EMI properties, depending on the chemistry of the Maxines themselves. So broadly showing this in a kind of quick way, as I realize I'm running out of time, depending on the Maxines, you could change, depending on the chemistry of the Maxines, you could change their electrical properties over multiple orders of magnitude, and this changes the EMI shielding capability and the absorption to reflection itself. This also changes the optical properties. As you can see, we have different optical properties here, and this allows pretty much any Maxine to be used for EMI shielding, depending on what you want to accomplish, by kind of looking at the entire picture of the properties of Maxines themselves. Now, this also allows us to do stuff like tunable and controllable electrochemical energy storage. You can go from Ti2C to NB2C, for example, here, and you can have different redox capabilities over at different potentials, and you get actually consequently different electrochemical energy storage. So in some cases, you get a synergistic effect between the M elements, and you can actually outperform either extreme using some of these middle compositions. So this is something that's pretty unique with Maxines and something that's incredibly valuable. It allows us, all of those applications I was showing you, to then pinpoint the exact best chemistry, the exact best Maxine to target that application for whichever specific application it is, whether we want to adsorb specific gases for gas sensing, or whether we want an exact capacitance or an exact EMI shielding or a specific color band filter. It allows us to do this with our chemistries. And like I said, there's over 30 discrete stoichiometric MaxEnes that have been discovered experimentally already today. There's many more being discovered all the time. I unfortunately don't have an infinite amount of time, or I could just be discovering them all day. Here's a non-comprehensive list that is actually out of date, even within 2 years. So I didn't get a chance to talk about this MaxEne, so the M5X4 MaxEne, which has incredible properties in and of itself. But there's many of these MaxEnes that haven't been investigated as in-depth as Ti3C2. So the MaxEne field is still wide open and huge for tons of research to get involved with. And it's possible, unlike many two-dimensional materials, to very nicely target these large-scale applications. So we can produce, like I said, a kilo in our lab. We're not an industrial facility. We can produce a kilogram of 2D material in one go. With that, I'd like to thank all of my funding sources. If you're interested in any of our articles, so many MaxEne articles, you can download them here for free. And so our password is here. And if you want to get a good overview of MaxEne properties in general, this article is a very nice review article we published that goes through how to characterize MaxEnes, what it means in terms of our properties, and broadly, how then you use MaxEnes. And if you're interested in learning how to make MaxEnes yourself or learning how to use them in different applications, we have a course in February where we have a team of assistant professors, PhD students, postdocs, and Yuri Gagotsi himself, who will be teaching some fundamentals applications of synthesis, characterization, electrochemical energy storage, and biomedicine. And with that, I would be happy to answer any questions you may have.
Thank you very much, Dr. Shak. Do we have a question from the audience, Dr. Kishore?
If anyone have a question, please raise your hand and I will unmute you.
See, if there's no questions, it means I was either perfectly clear or I completely confused everyone.
No, but you would not get away like that.
I want to ask a question. Namita, you are unmuted. You can talk.
Yes, sir. Thank you, sir, for your lecture. I want to ask that what are the important factors which we need to consider while synthesizing a MaxEnes?
So one of the things that's it's a good and a bad thing about MaxEnes is there's so many levers you can tune with MaxEnes. So like I showed, if you want to produce MaxEnes for electronic devices, so if you want to have very large MaxEne flakes with very high conductivity and very uniform, then you would want to produce them one way, where you want to produce a max in a specific way and then the MaxEne in a specific way. If you're doing something like catalysis, right, then you actually do want defect sites because those are more chemically active. Or if you want to incorporate different metals onto the defect sites, having more defect sites in that case might be good. And so in that case, you may want to use a higher HF concentration to actually induce more defects. So your question is it seems like a simple question on the surface, but it's actually an incredibly detailed question where it depends on what you want to do with your MaxEne.
Okay, are there any other questions? So if not, I have, Dr. Shak, I have discussed a while ago with some colleagues in Europe. I was interested in MaxEnes because they are I don't know if you can call them conductive clays. And I was surprised, I was disencouraged to work on MaxEnes because of their chemical instability. Are they really unstable, or do you work, or did you develop very stable MaxEnes, and maybe it will change my mind?
So I have another slide right next, actually, that shows this. We developed a way by reducing the amount of defects in the max phase. So we actually found out recently, about a year or two ago, that max phases themselves, while we say they're carbides broadly, we'll say carbides, they're actually oxycarbides. And so you can actually have oxygen in the carbon lattice. And if you have oxygen in the carbon lattice, this is where the defect sites happen, and then this is where the instability happens. And so we've actually optimized the synthesis to reduce all of these titanium defects and the oxygen incorporation in Melanus. And based on this, we have solution stable more than 10 months. We stopped measuring after 10 months purely because at some point we had to publish this paper. But even after 6 months, you see in Raman spectroscopy, we don't see any TiO2 formation. You see a TEM micrograph where you see these small pinhole defects that start occurring. But in general, if you optimize the synthesis, there's obviously going to be some less stable MaxScenes. So the thinner the MaxScenes are, the less stable they are. The thicker, the more stable. But based on optimizing the synthesis, I have some of that batch of that 1 kilo of MaxScene sitting still in lab after 6 or 7 months with really no change in properties. So by optimizing the synthesis, we can improve the stability by orders of magnitude.
Yeah, thank you very much. Thank you. It was a very, very nice lecture. I was very much interested because I worked a lot on the natural clays, and this is really very inspiring, and I really liked very much the content. You have done a lot of work on MaxScenes, and congratulations and good luck for the future. Thank you very much.
Thank you so much.
Okay, so now we're going to move to the next lecture. It will be given by Dr. Youssef Snoussi from University Paris-Cité. We had earlier Professor Benoit Pirot. It will be on biochar materials for sustainable medicine and agriculture. So a few words about Dr. Youssef Snoussi, which I know very well. He worked with me and in collaboration with his team in Tunisia. He received his PhD in chemistry from the University of Carthage in Tunisia, in the city of Bizerte, the northern part of northest part of Tunisia in North Africa. He developed mesoporous silica and joined the University of Lille for 1 year postdoc to work in the domain of catalyst and catalysis. With a lot of sustainable development aspects in his work. In 2021, he joined University Paris-Cité as assistant professor position and to work on biochar, another kind of mesoporous materials for water treatment, neglected tropical disease applications, and also possible potential smart agricultural applications. So Dr. Youssef, anytime, please.
Okay, do you hear me?
Very well, very well.
Yeah, just I'm trying to share the screen. I'm not able to do it. Yeah, I'm facing.
There is a share on the bottom of the screen. You can find microphone and video and share.
Yeah, and there is share too, yeah.
Yeah.
Yeah, there is open system preferences.
Yeah, you can choose your PowerPoint.
Yeah. No. Again. Yeah. Yeah, everything is no. It's not working. Let me try something else. Where is sharing?
You have to open your PowerPoint first.
Yeah.
Then when you press share, you will have you know the files that you opened already, and you can choose your PowerPoint.
Because I click on share, yeah?
Yes.
Yeah, it asked me to allow WebEx to share my
Yes.
content.
Yes, you have to allow WebEx to share your
Yeah.
content.
It asked me to open the system preferences.
Yes, okay. You have from your computer to give access for WebEx.
Yeah, I'm doing it. Just a moment. General. System preferences. Yeah, just a moment. Yeah, doing it.
It's okay, Dr. Yusuf, take your time. These things happen all the time with technology.
Yeah, we had the same issue with Professor Lahsini at the rehearsal on Saturday. On Saturday.
Usually it works, but I don't know what. Face up. Even I'm trying the mobile phone, but to get connected. I don't know what's happening. Open system.
Do you want to try with your phone?
Yeah, I'm going. Yeah.
Okay, I give you the access on your phone. If you want, we can proceed with Professor Al-Husseini while we are solving your problem. Would you like to do this?
Yeah. Yeah. Thank you. Just to make sure. Just the last trial. Oh yeah. Turn on storage.
Okay, we can proceed with Professor Al-Husseini if he's ready. Professor Al-Husseini, can you hear me?
Yeah, I'm hearing you.
Okay, do you
But
mind
now,
start?
yeah.
Okay, Professor Shahimi, you can proceed with Dr. Al-Husseini while we
I have
solving.
just to, okay.
No, not this one.
I am. Could you please give me the hand to share my presentation with you? Yeah. Okay.
Professor Shahimi, can you introduce Dr. Al-Husseini to us?
Yeah, of course. Yes, hello, Professor Lahsini.
Are you seeing my? Okay.
Okay, so yeah, we had this issue earlier, but okay, it's gonna be solved, I hope. Okay, so we have a keynote lecture now by Dr. Mohammed Lahsini from Morocco. The talk is about biodegradable materials from elaboration to application as coating materials of water-soluble fertilizer. Actually, I had the idea to invite Professor Lahsini because I was a reviewer of a remarkable PhD thesis from Morocco, which was directed by Professor Lahsini, and it was a remarkable work on this application for future and sustainable agriculture. So Professor Mohammed Lahsini is from Morocco, born in 1966. He received both master and PhD from the University of Bordeaux in France in 1991 and 94. He was supervised by Professor Bernard Joussom after postdoc with Professor Joussom in the same group. So in the same group, he started the academic career in Qadi Ayad University in 1995 as assistant professor, and in 2002 he was appointed full professor. From 2002 to 2019, he was several times as a visiting scientist at Helsinki University in Finland with Professor Timo Repo and Marco Leskela,
at University of Hamburg with Professor Hans Krischeldorf, also at University of Rouen, not far from this place, Qatar University from 2013 to 16, Zagreb University, and Orléans University in France in 2013. He was the recipient of the Alexander von Humboldt Research Award for experienced researcher. His research covers organometallic and macromolecular chemistry, heterogeneous catalysis for fine chemical synthesis, and homogeneous catalysis in biopolymers and bio-nanocomposite materials, and also green chemistry, including the chemistry of biosourced materials. He has published over 100 publications in reputed and high impact factor international journals. Professor Lahsini, please, anytime.
Thank you very much, Professor Shahimi, for this kind of introduction. I'm very happy to give my lecture today, and I would like first to thank my warm thanks to all organizing committee, and especially for you, because you contacted me last week, I think, 2 weeks ago, presentation. I'm very glad to give it today. So my presentation concerns basic from elaboration to application as coating materials. Today we'll try to talk about the application as coating materials for water solubilizers. So why we are interested to develop this kind of materials, this kind of biodegradable materials in our group? As I have a problem to as you know, production of plastics is increasing year after year, and as you can, in 2018, the production, it was around 379 million tons a year instead of only 2 million tons in 1950. So there is an increase in production and consumption of plastic. This is because the excellent properties of plastics. They have a good mechanical properties, density that is good for transportation, and also they have good barrier properties, and it's easy to, and it's low cost. It costs low cost if you compare it with other materials. So because of this, there is different application of plastics. If we look around, we have a plastic everywhere. So it can be used in agriculture, microelectronics, transportation, construction, and so on. But all this plastic, most of this plastic, the main source of plastic is petroleum, which is non-renewable first. And also the most of these plastic polymers are not biodegradable, and their accumulation in nature causes problem for environment for every country in the world. And these materials waste occupy a large volume in landfills and now we start to talk about plastic continents. A few years ago, it had reported that around 8 million tons are rejected each year in the I lost my presentation, Professor Shahimi. Are you hearing me?
I hear you, yeah.
But I lost. I have to share. Please, could you give me the hand to share my presentation?
Mrs. Noor? Noor? Hello, Mrs. Noor? Hello?
I'm sorry, Prof. I don't know why.
Yeah, no problem. I'm trying to contact Dr. Kishore.
I can hear you very well, Dr.
Oh,
Lahsani.
Yeah, just I have to share again my presentation because I don't know why suddenly it.
You left. Okay, I will give it to you backwards.
Yeah, thank you.
Yeah.
Just I repeat what their accumulation in nature cause a series of problems for the environment for every country in the world, and these materials waste now occupy a large volume in landfills and dams, and now we start to talk about plastic containers. And few weeks ago, it has been reported that around 8 million tons are rejected each year in the oceans and sea. That's alarm for environment. And as we can see over the next 30 years, we will produce 4 times as much plastic waste as now, and we should find solution for that. The solution is that to develop biodegradable polymer that has the same or similar properties as classical plastics. During the last decades, a lot of researchers and scientists, they looked for biodegradable polymer that can be developed, can be that can be removed from nature by biodegradation. And the most open polymers for this application are based in aliphatic polyesters, mainly polylactide, polyepsilon caprolactone, polydihydroxybutyrate, and their copolymers. All these polymers have a lot of application in pharmaceutical field and also in medical field. And now we start to have some application in electronic industry, agriculture, transportation, and textiles. So these aliphatic polyesters can be prepared by 2 different kinds of methods, by polycondensation reaction or by the Rein-Optine polymerization reaction. Polycondensation reaction, it's less expensive. Normally, it's convenient method. But with this method, because we can use, for example, lactic acid as monomer, and by condensation or polycondensation, we should prepare normally polylactide. But unfortunately, the polycondensation reaction led only to the low molecular weight polymer with a broad dispersity that they cannot be used for technical, as they have low mechanical properties, and also they cannot be used as a prepolymer for block or multi-block polymer, as they are prepared by broad dispersity. And also other problem with this method that we cannot achieve specific end group in the polymer. Sometimes we need to have a specific end group for some specific application. The other method that can be used to prepare these aliphatic polyesters is Rein-Optine polymerization of cyclic esters. This reaction leads to prepare high molecular weights with low dispersity, and also we can prepare block and multi-block polymer, and we can achieve
Dr. Lahsani, I think we lost the connection with Dr. Lahsani. Just wait for him.
Shami?
But Dr. Husseini, I gave you the access. You can proceed. It's
I'm
okay.
so sorry. I don't know why. I have
No
internet.
problem. No problem. This technical issue always like happened. It's okay.
That's okay.
Yes, we can see.
Yeah, thank you very much. And I'm sorry for this.
You can, if
So
you want,
the-
you can close your video just to make the internet faster and the voice clearer.
Okay,
If you
yeah, okay. Yeah, but anyhow, to remove the video. So there is also the anionic Raynaud-Payne polymerization reaction that is based in general of metal alkoxide and metals are sodium, potassium, and lithium, and magnesium too. But these catalysts are extremely reactive toward the Raynaud-Payne polymerization reaction, and this cause non-control of the polymerization because of high difference between electronegativity of these metals and also with oxygen. So the balance or the catalyst between cationic Raynaud-Payne polymerization and anionic polymerization is coordination insertion polymerization that is really effectiveness method to prepare a good control polymerization, and it use in general metal alkoxide as catalyst. But this reaction or this way normally necessitates to dry all reagents before used. And this reaction normally is based on metal alkoxide like aluminum, tin, titanium, tin, zinc, iron, and bismuth. And this reaction led normally to the good control of the polymerization reaction. We can achieve a specific end group, and also we can prepare block and multi-block polymer and also star polymers. In general, a good catalyst for the polymerization reaction should require the preparation of high molecular weight polymer by controlling the ratio between monomer to catalyst, and also should lead to control of molecular weight by controlling the ratio between monomer to catalyst, lead to the preparation of multi-block and the block copolymers, and also the catalyst should give the polymerization without side reaction. In our case, no racemization reaction or backbeating reaction. And the new requirement concerning aliphatic polyester as biodegradable polymers, when they are intended for medical and pharmaceutical application, that the catalyst should be low toxic. So if we look in the literature, there are a lot of metal alkoxide catalysts for the Raynaud-Payne polymerization reaction, but the most used one are based on tin metal complexes. They are tin 4 alkoxide and tin 2 alkoxide or octane white. The tin 2 alkoxide is the referential catalyst because it has been admitted by US Food and Drug Administration and food stabilizers, so it's not toxic. But this catalyst or this initiator for the Raynaud-Payne polymerization, in order to act as catalyst for the polymerization, we have to use alcohol as co-initiator. And as you can see here, this reaction is the equilibrium. So we have to use large excess of alcohol to form tin alkoxide that act as catalyst toward the Raynaud-Payne polymerization reaction. So, but this alcohol on excess in the technical production of polylactide or polycaprolactone can cause the anticipated termination of reaction by reaction with propagation chain, and then they stop the polymerization and lead to the end control of the reaction of the polymerization. While the tin 4 alkoxide are really good catalyst toward the Raynaud-Payne polymerization, we don't need to use the alcohol as co-initiator because we have this tin alkoxide bond that is the real catalyst toward the Raynaud-Payne polymerization. With this catalyst, we can prepare block polymer, multi-block polymer, cycle polymer, and we can control really the polymerization. And it has been reported also that more the alkoxy group on the metal increase, more the activity is higher toward the rheonuclein polymerization. But all these complexes, even if all of them are really active toward the rheonuclein polymerization, but they cannot be used for technical production, as this tin carbon bond, it's really toxic. So in order to benefit from the high activity of tin 4 alkoxide and low toxicity of tin 2 octane white, we were interested on tin 4 tetraalkoxide because there is no carbon bond between tin metals and alkyl. Then after hydrolysis of this compound, we form tin oxide that is admitted by American Food and Drug Administration. And also this complex will be more active if we compare it with all these 4 butylated tin 4 alkoxides. So we tested for the rheonuclein polymerization of lactide and epsilon caprolactone. Here I will show you only one example for the rheonuclein polymerization of the lactide. We use 3 different kinds of tin 4 alkoxide with tertiary oxide, tertiary alkoxide, secondary alkoxide, and primary alkoxide. And of course, we compare their activity with the standard one. As you can see, with tertiary amyl oxide and isopropoxide, we have a high activity if we compare it with tin 2 octane white. But with tin primary alkoxide, almost no reaction has been observed even after 20 hours of the reaction. This is because this complex, it's not monomeric, it's like oligomers, and it's still oligomers in experimental condition of this polymerization reaction. So it's hexacoordinate, and there is no free site for the initiation of the reaction because the mechanism of the reaction is complexation insertion. And we can see here also, we observe that the molar mass increase linearly with the conversion. This indicating that we have a really control of the polymerization. We are interested with control of the polymerization, but also with living character of the polymerization. To confirm if we have living character or not, we start first the polymerization of lactide till 90% of conversion. We take out sample to analyze with SEC, with chromatography, and we added the equivalent quantity of other monomer like lactide. And at the end of the conversion, we measure the molar mass by GPC. And as you can see here, after the first polymerization, we have 70,000 gram per Dalton. And after the second polymerization, we have double molar mass. But what is important, that we have monomodal curves indicating that we have block polymers. So this complex, it's a really, really good catalyst. Tin alkoxide are really good catalyst toward the rheonuclein polymerization of aliphatic of cyclic esters. But we should work in a really dry condition if we compare with tin octane white. That's limits the application for technical or for industrial application. Looking toward really high catalyst, less toxic catalyst, and stable enough to make reaction in a really simple condition, we explore some experiment that we have been done a few years ago concerning tin alkenyl compounds. We show and we demonstrate that tin alkenyl can react with alcohol to give tin alkoxide. And here we don't have this equilibrium reaction. We can use 1 alcohol, 2 alcohol, or 3 alcohol to substitute all of them or only one, and then we can control the polymerization. The hydrolysis of tin alkenyl lead tin oxide like tin alkoxide or tin octane white. And also, if we compare this with octane white, we will need not to use large excess of alcohol. That's sometimes lead to the non-control of the polymerization. And it's easy to prepare tin alkenyl. We can prepare phenyl acetyl lithium with tin chloride, and we can prepare the compound easily with the high yield. So when we prepare this catalyst, we use it with 1 alcohol as co-initiator. We form first tin alkoxide that act as real catalyst toward the rheonuclein polymerization. So, and we form the polylactide. As you can see here, we have a linear relationship between monomass and the conversion. This indicating that we have a control, good control of the polymerization. We don't have any side reaction. And also here, we made the same experiment that we have done with tin alkoxide, and you can see we form really block copolymer. This indicating that we have really living character of the polymerization by using tin alkenyl as catalyst and alcohol as co-initiator. What is important with this catalyst? Then we realize the reaction in bulk without using a solvent, like in technical production, without drying our monomer, neither the catalyst, without using alcohol as co-initiator, and we use the really high ratio between monomer to catalyst, because we cannot remove the catalyst from the polymer after polymerization because we work in bulk, normally in technical production. And as you can see, we use 10,000 to 1, 9,000 to 1, and 5,000 to 1. After the polymerization, we'll have small amount, some ppm of catalyst in the polymers. And at bulk condition, almost total conversion has been reached after only 15 minutes. And as you can see, we have really high molecular weight and high polymer. The challenge with this reaction was how to remove the polymer from the reactor. So we success to prepare, it was the first time in which we can prepare aliphatic polyester in open air reaction. So we explore this catalyst to prepare different kind of polymers. And as I told from the beginning of this presentation, the application that we attended with these polymers are packaging application and the coating fertilizers. So to have this application, we should improve some properties of these plastics, like thermal stability, barrier properties, mechanical properties, and also to have this balance between hydrophobic character to characteristics fertilizer coating, because we need to stop the water and to penetrate water. I will explain this later. So to improve these properties, it has been reported in the literature that we can incorporate some nanofillers with the polymers. So how we can combine a nano charge or nano reinforcement with these matrix polymers. So there is three kind of methods. Melt dispersion, in which we normally, this is convenient for industry because it's not need any special preparation. Just we melt the polymer, we add the fillers, we mix, and we have our nanocomposites. This is also dispersion solution. This is convenient method for water-soluble polymers. So we can solubilize our polymer and with fillers and mix, evaporate the water, and we have our polymers. And the third one is in situ polymerization. This is, we mix the monomer with the fillers and we start the polymerization in presence of the fillers. Or this method has been published with different kind of polymers. The melt dispersion is convenient method when the polymer is hydrophilic character and the filler is hydrophilic characters, and vice versa. And also this method is convenient when the polymer is hydrosoluble, but if not, we have to use the organic solvent, that it's expensive and not good for environment. The in situ polymerization, it's a good method when the fillers don't affect the control of the polymerization. I can just show you here. To melt mixed in, we have a polymer, fillers, we mix them, normally we have a composite membrane. But all the fillers that we used to increase the mechanical properties are normally hydrophilic characters, and the polymers, the polymers are hydrophobic. So after mixing, we have some fillers, so that's not good for mechanical properties. And other things that when we mixed aliphatic polyesters with the fillers with lots of OH group on the surface, it has been observed that the viscosity decrease. This indicating that at high temperature, the polymer we have decomposition of the polymers. So one good method to prepare this nanocomposite, biodegradable nanocomposite, that it's to use rhenoprene, in situ rhenoprene polymerization of epsilon caprolactone with lactide by using nanofillers and the catalyst. The standard one, tin octane white, it's not good catalyst for this, because even polysaccharide and mineral clays, we have water inside, and it's hard to remove all water from polysaccharide and or mineral. That's why we tested the polymerization with our catalyst that we have used without drying the monomer, neither the initiator, and to see if we can prepare polymer with high molecular weight, and if we can control the polymer by controlling the content of nanofillers, and then we can see if we have really good mechanical properties or not. As you can see, this is the fillers, and we have the monomer and the catalyst. First, what is we treat at raw temperature, at normal temperature, we reacted our catalyst with the fillers. We have first this reaction between tin alkenyl with OH group on the surface of the fillers, and then we form tin alkoxide that can act as initiator for the rhenoprene polymerization reaction. And so we graft the polymer on the surface of the fillers, and after the end of the reaction, we have a really covalent bond between fillers and the polymer. As you can see, the reaction was carried out with different contents of fillers, even with hydroxide nanotubes or with guar gum. We used polysaccharide and the clay. We used different clays, but today I present hydroxide nanotubes as fillers and also as co-initiator for the rhenoprene. With guar gum, as you can see, the molar mass decreased by increasing the contents of guar gum, and we observe the same phenomena with hydroxide nanotubes. This is normal. Why? Because with low fillers contents, we have only small active center, and we have the same quantity of the monomer. So we polymerize in small, for example, here in 2 OH group, then the longer of chain is longer than 3% and then 5%. This is logic. And how to be sure that we graft our polymer on the surface of the fillers? We first characterize our nanocomposite with IR, and as you can see here, this is free guar gum, and here we have polycaprolactone, free polycaprolactone, and here we have nanocomposite with 1%, 3%, and 5%. And I have to tell you that all these compounds are pure one. How we did? We solubilize or disperse our composite in dichloromethane, and by centrifugation, we precipitate our nanocomposite, and we analyze, and then we can see that we have both fillers and the polymer. The same phenomena we observed with hydroxide nanotubes. And to confirm that we really graft our polymer on the fillers, what we did, we dispersed the guar gum, for example, in dichloromethane, guar gum plus free PCl in dichloromethane, and we disperse also our grafted polymer in dichloromethane. As you can see here, after 24 hours, we observe the precipitation of guar gum, but the polycaprolactone still soluble in dichloromethane, and here we have stable suspension in dichloromethane. The same phenomena we observed with hydroxide nanotubes, this indicating that really we graft our polymer on the surface of the fillers. And as I told during my presentation, that's the hydrophilic character. It's really important property for fertilizer coating. And as you can see, when we increase the fillers, the hydrophilicity increase, this indicating that we can control the balance between hydrophobic character and hydrophilic character, even with hydroxide nanotubes and guar gum, the same phenomena would observe. The mechanical properties increase by increasing the contents of the fillers with guar gum and also with hydroxide nanotubes. As you can see, the problem is with this melt mixing that as the fillers are hydrophilic character and the polymer hydrophobic character, normally in general we have not a good connection between them. And as here we graft the polymer with filler, you can see we have really homogeneous dispersion concerning the hydroxide nanotubes, and here also with guar gum we have really homogeneous distribution. This is the same image of neat polycarpolactone. Even for thermal properties, as you can see with guar gum, the thermal property is really important if you compare it with neat polycarpolactone, and also with hydroxide nanotubes we increase the thermal stability that is important for packaging applications. And as this polymer is intended for application, and after that we need to have its biodegradation. And as you can see, the biodegradability of polycarpolactone, for example, in the soil increase by increasing the contents of the fillers, even with hydroxide nanotubes. This is because normally the degradation of the polymer, it's like hydrolysis of aliphatic polyesters. As even guar gum and the hydroxide nanotubes are hydrophilic characters, so they absorb water, and this water can react with the polymer, and then we have infin this hydrolysis and decomposition of the polymer. So as I told, one of the application of these materials is to coat hydrosoluble fertilizers. Why we are interested to coat the hydrosoluble fertilizer? Because as you know, the population is growing year after year, and the use of fertilization it's needed year after year, and we use a huge amount of fertilizers to improve the yield of agriculture. For that, we use normally these hydrosoluble fertilizers, and unfortunately, these hydrosoluble fertilizers, it's fastly soluble in water, and the rate of solubilization, it's really high if you compare it with assimilation with the crops, that we lost between 75 to 40 to 75% of fertilizer, and that's led to the contamination of water, and also that led to use the fertilizer frequently, that cost more expensive, and also phosphate, for example, it's not renewable resources that we have to protect it. To resolve this problem, a lot of scientists and researchers has developed some coating agent for these hydrosoluble fertilizers. The first polymer that has been used is sulfur coating. This led to a control of release of the fertilizer, but this polymer, it's not mechanically stable. During storage and transportation, we have some failure, so we don't have normally a good control of the release of fertilizers. And since 1970, a lot of research and even application in industry use the synthetic polymer as coating agent toward for slow release fertilizers. These mainly polyacrylate, for example, and lead really good slow release nutrient, and the coating film without failure is mechanically stable, but the problem is that they are not biodegradable, these polymers. And in 1997, it has been reported that the accumulation of plastic residue in Arab land led around 50 kilograms per hectare per year. So this is not a good solution for we made lots of pollution with this kind of polymer as coating as coating agent for fertilizers. One solution is to use bio-based polymer like polysaccharide because they are available, not expensive, and biodegradable. But all these polymer are really hydrophilic character. So the problem, they cannot. They have bad barrier properties toward water. So we cannot control the penetration of water inside the granules. So the release, we cannot meet really the European standard to release this kind of nutrient. One solution, for example, I will show you here one example in which we use the chitosan as biodegradable polymer as coating agent. And here the red, this is uncoated granules. This is for liberation of phosphate, and almost 1.5 hours it's enough to solubilize all the fertilizer in water. But when we use the chitosan, we observe we have some delay, but it's not sufficient to attend standard regulation to have a good control of the release. To have a good release, we need to use double coating, inner coating and outer coating. Inner coating with chitosan and outer coating with wax, because wax is hydrophobic character. But this is not a good solution because it needs more time, more compound, and we didn't reach the standard condition to have this good slow release. For that, we explore our nanocomposite because we can control the balance between hydrophilic character. We have really good mechanical properties, and we can have good adhesion between films and granule. We can have this winning behavior, and also our polymer or nanocomposites are biodegradable character. So I show you here, we used granule fertilizers, and we coated with polycaprolactone grafted guar-gum and polycaprolactone grafted halosite nanotubes. We do the coating, it can be done by dip coating or by rotatory damp. So it's easy to coat, and we can control the tint of the coated polymer. And as you can see here, we have really good adhesion between the coating agent and the granules. And in the surface, we have really homogeneous distribution between of our distribution of the coated materials. We studied the release of nitrogen here, and as you can see with guar-gum, this is no uncoated granules, and this is with 5%, 3%, and 1%, and this is neat caprolactone. And as you can see, with 1%, we have really good. We need around 50 hours to release the total nitrogen, and even with halosite nanotubes, we need more than 50 hours to release total. This is indicating that this material can be used as coating agent for control liberation of fertilizers. So during this presentation, I show you really good catalyst for open air polymerization of epsilon caprolactone and lactide in presence of guar-gum and halosite nanotubes. The molecular weights could be controlled by varying the content of during the polymerization. The same results show that we have homogeneous dispersion of fillers into epsilon caprolactone. We can control the release of fertilizers by using different kind of contents of polymer of fillers and the polymers. And these materials could have applications in industry. And at the end, I would like to thank my collaborator, Professor Timo Ripo from Helsinki University, Professor Krischendorf from Hamburg, Geraldine from Rouen University, Abdelkarim El Kadib from Fas University, Mustafa Rehan from my university, and my financial support, Center of National Research, Academy Hassan II, OCP, they give us lots of money concerning fertilizers, Alexander Van Humboldt and Campus France, and also my PhD student that worked in this research. And again, thank you very much for your attention. And I'm open for all questions if there is some questions.
Thank you very much, Professor Mohammed Al-Hassini. I know a little bit of the work, so I leave the question for the audience. If there are any questions on polymers, biodegradable polymers, and application for agriculture. Hello?
Raise your hand if you want to unmute you.
Sorry?
They must raise hand to be unmuted. Yeah. We have some participants, but they are quiet. Okay, so now I must ask a question. So for agriculture, we are interested in these porous materials to retain water below underground, so below the ground, to retain water for the plants or for the trees. So you use natural clays. So is it a way also, because you have also biodegradable polymers that degrade, while they degrade, they release the fertilizer. What happens afterwards? And what happens for the clay? The clay, okay, is compatible, it is natural product. Is it also the clay? Is it also a way to retain water, to attract water, or there is a repulsion of water? So you have to release the fertilizer, but also like these, for example, for my garden, I buy clay balls, 1 centimeter diameter clay balls, and then we put the soil, we plant and we put the soil. Do you intend? Did you work with farmers? Did you work also on the retention of water when you use these biocompatible, biodegradable polymer clay nanocomposites? What is your opinion on?
Yeah, it's like super absorbent. You know, the clay and polysaccharide are really convenient for arid, the region in which we have small amount of water. We don't have a lot of water because the clay can absorb water and the crops can use it. Can use it. And now, in collaboration with one biological department, we are testing these fertilizers to see versus the quantity of water. When we have only biodegradable polymer without clay and without polysaccharide, if we need more water than when we use, for example, chitosan and clay. And there is other work under. We try to use only clay as coating, not coating fertilizer, but cross-linker clay with fertilizers, and we are testing because with natural fertilizers we have some heavy metals that are not good for crops, and we observe that when we use the clay with fertilizers, we release only phosphate, for example, and the heavy metals still belong to the clay. Of course, we have to remove this clay, but we are using both clay as coating and also we use it in as composite materials.
I can't hear Professor Mohammed.
Ah.
The voice is clear for me.
Are you hearing me?
Yeah, I can hear you very
Dr.
well.
Kishore, I cannot hear Professor Mohammed.
But I can hear him very well.
We can hear.
Could you please repeat the explanation? Could you please repeat the explanation?
The use of these hydrophilic fillers, it's good for arid soil because it can absorb more water and release its water continuously with the time. And with collaboration with one biological department, we are testing the coated and uncoated fertilizer and coated fertilizer with only polymers and with composite by increasing the contents of these fillers, and we will see which one need more water to grow easily. And sure, when we use the clay, we absorb more water, and this water can release in longer time.
Okay, thank you very much. Thank you for the explanation. Dr. Kishore, are there any other participants who would like to ask a question?
No,
So-
everything is clear. Yeah.
Excuse me, Dr. Kishore?
Yeah, everything is clear. Yeah, please proceed.
Okay, thank you. Mohammed, Professor Lahsini, I thank you very much. Thank you very much. Thank you very much for your...
Again, I would like to thank you very much for the invitation, and my hello to our CAM teams that I visited 2 times a few years ago. And I hope that we will have the opportunity to make other presentation. Thank you, and have.
Thank you very much. It was great. Thank you.
Yeah.
Thank you very much. Okay, so the next speaker, we welcome again the technical issue has been solved. So I would like to introduce again Dr. Yusuf Snoussi. I briefly described his early career from PhD studies to now his postdoc, and he's now assistant professor at Université Paris-Cité to work on biochar, and there are things related in his ongoing research or near future research, something related to what we have just seen in the lecture, in the keynote lecture by Professor Mohammed Lahsini. So, Yusuf, anytime, please, for your lecture on biochar.
Okay, thank you, Professor. Do you hear me?
Yes, we
Yes,
can
very
hear you,
well.
and we can see the presentation also.
Okay, thank you. So first of all, I would like to thank the organizing committee for letting me this opportunity to present part of our work on biochar materials for sustainable medicine and agriculture. So I'll start by the general context. So nowadays, there is an ever-growing demand for highly functional nanomaterials for several applications, namely biomedical applications, in agricultural applications, energy production and storage. But these materials are still suffering from some important drawbacks related to the cost, to the procedures of production, to the noxious chemicals used for their preparation, and these procedures are time and energy consuming, and we have an important problem of biocompatibility. which is due to the side effects of these materials. So for these reasons, the biochar is considered as a future and prominent candidate for the design of functional materials. It permits its fabrication permits to the management and the valorization of the agro-waste, the tremendous and huge amount of agro-waste generated. The biochar is eco-friendly and biocompatible materials, simply prepared, and it has a particular physico-chemical properties, and it can be employed for a wide area in one wide area of applications. And the fabrication of biochar is cost effective. For example, to produce 300 kilograms of biochar from sugarcane bagasse, it costs only $440, all included. And the biochar fabrication process is a process that respects most of the 12 principles of green chemistry. So our main objectives is to study the influence of the initial biomass and its composition and its origin on the physico-chemical properties of the derived biochar. And we aim to valorize the two phases of the biomass. It's a solid phase to generate biochar, and the liquid extract to extract the liquid extract to enable the phytoreduction of metal ions. And we also aim to develop soft and green treatments of the agro-waste to enhance the textural and structural properties of the derived biochar by optimizing also the carbonization parameters, and design biochar-based nanocomposites for several applications, water remediation and anti-parasitic activity. So in this presentation, I'll put a special focus on the parasite for the anti-parasitic activity. I'll put a special focus on three parasites that are responsible for the neglected tropical diseases. So these parasites are two leishmaniasis and Trypanosoma cruzi, and the neglected tropical diseases are classified neglected by the World Health Organization because of the lack of financial support for research and development of new drugs, and the rate of pathogenicity and virulence caused by the germ, and because of the rate of pathogenicity and virulence caused by these germs, which is very high. For example, untreated visceral leishmaniasis is deadly in 95% of cases. And it is worth recalling that about 1 billion people are currently affected by neglected tropical disease. So let's have a look at the geographical distribution of leishmaniasis. So for 98 countries are classified endemic, and we are recording 1.3 million cases per year, causing between 20,000 and 30,000 deaths. For the Chagas diseases, we have almost 10,000 deaths per year, according to the Centers for Disease Control and Prevention. So we have started by the design of anti-kinetoplastid agents from olive peat, which is the powdered crushed olive stones obtained after trituration of olives. So we have proposed a simple and reproducible method to prepare biochar decorated with silver nanoparticles after wet impregnation of the biomass of the powder with silver ion, and then after carbonization of the impregnated biomass, a slow carbonization at 400 degrees and reducing atmosphere. So the characterization techniques revealed that we have obtained the metallic silver on the surface of biochar, and as we can see here in the same images, we got a high and even distribution of silver nanoparticles over the biochar surface. The performance testing of our nanocomposite was carried out by our collaborator in Spain at the Institute of Tropical Diseases and Public Health in Canary Island, and it was found that biochar decorated with silver nanoparticles have an exceptional antiparasitic activity with a very low toxicity. So, and actually we are working with our collaborators on the formulation of an ointment. So also we have used the sugarcane bagasse, which is an agro waste obtained after juice extraction and sugar production to prepare biochar-based material. So we have proposed a green and zero waste strategy aiming to valorize the two phases of the sugarcane bagasse. The solid phase to generate the biochar, and the liquid extract to enable the phytoreduction of methyl-ions. The biomass was first macerated and ultrasonicated to extract, and then to extract the liquid, the natural reducing preparation, and then the biomass was in situ impregnated with silver and copper methyl-ions before undergoing a heat treatment. To enable the phytoreduction of methyl-ions. So we have after filtration, we have obtained the sludge, which is the biomass loaded with methyl-ions and phytoreduced methyl-ions. This sludge was carbonized to obtain the biochar decorated with the bimetallic copper silver. So the liquid waste generated after this process was microwaved in order to generate a free bimetallic silver copper and supported nanoparticles. So as we can see here, as one can see here in the map images, the adopted method provided biochar with more pronounced microporous structures, and with a higher surface area. As the surface area has increased by 20%, and the total pore volume increased by 27%. The XPS analysis of the biochar materials proved the formation of the metallic phase on the surface of the biochar, and proved also the formation of the bimetallic after microwaving the liquid waste. So we have also obtained, as can be seen here in the map images, a surface of biochar fully covered by copper and by metallic copper and silver. The team images reveal that we have a high and even distribution of metallic nanoparticles inside the porous network of the biochar. So the curve fitting of the Raman spectra exhibited that the biochar decorated with the biochar after deposition of bimetallic copper and silver is more graphitized. So when we say more graphitized, it means that we have more fluid circulation of electron, and we have more fluid electron transfers, which may explain the high catalytic activity of biochar decorated with copper and silver in the oxidative degradation of methylene blue. So for the study of the antiparasitic activity of the biochar materials and the unsupported silver copper nanoparticles, so the results revealed that we got very good antiparasitic activity of the biochar material and very high activity of free silver and copper nanoparticles. And actually, with our collaborators, we are working on the experimental design to control the cytotoxicity. The cytotoxicity of the bimetallic copper silver in order to formulate also to prepare a formulation or a cream or an ointment. So this was for the antiparasitic applications of our biochar materials. Also, biochar has been used for the agriculture applications. It was found that the biochar improved the soil aggregation, and it is used for the contaminant remediation in soil, and for the nutrients retention, and it was found efficient to promote microbial proliferation. So actually, we are working on the encapsulation of bioactive molecules extracted from the biomass itself in the biochar generated from the same biomass for the antifungal activity and to ensure a controlled and prolonged effect of these molecules. So in conclusion, the conversion of agri-waste into biochar is a very practical and simple solution to manage and valorize the tremendous amount of waste. Biomasses with different initial compositions provide biochar with different properties, physico-chemical properties and morphological properties. Biochar has a very particular and unique tunable structural properties. It constitutes a prominent eco-friendly and cost-effective platform for the design of highly functional materials. Recently, it was reported by La Tribune, the French economic journal, that biochar is the new black gold. So before finishing, I would like to thank all people who have contributed to the completion of this work, and thank you for your attention.
Okay, thank you very much, Youssef. Thank you for your contribution to the lab in Paris. Now your lecture is open for questions. I hope there will be questions. I have been asking questions since yesterday morning, so I hope the participants will find some interesting questions for this for your talk. Dr. Kishore, do we have any questions? The audience. I will not ask any because I'm involved in this work.
Please, anyone wants to ask, just raise your hand and I will unmute you. Anyone from the audience? Okay, we don't have any question.
Okay, so if it is clear, so I would like to thank again Youssef. I thank him also very much for his contribution to this topic, which we started less than 2 years ago, actually, in Paris. And I am also very grateful to. We missed the lecture yesterday of Professor Jacob Lorenzo Morales. He was going to give a lecture on the treatment of neglected tropical disease with some encapsulated compounds, natural compounds, and all other stuff. So without delay, we will move to the next talk. Are we on time, Mrs. Noor?
Okay, thank you so much.
Yes.
Yeah, okay. So the next speaker from the University of Cambridge in UK is Dr. Yaryan. The full name is Dr. Yaryan Abdul Samad. He is going to give a lecture on 2D materials in space. He sent us a long short biography. He's assistant professor of aerospace engineering in Khalifa University in United Arab Emirates, and senior research associate and senior teaching fellow at the University of Cambridge. He's also the chief technology advisor to a climate change company called Levidian, based in Cambridge. This company transforms waste gas resources to graphene and hydrogen. His research work is based on developing graphene and 2D materials-based technologies for space and aerospace. He was among the team of scientists on the European Space Agency, the ESA's zero gravity flights, who were the first to test graphene in zero gravity. Very interesting. He has also tested graphene-based materials for application in space using sound in rockets. He's a member of the science team of Rashid rover, which is due for launch within 2022 by MBRC in Emirates. He is the recipient of several awards, such as Young Leaders Award in 2020 by the UK Young Professional Society. He has numerous other awards, something very impressive. It will take a 20 minutes talk. And in addition to his research, he teaches a graduate course on graphene technology at the University of Cambridge. He is a proud graduate of Khalifa University prior to moving abroad, and he obtained his bachelor degree in engineering from Ghulam Ishaq Khan Institute in Pakistan. He graduated from GIKI with 2 gold medals, one for best academic performance and another for best overall performance. As I told you, it needs a whole 20 minutes talk for his awards. So please, Dr. Yaryan Abdul Samad, anytime.
Thank you, Professor. Can you hear me well?
Very well. Very well.
Thank you, Professor Muhammad, for the very, very kind introduction. You didn't have to read all that, but thanks a lot. Thank you anyways. So I think you said it all, so I don't need to spend any time on the introduction. So I'm speaking on 2D materials. As you can see here. So first of all, I'll talk a bit about production of graphene and related materials. Their statistical characteristics. How do we print and quote or demonstrators, and as well as their application. So when you talk about graphene and related materials, they can be used for composites and sensors, they can be used for electromagnetic devices, they can be used for energy conversion and energy storage. But then graphene for every application comes from different kind of methodology, different resource, different methodology. For example, graphene can be made from grinding exfoliations, high shear exfoliation, ball milling, electrochemical exfoliation, ultrasonication, and then also some more pristine methods of making graphene in 2D materials such as CVD growth, epitaxial growth, annealing, wet chemistry, and whatnot. So among all these exfoliation techniques, I do almost all except for CVD and epitaxial. So we employ all these methods for producing 2D materials, including graphene. We take synthetic graphite more often than not for a simple reason, because synthetic graphite is considered to be more sustainable because graphite resources in earth crust are depleting. So we try to use synthetic graphite, which are particles of these kind of sizes, 15 to 20 micron mostly. For some applications, we use larger plate sizes and we expand them. And then we use our own proprietary technique, which is called high pressure homogenization, where we exfoliate these bulk crystals of graphite and for other 2D materials as well. So high pressure homogenizer uses shear exfoliation. So we basically fill the reservoir here with bulk crystals of graphite or other 2D materials suspended in a liquid, preferably water, and then we pump it at a very high pressure, around 2000 bar, through this micro channel, which is 100, 200 micrometer in diameter, and it's made of diamond. And then the shear forces here, so as you can see here, this is the distribution of shear forces around this diameter. So the shear forces in this region are responsible for exfoliating the weak van der Waals forces in bulk 2D crystals of 2D materials. So once we make these 2D materials, they are in the form of inks and suspensions, just like the one you see. They're very stable up to 6 months to a year. And then they are flake-like, as you can see here. And the distribution of lateral size is around 1 micrometer for a starting crystal, graphite crystal of almost 15 to 20 micron. And then this, of course, the distribution will shift to right or shift to higher flake sizes if we use a resource material which is bigger in size to start with. And of course, with these methods, we can achieve very high yield. So we are able to produce a kg of these kind of inks and suspensions, actually powder of material per hour per machine. And then we are able to develop inks and suspensions, stable inks and suspensions of graphene and 2D materials with concentrations starting from 0.1 until 60 weight %. So these kind of concentrations are unheard of. The use of these kind of concentrations is in printing, because you don't need a lot of printing passes in order to transfer as much material as you want for a particular. We've done detailed statistical analysis. So our PhD student has spent a lot of time to develop this method of statistical analysis of 2D materials in general using atomic force microscope. So these are the processed material after we have exfoliated. You can see the sheets of graphene here after 100 cycles, 300 cycles, and 500 cycles of processing in that machine. And using these images, we have developed a Python code where we have basically, we feed this image to the Python code, and we are able to gauge the size, the lateral size, thicknesses, geometry of all these flakes. So we have almost studied 1 million flakes with this method. And from the 1 million flakes, we have measured the area, basically is the dimension, lateral size, you can say. start with around these kind of sizes, lateral sizes, and then as soon as we process them, we are left with these flake sizes of exfoliated material. So these are based on, and then of course the number of layers. So the more you process it, the more lesser number of layers you get. So we can achieve up to 90% of exfoliation with this method, you could say. So we have done these statistics. Flakes. So this data here is for 1 million flakes of graphite. Okay, so this is some more statistical analysis where we have plotted the lateral size on one side and so with the processing, we can see that almost the processing results in lateral size and number of cycles. Their relationship is kind of linear. So the more you process, although you decrease the lateral size, but you diminish the thickness as well, which means that we cause more exfoliation. Anyways, I'll go ahead and I'll skip this statistical analysis because I think that I've said enough about statistics. So this is the Raman spectra of pure graphite, and then of course graphene obtained. So one would say that when we are exfoliating graphite, we are causing the material to induce defect, and because there is a D peak here, while we are getting this G peak of graphene in the 2D, but then there is additional D peak arising from the processing cycle of our exfoliation process. But then we have also developed a method of finding out whether this D peak is coming from the defect or it's coming from the edge effects. So we plot ID over IG versus the FW of the G peak, and then we find out that there is no particular relationship between the processing cycle. Means basically that there is these D peaks are coming from the edge effects. So these are, since we are exfoliating, we are decreasing the sizes of the crystals. So the edges are increasing, and this D is because of the edges and not because of defects. And then there are other methods of counting the defects. We've done those as well, where we don't find additional defects once we exfoliate. So our method is not inducing any defects, rather it is increasing the number of edges. Okay, so this is some more Raman of this material. Effects, but these are edge effects, and that's how the sheets of graphene after exposure. We've also made these inks and tested their electrical conductivities, because for graphene vesting, electrical conductivity is one of the most exploitable property per se. So we have exfoliated graphene here. We have exfoliated graphene with binder. And then we have normal graphene. So this is expanded graphene, normal graphene from the process that we adopt, and then graphene with binder. So the expanded graphite, which is pre-expanded first and then exfoliated to make graphene, it results in electrical conductivities of more than 10⁵ Siemens per meter, which is the state of the art in graphene-based exfoliated materials. Apart from graphene, we also produce other materials. So here you see the example of molybdenum disulfide. So this is also using the same method of high pressure homogenization. Then on the right side, you see this blue color. So this is molybdenum trioxide, again, produced via the same method as I described before. And then with this method, we're able to produce molybdenum disulfide or other 2D materials with concentrations much more than the usually perceived. For example, for molybdenum disulfide, we can produce 12 milligram per milliliter of disulfide suspended in IPA very easily, which can be inkjet printed or deposited by spray coating or other printing and coating methods. After we make these materials, including graphene and other related 2D materials, then of course their manufacturing is the next step. We adopt inkjet printing, screen printing, 3D printing, flexographic printing, spray coating, bar coating, nano-print litho, biodot printing, among many other printing techniques to deposit and develop these 2D materials into components and devices. So this is an example of a screen printed graphene on paper where we are achieving the resolution of around 100 micrometer with a simple printing technique. We can also do the same with flexographic printing. So the same inks can be printed just like a newspaper, basically using the flexographic printing technique and also 3-roll mill. We also convert these inks and suspensions of 2D materials into forms and 3D structures. So we simply directional freeze dry these structures to get structures, 3D structures of choice, and we can align them by controlling the freezing process. So as you can see here, different architectures of pores, and that's because we can control it with directional freezing process. And also we can also control the density, so we are able to produce high concentrations, as I said. So that's why we can also produce these forms and 3D structures of graphene and 2D materials with different densities up to 600 milligram per centimeter cube. Also, the shapes can be tweaked. We also can template coat these 2D materials. Exactly mimic the nickel form into graphene, and then you can see here that this is a hollow kind of a structure. Of course, these 2D structures are very low in density. Higher weights, much higher than their own weight. This is a typical structure under a videograph of these 2D materials. I hope that I can run it. So this is the 3D structure, 3D graphene of 2D materials under a videograph. Here you can see the scale. So these pores are around 5 to 10 microns each, and they can be, of course, tweaked, as I said, with directional freezing, and we can develop different kind of architectures. We also inkjet print these inks to make devices. Here you see an example of a fully inkjet printed graphene and molybdenum disulfide based moisture sensor. So here we can basically print these on plastic and silicon and many other substrates with very fast response rate. And we can also coat these 2D materials on textiles. For example, here you see a single fiber of textile. In this case, it's nylon. But we can coat them on polyester, nylon, cotton, wool, Kevlar, glass fibers, and many others. So we started this work in 2013. It has been followed around the world, and graphene and 2D material-based textiles have picked up as much as the Nobel laureate himself has started is doing a lot of graphene and 2D materials-based textile work, which we had started basically. And these are the textiles coated, uncoated, and then here coated with graphene and then twisted in situ under the scanning electron. When you twist them, you see that the coating is still intact until you twist them for 7 twist cycles, and only then you can see some cracks developing on the coating. Basically, these cracks are coming from the so the adhesion of coating is so strong that it can only be broken if there is a breakage on the surface of nylon. We have used these textile for pressure sensing. So this is a wristband out of these textiles where we can basically sense the blood pressure of our blood flowing through our veins. That's because these pressure sensors are 20 times more sensitive than the state-of-the-art graphene-based pressure sensors, and that sense the blood flowing through our veins with these. Now, some other demonstrators. I'll not waste a lot of time, so we have made these different demonstrators. Printed graphene on papers and plastics and textiles. So this is a smart belt using graphene. And also we have made shoe sole sensors of graphene for gaming applications. So this is me trying these shoe soles of graphene connected via Bluetooth to the snowboarding game. So we can play these snowboarding games using graphene-based shoe sole sensors. This is a graphene-based speaker that we've developed in collaboration. This is another demonstrator where we have printed graphene on papers, and we can play music, you know, kind of when we step on these pressure sensitive graphene-based papers, basically. So this is a graphene-based dancing floor, kind of, or music floor. So for space applications, we are putting graphene into looped pipes. So we are replacing the evaporator part of looped pipes with graphene. So the state-of-the-art material is stainless steel or nickel. So we either coat them with graphene or we completely make it out of graphene. And graphene is used for wettability. So we use these graphene-based looped pipes for space applications. Test them in a parabolic flight. So a parabolic flight basically is a zero gravity flight, which takes this kind of a path, is launched at around 150 degrees. Engine is turned off, and then, you know, it goes into a free microgravity condition. And because of this microgravity, we are able to test something in microgravity environment. And this is our test setup. So we have graphene-based looped pipe installed in this test rig, a space-approved test rig. And this is our experimental setup inside the microgravity flight. So this is me with my colleague. We are in the zero gravity and testing these graphene-based looped pipes. For recent test, which we have done flying from Bordeaux, France, where we have tested these graphene-based looped pipes for space applications in using a parabolic flight. So these are the results from the parabolic flight. So we have graphene and CNT-based wicks, the evaporators, which perform almost 8 times better than the state-of-the-art steel and nickel-based looped pipes. And then, of course, there is graphene only. Works well as well, but not as good as the graphene CNT combination. We have also launched the sounding rocket with some of our graphene experiments. So we are trying to understand the evaporation procedure of evaporation graphene using the sounding rocket. So we have graphene installed in the sounding rocket. So this was the first time that graphene was launched in space, basically, because the sounding rocket was launched to a height of 150 kilometers, which is above the Kármán line, which is at 100 kilometers. So this sounding rocket reached the space, and then we tested the use of graphene for space applications. Here we are trying to understand the printing and deposition of graphene. So we are trying to understand the evaporation of graphene. This is our experimental setup, and the graphene deposition is caused here with a heating element, and a magnetic field is basically applied in order to see the effect of electric field is applied so the evaporation of graphene inks and suspensions is studied with the application of an electric field. So this is the testing setup after it was launched and brought back, and then here we have these graphene-based inks which were then deposited. So this Maser 14 sounding rocket by Swedish Space Corporation was used, where our experiment was installed here, the ARS experiment, and then we studied the evaporation of graphene and other 2D materials. These are the results obtained. So the summary, the results are as follows. So we have, of course, completely different behavior of liquid evaporating, the graphene evaporation in microgravity compared to ground conditions. Here you can see the ground conditions without electric field and with electric field. So the difference between without electric field and with electric field in the evaporation in the ground condition is almost negligible. But when you are in the microgravity condition, you can see the wettability is different. And also with the application of electric field, the shape of the droplet is completely different. So this tells us that printing or deposition or evaporation process, wettability, all these phenomena will be different in microgravity conditions compared to the ground-based conditions. And we can basically quantify that and try to prepare ourselves based on such environment. So these are the results. So we have printed and deposited basically CNTs and graphene. So these 2 droplets, 1, 2 droplets, and then 3 and 4 droplets. So, we try to deposit as much as possible. And after that, this is graphene and CNTs combined. And also we have done graphene alone. Additionally, we are testing graphene also in the Rashid rover, which is being launched from, actually, I cannot disclose much about this, but you'll see it in the news. So we are launching this experiment with the Mohammed bin Rashid Space Center. We are we're in the science team of the Rashid rover, which is being launched very soon. We have around 11 graphene-based samples installed in this rover, which is going to the moon. And it will be the first time that 2D materials such as graphene and other 2D materials as well, which we'll disclose very soon, will be tested on the surface of the moon. So the experimental details will be disclosed very soon. So in conclusion, we actually perform large-scale production of graphene and related materials and their conductivity. We achieve around 150,000 Siemens per meter. We make inks and coatings, and then their applications for environmental, space, and energy and sensing applications. So with this, I thank all the collaborators, mentors, students, agencies for their help. And especially I would like to extend my thanks to my mentor, Professor Andrea Ferrari, and also very close collaborator, Dr. Carlo Iorio.
Hello.
Can you hear me?
Yeah, okay, thank you very much. Dr. Abdel Samad, a very nice lecture on graphene and so the lecture is open for discussion, for questions. Is there any questions, Mrs. Noor?
No, I can't see any hands.
Okay, so I have to, again, I have to ask. Okay, I can ask question. I had the questions, but I wanted to the audience to ask some. Thank you very much. It was really brilliant and very stunning SEM micrographs. It's really stunning. Very nice work. I would like to ask a question about just for the concept. Why there are so many applications with graphene, not with carbon nanotubes? Is it a failure? Carbon nanotubes, I find them more maybe interesting. They are worms, nanoworms or microworms. They have 2 dimensions. Why a Nobel Prize for Fuller-N nanotubes, and why not? Why the industrial applications, the more applied aspect concerned with graphene? Is there any specific reason for that?
Yeah, so it's a very broad and complex question, Professor Muhammad. But I mean, it's very general. You made it very generalized, but in general, CNT is much more mature than graphene, of course. And for fullerene, Nobel Prize was granted to Smalley, but the CNT invention did not get any Nobel Prize. And after that, graphene got the Nobel Prize. So I think CNTs in general is more mature because, you know, it has been around for much more time than graphene. So it has seen many applications before, but maybe because of a lot of studies on CNTs, there were also some toxic studies. So the toxicity of CNTs, it's kind of proven that it's a toxic material. It cannot be, you know, in contact with skin. It cannot go in vivo applications. It cannot, you know, be easily handled in a powdered form. As far as graphene is concerned, there are many studies on graphene, the toxicity of graphene, although there is no conclusive study, but more often than not, when people study the toxicity of graphene, they've come up with this result that it is not a toxic material. So this is also, I think, more encouraging for people to apply in different applications and with ease. And also, since it's a newer material, so the 2D material, the class of 2D materials, including graphene, they're very new, and some of the 2D materials actually have been around for only a few years. For example, Maxine was first made in 2011, and then since then, you know, it has picked up. And similarly, there are so many other 2D materials which have come recently, for example, silicene, etc., borofene. So the class of 2D material is getting a lot of attention. So we cannot say for sure where would it head, but I would like to believe that it's heading in the right direction because I'm also helping a company, and I'm one of the main people at the company to help commercialize the graphene and put it in real applications. So I would like to believe, and I strongly, you know, believe that graphene can make it to the market in a much better way than CNT did for a number of reasons.
Okay, and maybe a very short question. Because I'm interested, I'm working now on biochar. I see a lot of development of going from agro waste to biochar and then converting biochar to graphene. Do you think this is maybe a good way to produce in eco-friendly way the production of graphene from agro waste via biochar?
Definitely. So if you remember when I started my talk, I said that we prefer synthetic graphite over natural graphite because of sustainability. So in order to create or make graphene from biochar, you need to graphitize biochar, and then, you know, that's the synthetic graphite for us, and then we make graphene out of that synthetic graphite. So definitely,
you need to go high in temperature.
Sorry?
You need to go to a high temperature, very high temperature.
Yes, so you need to go to graphitizing temperatures in order to, make graphite out of any biological biomass per se.
Okay, thank you very much. Thank you. Thank you for accepting our invitation. It was great to listen to you. Thank you very much.
Lord Professor, thank you for giving me the chance.
Okay, so now we move to the last lecture. So the last lecture will be given by Dr. Wasim Haider on development and characterization of thin film metallic glasses for anode materials. I have a short bio. Dr. Haider is a tenured associate professor at School of Engineering and Technology in Michigan, Central Michigan University. He earned his PhD in mechanical eng from Florida International University in 2010. Then he got a postdoc fellowship in materials science and engineering at Pennsylvania State University. Afterwards, he joined orthopedic research labs as a research scientist at State University of New York. In 2012, he joined University of Texas, where he served for 3 years as tenure track assistant professor. His research focuses are on material science and biomedical engineering, with special emphasis on biomedical materials, surface chemistry, electrochemistry, bulk metallic glasses, and nanomaterials. His research is supported by NSF and the Department of Defense. So, Dr. Haider, please, anytime.
Okay, thank you very much. Do you see my screen?
Not yet.
Okay, let me see here. I'm trying to see how to.
On the bottom of the screen, you will find the mic, the video, and share.
Sorry, say one more time. Your voice is breaking up.
Yeah, on the bottom of the screen, you will find share.
Yes. When I go to share, it says the privacy settings only.
Yes, you have to give an access for WebEx to access your laptop.
Okay, let me see if I can work.
You have to go to setting and to privacy and give access for WebEx.
Okay, let me just go here really quick. I apologize. I'm not sure how. Usually we always use WebEx and it always works, but for some reason it's not working right now.
It's okay. Take your time.
Okay. Clicking on WebEx, but for some reason when I click on it, it's not working. So I apologize for the mistake. So let me see if I can.
Would you like to send me your PowerPoint and you want me to share it from my laptop?
Yeah, that would be great. I think. Let me see if I can.
My email is Noor. You know my email, Noor.
Yes, yes. Okay. Okay, I just sent you an email. Can you please see if you can open it? Should be there just in a few seconds. It's already gone from my side. Okay, do you have an email now?
Yes, I have it and I will share it now.
Okay, perfect. Thank you so much. So while you are putting everything, so
Okay, can you see my screen?
not okay, perfect. Yeah, you can make it. So thank you so much. I really appreciate it, and sorry for the technical difficulties here. So once again, my name is Wasim Haider, and I'm a tenured associate professor at Central Michigan University. So I would like to thank the University of Qatar for inviting me here for this talk. So today I will be talking on development and characterization of thin film metallic glasses for anode materials. So as you know, the transient implantable medical devices is gaining research enthusiasm as an emerging technology in biomedicine. So to provide the onboard powering of such devices, a biodegradable battery is a promising choice. So, however, the anode materials in such batteries, is usually made from either magnesium or its alloys, and they suffer from parasitic corrosion and also the faster discharge kinetics. And these are the two main factors that limit the lifetime of these devices. So in the pursuit of finding the better anode material, here in this research, we have developed a combinatorial development to fabricate the materials. So the last slide was basically a graphic or a abstract for my research. So we have combinatorial development. We developed this magnesium zinc alloys, and then we have studied its detailed microstructure using grazing angle X-ray diffraction and transmission electron microscopy. And then we have studied electrochemical analysis using the potential dynamic polarization test and electrochemical impedance spectroscopy. And then finally, we have also studied the charge discharge characteristics of this battery. Okay, next slide, please. So here, basically in this slide, it really tells you that we have a pure targets of magnesium. When I say pure, it's about 99.95% pure. So pure targets of magnesium and zinc are individually sputtered as well as co-sputtered using Nano 36 sputtering system. And that sputtering system is from Kurji, Alaska company. To develop thin films on the glass substrate. So as you can see here that I have named them from MZ1 to MZ6. So MZ1 is a pure magnesium target, or it's a pure magnesium film. And then MZ6 is a pure zinc film. And then from MZ2 to MZ5, as you can see that the concentration of zinc is increasing from 6 atomic percent all the way to 41 atomic percent. And also you could see that we have used RF and DC guns. So RF gun was used for magnesium and DC guns was used for the zinc. So we have also measured the thickness of these films. Next slide, please. So here you can see that we have a grazing incident X-ray diffraction of the films. So you could see that we have a fully crystalline structure to fully amorphous structures. If I go a little bit, so in this slides, you can see that there are 6 system MZX systems. So the single component system, which is MZ1, again pure zinc, and pure magnesium, and MZ6, which is pure zinc, demonstrate full-scale crystallinity as shown by the diffraction patterns in this figure. So the binary systems, however, exhibit different microstructures. So upon the addition of zinc into magnesium, so let's look at Mz2, which is about 6 atomic percent of zinc, and Mz3, which is about 20 atomic percent of zinc. In these two systems, some peaks of magnesium correspondingly disappear, and also more in 3 than in 2, so indicating a corresponding loss of full-scale crystallinity. However, no diffraction peak representation of zinc or any other intermetallic in both Mz2 and Mz3. So I have basically divided all of these 6 systems into 3 categories, A, B, and C. So A, as you can see, is a fully crystalline material, and B is showing some crystalline and some amorphous behavior, so I can call it semi-crystalline maybe. And then the C systems, which is Mz2 and Mz3, you can see a broad peaks, which is representing the amorphous behaviors. Next slide, please. Also, the major limitation associated with the biodegradable batteries is the rapid degradation of magnesium anodes in the physiological media. So we have used simply phosphate buffer saline to study the potentiodynamic polarization of the 6 systems. As you can see that at more negative potentials than OCP, the polarization trends demonstrate the kinetics of reduction reactions, that is, hydrogen evolution due to water dissociation and or reduction of any dissolved oxygen in the PBS. So again, Mz1, again, a pure magnesium, exhibits a highly negative corrosion potential. So you can see the E-core values of about -196 volts as compared to standard Calomel electrode in the PBS. Similarly, at such negative potentials, the dissolution of magnesium is controlled by the hydrogen evolution, which is thermodynamically favorable. Again, now if we move on to the Mz2 system with the addition of 6 atomic percent zinc to magnesium, the potentiodynamic polarization scans of the binary system demonstrate a shift in E-core towards the negative values. In this case, now it's only approximately, you can say, about -1.47 volts. So both the cathodic and anodic polarization trends are changed due to relatively positive reduction potential of zinc than magnesium and a limited kinetics of hydrogen evolution on zinc. So in simple words, I can say that in Mz2 system, the hydrogen evolution on zinc is kinetically slow and may control the anodic dissolution of magnesium. Again, I mean, I can talk more and more about these slides, but again, this is the overall trends, as you can see, that it's moving, in the negative potentials, and also the I-core values are also, moving towards the right. Next slide, please. So here in this table, you could see that we have listed all the E-core and I-core values, including the Tafel slopes. After finding the Tafel slopes, we found the beta anodic and beta cathodic, and we have listed them here for the comparative analysis. Okay, let's move on to the next slide, please. So here's a electrochemical impedance spectroscopy for MZX anodes. So in order to estimate the dissolution tendencies of MZX systems, the spectra are simulated using 2-time constant equivalent electrical circuit, which you can see all the way in the bottom right here. So the 2-time constant is proposed based on the single phase shift as a function of applied frequency. Also, the 2 capacitive loops at high and a medium frequency ranges are evident. Are evident in the Nyquist plots, as you can see. So the high frequency loop represents the impedance of corrosion film on the substrate, while the medium to low frequency loops represents the charge transfer processes at the electrode-electrolyte interface. So very quickly, let's move on to the next slide, because I have some of the values here. In this table, you could see that, so we have R1, which is the film resistance, basically. Then we have R2, which is the charge transfer resistance. and then we have RT, which is the total resistance. Total resistance is basically the combination of R1 plus R2. So we have calculated from equivalent electric circuits fitting, of the experimental EIS data. So let's move on to the next slide. Okay, so again here in the 2 electrode setup, so MZX systems, negative electrodes are sputtered, and the sputtered iron, or Fe, as a positive electrodes are coupled and immersed in PBS, shows a potential static EI spectra conducted at OCP, open circuit potential, of the MZX systems. So as you can see that all the systems except MZ6 exhibit a similar impedance trends in the Nyquist plots, consisting of the depressed semicircle in the medium frequency range that is associated with the charge transfer processes occurring at the electrode and electrolyte interface, basically owing to the galvanic coupling of MZX and iron electrodes. Again, the Warburg element appearing at low frequencies regions is associated with diffusion control processes. And if you look at the high frequencies, high frequency intercept at Z real axis represents the electrochemical series resistance, ESR, of the cells associated with the potential drop across the electrode-electrolyte interface at the resistance of the electrical connections. So let's move forward. Okay, so now this is an important graph, which is basically the galvanostatic discharge of all the 6 systems. So again, to assess the discharge performance of the sputtered MZX systems coupled with iron in a PBS, so galvanostatic discharge profiles are obtained again in the 2 electrode systems by implying 10 microamperes per square centimeter current density. So, so in this galvanostatic discharge profiles, you could see that the cell potential drops immediately upon the application of discharge current density, which is associated with the kinetic limitation of the electrochemical reactions. So very quickly, if you look at MZ1, which is pure magnesium, shows the highest output voltage. So again, with the addition of 6 atom% zinc, which is MZ2 system, the voltage decreases slightly, accompanied by the slight increase in discharge time at the same applied discharge current density, which is 10 microamps per square centimeter. However, both MZ1 and MZ2 shows a complete dissolution before reaching the cutoff potential, right? The other binary systems, if you look at MZ3, 4, and 5, sorry, if you can go back to the previous slide very quick. So if you look at MZ3, 4, and 5, they shows no sign of complete dissolution, rather an overall drop in discharge voltage with time and registered. So among the binary system MZ3 and MZ2, yeah, you can move on to the next slide, unexpectedly shows a quick drop in discharge potentials, while MZ4 demonstrate a longest discharge time. Again, MZ6, which is a pure zinc, due to much nobler electrochemical potential, quickly drops to the cutoff potential, demonstrating its main shortcoming as an anode material for such applications. So with that being said, now, sorry, go back to the previous slide very quickly. Just a couple things about, no, the next one, please. Yeah, this one. So in this figure, the average discharging rate of the discharge voltage, as well as the open circuit potential just after the cell assembly is shown. So owing to the more negative OCP of pure magnesium, which is MZ1 in PBS, and the large cell potential, approximately, I could say 1.6 volts, is observed that decrease to, so from 1.6 volts, it has decreased to about 1.3 with the addition of zinc if you look at MZ2 and MZ3, MZ4 and MZ5. So the cell potential after assembly is the maximum potential difference between the positive and negative electrodes. And then upon discharge, the over potential caused by the charge transfer processes and the diffusional processes may contribute to the decrease in charge potential under applied load. So yeah, let's move forward. So now with that being said, I would like to quickly go ahead and conclude. So positive shift in the corrosion potential upon addition of zinc. Similarly, the role of microstructure plays a very influential role in governing the discharge characteristics. As you could see that more and more zincs are being, when we add zinc into magnesium, it is becoming more amorphous, and that plays an important role in charge kinetics. Also, longest discharge time, approximately 2 times that of magnesium, is registered for MZ4 systems. That may be attributed to the amorphous structure. And last but not the least, a controllable strategy for tailoring the dissolution or discharge kinetics can be done with addition of magnesium and zinc. So with that being said, I would like to acknowledge so this work is basically from one of my graduate student, Mudassar Khan, and then I would like to acknowledge all of my collaborators and colleagues, Dr. Ishraq, Dr. Petkov, Dr. Fallman, Dr. Bullard, Dr. Dean, Dr. Sun, and our technicians and other graduate students. So thank you so much for listening, and I would be happy to answer any questions. And here is my email if any students or if anybody wants to reach me later for any potential collaborations or any questions, I would be happy to do so. So thank you very much.
Thank you very much, Dr. Wasim. Is there any question in the audience, Mrs. Noor or Dr. Kishore?
I can't see any hands. Please, if anyone wants to ask, just raise your hand.
I can see that it's the end of the day. People are getting tired, so they're ready for the closing ceremony.
Yes, it's 7 p.m. here in Qatar.
Okay.
Yeah, I'm
but
sorry.
Anyways, you have my emails. If there's any questions that you have in your mind later, you can always ask me, or now you can ask me, however you like it.
Yeah. Okay. Thank you. Thank you very much. Thank you. This is the last. It's very much beyond my expertise, and
That's okay.
This time I have no. It's silly. I have no question, but I have been asking questions since yesterday morning.
That's not a problem at all. I know it's the end of the day. Everybody's kind of tired, and
this is too far from my work. I've done a lot of work on the different materials, but this one is too far from my skills, my field of expertise. Thank you very much, Dr. Wasim. It was a pleasure to listen to you, and congratulations on your achievements, and good luck for the future. With this, we close CHEMIT, Chemicals and Materials for Emerging Technologies, 2022. This is the second edition. It's an e-conference. Hope the next one in person. So, Mrs. Noor, what?
Thank you so much, Professor Shahini. First of all, I would like, in behalf of all the organizing committee, to thank all the speakers, moderators, and also the participants. It was really, a concentrated course, but it was very informative, and I am so blessed to see such a good names in the schedule. I would like to thank also all the organizing committee, Chemistry Africa, UNESCO for collaborating with us, and I would like to announce the poster award. So just let me share my my screen. Can you see my screen? The announcement?
Yes.
So we have 4 winners. We have 2 winners for the first Best Poster Award. The first one, Dream Haji and Khaira Haji, for their poster entitled High Performance Multifunctional Smart Thermochromic Polymers for Chemical Industry. The next one, the first
Congratulations.
award also, for Anoop K for his poster entitled Concentrated Sunlight for Accelerated Stability Studies of Perovskite Solar Scales. So congrats, Anoop.
Yeah, congratulations.
The second award goes to Glenta Bridge de Souza for her poster entitled Development of Sustainable Biopolymer-Based Hybrid Foams as G-Post Water. Congrats, de Souza. And the last one, the third prize is for Vihab Broker for electrical characterization of 2D high-K dielectric gate stack on SI substrate. So I would like to congratulate all the winners, and I would like to congratulate you, Professor Shahini, for finishing this conference. And would like really to thank the Chemistry Africa for collaborating with us and helping us in organizing things. So thank you so much, and please do not hesitate to contact me or Professor Shahini if you need any question about the conference and for any future collaboration. Thank you
Yeah,
so much.
we would like to receive feedback and probably start to organize. I think this time the first edition was mostly dedicated to the editors and collaborators of the editors of Chemistry Africa and Emergent Materials. I would like to say that these 2 Springer sister journals will receive their impact factors in June 2023. Near 4 for Emergent Materials, near 2.3 for Chemistry Africa. The 2 journals are growing very fast and very well, and we have a very good teams of reviewers and editors to take the articles to a very high quality articles before publications. And I hope with Dr. Kishore and Professor Mariam will work from now on to prepare. I hope next edition will be in person. I hope somewhere in Europe or in Tunisia, the home of Chemistry Africa in North Africa. And I hope we will meet in person next time. But these 2 editions show that there is a great interest in sustainable development, and I'm wondering if we should not change the name to chemists, like chemistry and materials for emergent sustainable technologies. That will be more in line with sustainable developments. And I think the Dr. Kishore and Professor Mariam had a very great idea to switch to sessions sorted by sustainable development goals. With this, I would like to thank again all the speakers. We missed Professor Matt Dodd from Canada because he had some important medical consultation. And also we had, I apologize for Professor Jacob Lorenzo Morales. We missed his lecture on neglected tropical disease. I would like to thank all the speakers again and all those who attended this 2-day e-conference. I've seen constantly a lot of participants attending, and thank you very much. Thank you all in Qatar in Doha for organizing the e-conference, and I do hope we will the next one will be even more successful and longer, probably 3-day conference in person. Thank you very much, Mrs. Noor. Thank you, Dr. Kishore. We have done so well within a very short period of time. It was great, really great, and I hope you will have a great World Cup in Qatar, and it's an opportunity to meet people from the whole world in Qatar and Doha. Thank you very much, and if there is anything, maybe Dr. Kishore, anything to say last?
No, thank you, Dr. Shaimi. Actually, I do remember, when we start this conference schedule, it was too short.
Yes,
but
exactly.
Somehow we managed to bring all the speakers, including all the CAM members who came in front of to collect all the speakers, and they are the moderators also. They have been helped. I mean, this success is a collective effort from all the people. So congratulations, everyone. I said. I mean, Qatar University now trying to make it offline, face-to-face meetings. And I believe next year, maybe in March or April, sure, we will make it, offline, and everyone can meet together. That could be much better. You can for my collaborations and grants also, and I also thank Ms. Noor. 2 days we were just working continuously from the morning to evening. Yeah, thanks, Noor. I know being family that it's difficult for you, but even though you have been tried a lot. Yeah, thank you very much.
Thank you all. Stay safe and see you in another edition of the conference. Good night.
Night.
Thank you. Good night. Thank you. Thank you. Good night.